Often students in calculus at this point will start to ask questions about different integration rules. And one common question we get is, do we have a product rule for integration? Because often we'll have a product like x times sine of x that we need to take the integral of, and we don't have any formula that does it straightforward. So it'd be nice if we had some type of product rule for integration. And the answer is maybe we don't exactly have a product rule, but we have something that's close to the product rule that we're going to call integration by parts. The idea here is if I have a product, let's say f of x times g of x, and we'll just say that's equal to our h of x. And if I were to take the derivative of both sides, we would get, using the product rule of derivatives, the derivative of the first times the second plus the first times the derivative of the second is equal to our derivative. Now let's try and go backwards here, just for the sake of going backwards. Let's take the integral of both sides. So if we took the integral of both sides on the left, we would have the integral of f prime of x gx dx plus the integral of f of x g prime of x dx is equal to the antiderivative of h prime, and the fundamental theorem of calculus tells us that's just h of x. But from the beginning, we know h of x is really just f of x times g of x. And what I'm going to do next is I'm going to subtract this first term across. We're going to subtract the integral of f prime of x g of x dx from both sides. Ultimately, what we're trying to do is we're solving to get this middle integral alone. So when we do that, subtracting off, we're just left with on the left the integral of f of x times g prime of x dx is equal to our f of x g of x minus the integral of f prime of x g of x dx. From here, we're going to make a little bit of a substitution. We're going to see what happens when I let u equal my regular function f of x. So this first part is going to become u. And then we're going to have this other thing. I'm going to call it dv equal to the rest of it, the g prime of x dx. Well, we've got a lot of other pieces, so I'm also going to find du and regular v. Du is the derivative of u, so that's f prime of x dx. And v, that's the antiderivative of dv, and the antiderivative of g prime we know is just g of x. So when we put this together, we now have the integral of u dv is equal to f of x, but f of x we know is u, and g of x we know is v. So we'll say uv minus the integral, and if we look, we've got f prime dx. F prime dx is just du, and the g of x is just v. So we have the integral of v du. And so this integral becomes our formula, though it may not look like much right now, becomes our formula for integration by parts to break up the product rule. The integral of u dv is equal to u times v minus v, the integral of v du. And the idea here is we're going to have some product, some integral u dv that we cannot take the antiderivative of. Using this substitution, we'll end up with an integral that hopefully will be simpler that we can take the antiderivative of, which is v du. Let's see what this looks like with some examples. Keep the formula up on top as we do our first example here. Let's find, I referred to it earlier, the integral of x sine of x dx. Now, under normal situations, we wouldn't be able to find this antiderivative. But if we break it up into the piece that is u and the dv, let's let x be the u, and the rest of it, sine x dx, be the dv. Then we can find the derivative of u. The derivative of x is just dx. And we're also missing the v from our formula. V is the antiderivative of dv. The antiderivative of sine x is negative cosine of x. Once we've identified these pieces, we can plug them into our integral. The problem at the top should be our original integral, the integral of u dv, the integral of x times sine dx. Notice that's all in the top row. That's equal to u times v. U is x, v is negative cosine x, minus the integral of v, which is negative cosine. I'm going to pull the negative out, du. Notice when we set this up, the top row is our original problem. The bottom row is the integral we solve. Because now, keeping the x cosine of x by itself, plus we know the antiderivative of cosine is sine, plus a constant. And now we've got our integral of x sine x to be x, negative x cosine x, plus the sine of x, plus a constant. And that's how we break up our integration by parts. The big question to make integration by parts work, though, I'll put this over to the side here, number 2, is how do we decide what is the u? Because if we get the u and the dv backwards, the equation does not become simpler. If you want to see that work out in practice, go ahead and try that previous problem where you make the u sine of x and the dv x dx, and you'll see you'll end up with a much more complex integral. So how do we decide which part is the u? Well, a little acronym to help you think about it is the acronym ILATE. If you can keep in mind this acronym ILATE, it gives you the order that it is generally recommended you just go through to pick which piece is the u. First, if you see any inverse trig, that's your u. If you still don't have a u, the next thing you'll look for is, do you have any logs, usually natural logs. Those are going to be what your u is. If there's no logs, you're looking for algebra. Those are like any x to the n's, any polynomials. If there's no algebra, we'll look to making the trig, sines, cosines, and tangents. If not, we'll look towards the exponentials. Exponentials are like e to the x or 2 to the x. And we use that hierarchy to help us to decide which piece is the u. So for example, if I were asked to find the integral of x e to the 2x dx, first I see there's no inverse trig or logs, but I do see algebra, an x to the n, specifically an x to the first power. So u is x, dv's the rest, e to the 2x dx. For our du, we take the derivative of x, which is dx. For our v, we take the antiderivative of e to the 2x, which is 1/2 e to the 2x. Then we plug into our formula. Remember, our formula is the integral of u dv is equal to uv minus the integral of v du. multiplying, we've got 1/2 x e to the 2x. That's our u times v. Minus the integral, and remember the integral is going to be our bottom row. Let's pull the constant of 1/2 out. E to the 2x dx. And now I just solve this last integral. 1/2 x e to the 2x minus 1/2 times the antiderivative of e to the 2x is 1/2 e to the 2x plus a constant. Or simplifying, just multiplying the 1/2 times 1/2, we'll have 1/2 x e to the 2x minus 1/4 e to the 2x plus a constant. And we found our antiderivative. Should have been number 3. Number 2 was the isolate. Number 4, then, let's try another example. Let's find the integral of x squared sine of x dx. Again, going through isolate, we see that the algebra comes before trigs. So u is the algebra, x squared, dv is the rest, the sine x dx. du is equal to the derivative, 2x dx. V is the antiderivative, which is negative cosine of x. And now we go to our formula. Multiplying u times v is negative x squared cosine x minus the integral of the bottom row, negative cosine, bring the negative out. And I'm going to bring the 2 out as well. So we have x cosine x dx. However, we find ourselves in another situation that we can't take the integral of x cosine x. There's nothing, though, that prevents us from doing integration by parts twice. Let's do it again on this remaining piece. Again, algebra comes before trig in isolate, so x and cosine x dx. du is the derivative of x dx. V is the antiderivative of cosine, which is sine of x. And so, we still have our first term. Don't lose that first term from the first time. Negative x squared cosine x plus 2 times, also don't lose the plus 2. Now we have our integral. U times v is x sine of x. And the bottom row becomes our integral minus the integral of sine x dx. And now that integral is really easy to take. So looking at what we've got, the whole thing, negative x squared cosine x plus 2 times x sine of x minus the antiderivative of sine is negative cosine. So we'll do plus cosine x. And I'm just going to distribute that 2 through to spread it out. Negative x squared cosine x plus 2x sine of x plus 2 cosines of x plus our constant. Not forgetting that plus c. It should have been on the previous step as well. So sometimes we have to use this integration by parts trick 2, 3, 4, 5 times until we get down to something we can take the antiderivative of. Let's take a look at another example that gives us quite an interesting result. Let's take the integral of e to the x times sine x dx. Going through isolate, the trig comes first before the exponentials. So u is equal to sine x du, or dv, sorry, is e to the x dx. Our derivative of u, then, the derivative of sine, is cosine of x. The antiderivative of e to the x is e to the x. And so we end up with u times v, e to the x sine x, minus the integral of v du, the bottom row, e to the x cosine x. Oop, forgot my dx. Don't lose your dx. Well, the problem here is we can't take the antiderivative there either. So like the previous problem, why don't we do integration by parts again? Still, trig comes before the exponential. So u is the cosine of x. dv is the rest, e to the x dx. du then is the derivative of cosine, which is negative sine of x. v is the antiderivative of e to the x, which is still e to the x. Keeping everything we've got before, e to the x sine x minus u times v is e to the x cosine of x minus the integral of v du. Ooh, I lost my dx again. It becomes, let's pull the negative out, e to the x sine x dx. And I'm going to go ahead and distribute this negative through so we can see where we're at completely. E to the x sine x minus e to the x cosine x minus the integral of e to the x sine x dx. Well, again, we find ourselves with an integral that we cannot take. However, before we jump right back into integration by parts again, we should notice something interesting. The integral that we've ended up with is the exact same integral as the original problem. Remember, this whole expression is equal to the original problem, equal to the integral of e to the x sine x dx. It's equal to the original problem. So let's solve for that piece, that original problem piece. To get that integral all on one side, we're going to add it to the other side. That's going to give us e to the x sine x minus e to the x cosine x equals 2 times the integral of e to the x sine x dx. As we add anything to itself, we get 2 of them. Remember, that thing is what we're trying to solve for. We've got a 2 in the way. So what I'm going to do, I'll use brown now. We'll multiply by 1/2 on both sides. That way the 2's are gone. And what we end up with is, on the right, that the integral of e to the x sine x dx, which is the original problem, that's what we're looking for, is equal to 1/2 times e to the x sine x minus e to the x cosine of x. Don't forget, we still need to do plus a constant. We'll do the plus the c on the left. There's no reason it can't be on the left. But we end up with our final integral by doing integration by parts twice, and then we noticed, hey, we've got the original problem as part of our developing answer. So we can solve for that piece to find out what that piece is actually equal to. Quite a clever trick. Now, integration by parts centers on this original formula that we saw on the beginning. The integral of u dv is equal to uv minus the integral of v du. Most of our problems will work out that way. However, if special cases come up, we can use what is often called the tic-tac-toe method, also called the tableau method, which we can only use if the problem only has the last part of I late, the ATE. In fact, we can only use it if we've got the A along with either T or E, if we've got algebra hanging out with trig or exponentials. If we have algebra hanging out with trigs and exponentials, we can use this thing called the tic-tac-toe method to save us some work. If I want the integral of x to the 4th sine of x dx, notice x to the 4th, that's the algebra that we need, and the rest is trig, either trig or exponentials. This is when we will use the Tableau method or the tic-tac-toe method. To do this method, we'll set up one column for derivatives and one column for antiderivatives or integrals. The derivatives, as you would expect, is going to be the polynomial part, x to the fourth. And then what we're going to do is we're going to work our way down, taking derivatives of x to the fourth until we end up with 0. We have 4x cubed, 12x squared, 24x, 24, and finally 0. Then we'll work through the integrals with the other part, the sine of x. The antiderivative of sine of x is negative cosine of x. Notice I'm lining up my rows. The antiderivative of negative cosine is negative sine. The antiderivative of negative sine is cosine. The antiderivative of cosine is sine. And the antiderivative of sine is negative cosine. Next, what we'll do is we will connect diagonal rows through this table. And we'll start with a positive and start switching signs. Negative, positive, negative, positive. And what this table will do, or this little tic-tac-toe grid will do, is it helps us actually build the entire final answer. We're going to multiply times the diagonals. So this first diagonal, we've got a x to the fourth times we got a plus and a negative. A positive times a negative is a negative. So we've got x to the fourth times the cosine of x. Then the next diagonal is a negative, but we've got a negative negative, so that's going to make it a positive. 4x cubed sine of x. Then we've got a positive 12x squared times the cosine of x. Then we've got a negative 24x times the sine of x. And we have a positive times a negative, which makes it negative 24 times the cosine of x, plus our constant. And this is the antiderivative of x to the fourth sine x dx. Without the tic-tac-toe method, using traditional integration by parts, we would have had to done parts 4 times to get down to our final answer. And then make sure we don't make any errors with signs or distributing. Would have been a headache. But the tic-tac-toe method helps us simplify when we've got an algebraic expression with either trig or exponentials. Don't use this shortcut unless you're allowed to. If you're not allowed to, we have to use the traditional integration by parts rule. So try some of these on the homework assignment. Get really good at practicing these, and we'll talk about parts more in class. Next question we're going to look at as we do advanced integration techniques is how do we integrate a product of trig functions. And the short answer is we have to get creative with manipulating the trig functions to get them into a format that we can do integration either by regular substitution or integration by parts. So first we're going to talk about taking the integral of the cosine to some power of x times the sine to some power of x dx. And the first case we're going to look at is if either has an odd exponent. If j or k are odd. Our strategy we'll employ here is we will rewrite the odd exponent by pulling one out and use the fact that either cosine squared of x is 1 minus sine squared of x. Or similarly, sine squared of x is 1 minus cosine squared of x. So here's what that looks like. For example, if we want to integrate the cosine cubed of x sine squared of x dx. If both of them are odd, we can pick on either sine or cosine. Doesn't matter. If only one of them are odd, that's where we're going to focus our attention. So here we see that the cosine is odd. So what we're going to do is we're going to pull one of the cosines out. And that leaves behind, if we pulled one out, there were 3. It leaves 2 cosine squared of x behind. When we do that, we can grab the cosine that's got the even exponent and use our cosine right triangle property. When we make that substitution, we'll have the cosine of x times cosine squared is 1 minus sine squared of x times still the sine squared of x dx. And now if I distribute that sine through, we end up with, let's put the sine stuff first, a sine squared x minus a sine to the 4th x times, we still have that cosine x dx on the outside. But what's nice about this is if we make u equal to the sine of x, this is going to simplify really quickly, du being its derivative cosine x dx. And so we have the integral of u squared minus u to the 4th du, which we know is 1/3 u to the 3rd minus 1/5 u to the 5th. Or, substituting back, is 1/3 sine cubed x minus 1/5 sine to the 5th x, of course, plus the constant. And we found our integral. So our general strategy, if either one has an odd exponent, is we'll pull out one of them and then change the other one to using that right triangle trig identity of 1 minus sine squared or 1 minus cosine squared. And that'll make it into something we can do a basic u substitution with. Now, if we aren't so lucky and they both have even exponents, we need a slightly different strategy. If they both have even exponents, our strategy will be to use our trig properties. 2 of them specifically. The first one being that the sine squared of x is equal to 1/2 minus 1/2 cosine of 2x. Or that cosine squared of x is equal to 1/2 plus 1/2 cosine of 2x. Those substitutions will allow us to find something we can actually take the antiderivative of. So let's try an example. Let's do the integral of sine squared x cosine squared x dx. Both of them have even exponents. We're going to use these properties on both of them, both the sine squared and the cosine squared. And when we do, sine squared becomes 1/2 minus 1/2 cosine of 2x. Cosine squared becomes 1/2 plus 1/2 cosine of 2x dx. Let's go ahead and multiply this out. You'll notice we have a difference of squares here, a sum and a difference. So that's going to be 1/4 minus 1/4 cosine squared of 2x dx. Problem is, we again have a cosine with an even exponent. This just means we have to do the formula over again. So we've got the integral of 1/4 minus 1/4 times, and we'll use our formula for cosine squared, which is 1/2 plus 1/2 times the cosine of, and then we double our angle for x dx. If I distribute that 1/4 through, notice we'll end up with 1/4 minus 1/8 at the beginning. 1/4 minus 1/8 is 1/8 minus 1/8 cosine of 4x dx. And now I have something that I can actually take the integral of. That's going to give us 1/8 x minus, we can either use u substitution, or you might see the pattern coming, that it's 1/32 sine of 4x plus a constant. And so if they're both even exponents, we have to use these trig properties to make it into something that we can play with. And sometimes we have to use these properties over and over again as the expression gets longer and longer, but we still end up with something that we can quite nicely take the integral of. So sines and cosines. If the exponents, one of the exponents is odd, we can pull one of those exponents out. If they're both even, we use the trig properties. Let's look at a second product. This one takes a little bit more decision making, and that is finding the integral of the tangent to some exponent of x times the secant of some exponent of x dx. This is another one we have to commonly solve. First, because these integrals aren't as common, let's do a little recall. First, that the integral of secant squared x dx, we know that one to be tangent of x plus a constant. It's just the basic antiderivative rule. Also, the integral of secant x tangent x dx, that is the antiderivative of secant x plus a constant. And using substitution, we've gotten really good at taking the derivative, or I'm sorry, the antiderivative of the tangent of x dx, change it to sine over cosine, and then use u substitution, and we end up with the natural log of the secant of x plus a constant. And I'm going to give you one more, the integral of secant of x dx. Turns out if you multiply top and bottom by secant x plus tangent x, you get a nice little substitution that results in us getting the natural log of the secant of x plus the tangent of x plus a constant. So we're going to use those formulas throughout our work here as we work with tangent times secant. First thing I'll look at when I'm doing one of these problems is I want to know about the secant. First, if the secant is even and greater than or equal to 2. So the secant has an even exponent. I don't care about the tangent. What I will do is I will rewrite the secant to the j power of x. I'll pull out a secant squared. So we'll have secant to the j minus 2 of x times the secant of x, secant squared of x, sorry. And then I will use the fact that secant squared of x is equal to tangent squared of x plus 1 to write the secant to the j minus 2 of x in terms of the tangent of x. The idea is if I can keep the secant squared and make everything else into a tangent of x, then I can use u substitution where u is tangent and du is the secant squared bit that we've pulled out. So let's look at an example where we do just that. Let's do the integral of tangent to the 4th x secant to the 4th x dx. And I notice that secant is even. So because the secant is even, I'm going to pull out a secant squared. Tangent 4th x, when we pull out a secant squared, we're left with secant squared. And the goal is to hold on to the secant squared x and change the other one to be tangents so we can use a u substitution. So when we do that, the secant squared becomes tangent squared plus 1 times the other secant squared x dx that we're holding on to. This looks similar to the sine cosine problem we did, because now we have the integral of tangent to the 6th x plus tangent to the 4th x all times secant squared of x dx. And now we're ready to do our substitution. Because now if u is equal to the tangent of x, its derivative is the last part, the secant squared x dx. Just like we wanted, because now it simplifies just u to the 6th plus u to the 4th du, which is a very easy integral to take. U to the 7th times 1/7 plus u to the 5th times 1/5 plus a constant. Then we just substitute back to our tangents, because u is tangent of x, so we have 1/7 tangent to the 7th x plus 1/5 tangent to the 5th x plus a constant. And so if the secant is even, it will come out really nicely by pulling out a secant squared and changing everything else into tangents. Now, if the secant is not even, we're going to bring our attention to the tangent. First, if the tangent is odd, and there is no secant, we're just taking some integral of tangent to some odd power. What we will do is we will rewrite the tangent to the k of x by pulling out a tangent squared. It gives us tangent to the k minus 2 of x times tangent squared of x. The reason we'll do that is we can play with that tangent squared of x, and we have tangent to the k minus 2 times that tangent squared is secant squared x minus 1. And then if I distribute the tangent through, we end up with tangent to the k minus 2 times secant squared of x minus tangent to the k minus 2 of x. The goal here is we want to reduce down until that tangent of k minus 2 becomes just tangent to the first power. Because we know the antiderivative of tangent is the natural log of the secant. However, sometimes we're not going to be quite there yet, so we may need to repeat. The process again with this new tangent of an odd power. And we'll use the same process and the same formula to reduce tangent down by 2 again and tangent down by 2 again until tangent is finally reduced down to a first power. So, for example, if we want the integral of tangent to the 5th x dx, we'll pull out a tangent square. Times what's left is tangent cubed of x. And then that tangent squared becomes secant squared of x minus 1 times the remaining tangent cubed of x dx. Now, like before, we're going to distribute the tangent cubed through, and that's going to give us the integral of secant squared x tangent cubed x minus the tangent cube of x dx. Now, in the first part, I want to notice we're all set up for a substitution. If I make u equal to the tangent, du is secant squared, and that comes out really nicely. However, the next part is not so nice because we have tangent cubed. Tangent is still odd, and we don't know the integral of tangent cubed. So we're going to repeat this process again, just manipulating that tangent cubed using the same process. So now we have the integral of secant squared x tangent cubed x minus, pull out a tangent squared x times tangent x dx. Again, we're going to pick on that tangent squared, change it into secants. So we have the integral of secant squared x tangent cubed x minus, tangent is secant squared x minus 1 times tangent of x dx. Again, we're going to distribute through, and that will give us the integral of secant squared x tangent cubed x minus secant squared x tangent of x minus tangent of x dx. Actually, plus tangent of x dx, distributing the negative through as well. Being careful avoiding sign errors. All right, now we're ready to actually solve this. To help us solve this, we're going to break it into 3 integrals dx and solve each one individually. First, if we make u equal to the tangent of x and du equal to its derivative, secant squared x dx, this first integral becomes the integral of u cubed du, which is equal to 1/4 u to the 4th, which, when we substitute back, we get 1/4 times tangent to the 4th x. Similarly, on the second integral, if we make u equal to the tangent of x and du is equal to the secant squared of x dx, we end up with the integral of u dx, or du, which is equal to 1/2 u squared. Bringing down our sign, we are subtracting 1/2 times u is tangent of x, so tangent squared of x. Bringing down our sign of plus, and we know from our formulas the antiderivative of tangent of x is the natural log of the secant of x plus a constant. So that took a little bit more work, but the pattern and process was quite simple and straightforward. We pull out a tangent squared, change it to secants, see if we still have to pull out a tangent squared, change it to secant, and keep going until you finally get down to just an integral of tangent. Now, that's if there's no secant at all. If there is a secant, we're going to take a slightly different approach. Instead of making u tangent, we're going to make u into secant. Here's what it looks like. Number 4. So we've got an odd tangent with a secant. Our strategy is to rewrite tangent to the k of x, secant to the j of x, by pulling out a tangent and a secant, because tangent secant is the derivative of secant. So if we pull one tangent out, we're left with tangent to the k minus 1. Pull one secant out, we have secant to the j minus 1 of x on both of those, times tangent x secant x. Then we can use the fact that tangent squared of x is secant squared of x minus 1 to get rid of all the tangents so that we only have secant left. to write the tangent to the k minus 1 of x, we don't want that, in terms of secant. So odd tangent without secant, we try and change, we try to have a secant squared. Odd tangent with a secant, we try to have a tangent secant. Here's what it looks like. The integral of tangent cubed of x times secant to the 7th power of x dx. We've got an odd tangent hanging out with secants. As we discussed, we're going to pull out a secant and a tangent. So when we pull out a tangent, we'll have a tangent squared x left. When we pull out a secant, we'll have a secant to the 6th x left, with our tangent x, secant x pulled out, dx. Then what we can do is take our tangent squared and rewrite it using the fact that tangent squared is equal to secant squared minus 1. So that's going to give us the integral of secant squared x minus 1 times secant to the 6th x times tangent x secant x dx. And just as in the other examples, when we distribute that secant squared, we'll be able to use a u substitution. So we have the integral of secant to the 8th power x minus secant to the 6th power of x times tangent x secant x dx. And now we're set up for our u substitution, where u is that secant x, and du, its derivative, is what we pulled out to set ourselves up. Tangent x secant x dx. So that's going to give us the integral of u to the 8th minus u to the 6th du, which we can quickly take to be 1/9 times u to the 9th minus 1/7 times u to the 7th plus a constant. Switching back to our secant x, because u is secant x, we have 1/9 secant to the 9th of x minus 1/7 secant to the 7th of x plus a constant. And so if we have an odd tangent with the secant, what we can do is pull out a secant and tangent and then change everything else into secants. The one case that we haven't looked at yet is the one we prefer the least, because this one can get ugly fast. And that's if the tangent is even and the secant is odd. Because if the tangent is odd, we can either rewrite it with all secants and its derivative, or all tangents and its derivative, depending on whether or not we have a secant with it. If the secant is even, we can rewrite it so that we have a secant squared and then change everything to tangents. That's what we've done in all the previous examples. But when the tangent is even and the secant is odd, what we will do is we will use the fact that tangent squared of x is equal to secant squared of x minus 1 to write the tangent to the k of x power in terms of secant x. What that will allow us to do is use integration by parts, which is what we got good at doing in our last video. So let's look at one last example. Let's do the integral of the secant x times the tangent squared of x dx. And as you can see, the secant is odd, first power. The tangent is even, second power. So let's take that tangent squared and rewrite it. So we have the integral of secant x times secant squared x minus 1 dx. Distributing through, we end up with the integral of secant cubed of x minus secant of x dx. Now, if I write that as two integrals, the second integral, secant of x, we know is the natural log of secant plus tangent. But the secant cubed needs a little bit more work. So here's what we can do with that secant cubed. We're going to pull out a secant x, which leaves behind a secant squared x dx. That's going to give us something we can use integration by parts, because the derivative of secant is easy, and the antiderivative of secant squared is easy. We'll use integration by parts to work out this piece. Remember, we still have to do minus, and let's go ahead and take this integral. The integral of secant is the natural log of secant x plus tangent x plus a constant. But we're going to focus our attention with u being the secant of x and the dv being the secant squared of x dx. When we do that, du, the derivative of secant is secant x tangent x dx. V, the antiderivative of secant squared, is tangent of x. And so that integral becomes u times v, secant x tangent x, minus the integral of v du, tangent x times secant tangent. Let's put the secant first. Secant x tangent squared of x dx, minus, we still have the natural log of secant x plus tangent of x plus a constant. Well, it doesn't seem like we're getting any closer because we still have an odd secant and an even tangent on that derivative. However, if you notice, that integral is the original integral we tried to solve for. We learned with integration by parts, we just set that equal to what we're looking for, secant x times tangent squared x dx, and solve this algebraic expression for the integral. We'll add that to the other side. That'll give us two of them. So now we have secant x tangent x minus the natural log of secant x plus tangent of x plus a constant is equal to 2 of these integral secant x tangent squared x dx. To get rid of the 2, we'll multiply by 1/2 on both sides. And that gives us a final answer of 1/2 times secant x tangent x minus the natural log of secant x plus tangent of x plus a constant is equal to the integral we're looking for, secant x tangent squared of x dx. And we found our solution. So with these products of tangents and secants, or sines and cosines, we really need to pay attention to the exponents and how we can manipulate that exponent to give us something that we can use u substitution on, ideally, or in this last case, if we can't, because we've got an even tangent and an odd secant, we'll set it up to get integration by parts. These take a lot of practice to get used to the different situations, the different cases, so please take the time tonight to practice these. We'll see you in class to discuss them further. As we work with these advanced integration techniques, we're going to take a look at trigonometric substitution to answer the question, how do we take the integral of the square root of a sum or difference of squares. In other words, how do we take integrals that have the square root of a perfect square minus x squared, or the square root of x squared plus a perfect square, or the square root of x squared minus a perfect square? How do we take integrals involving those expressions? Those are very difficult to take generally with our current strategies, but if we use trig substitution and Pythagorean identities, these integrals become much simpler to evaluate, especially with the strategies we saw with the trig equations in our previous lesson. So first, just to review, the main Pythagorean identity that we know is that sine squared theta plus cosine squared theta equals 1. To get the other Pythagorean identities, we either divide by sine squared or cosine squared. If we divide by cosine squared, we end up with tangent squared theta plus 1 equals secant squared theta. If you divide by sine squared, you get the other one, but we're not going to use the other one today. These properties will help us simplify stuff down to integrals that are much easier to work with. So let's take a look at the three cases with the square roots of sums and differences. Let's start with the case where we're taking the square root of a perfect square, maybe 25, 9, 49, minus our variable squared. If we have a case where we have the square root of a squared minus x squared, what we will do is we will let x equal a times sine of theta. Now, when we do that, what that means, if I divide both sides by a, that means x over a is equal to the sine of theta. So we can build a triangle to represent our theta angle, a right triangle. Remember, sine is opposite over hypotenuse. So if sine is x over a, the hypotenuse is x. Sorry, the opposite is x, the hypotenuse is a. And the Pythagorean theorem tells us the other side is our a squared minus x squared. But what's nice is from this, if we let x equal a sine theta, then dx is equal to a cosine theta. Let's take a look at an example. Make that number 1 in black. Let's take a look at an example where we use this substitution and see how nice it simplifies our integral. Let's say we've got the integral of x cubed divided by the square root of 25 minus x squared dx. Notice we've got that square root bit with the difference of squares, 25 minus x squared. When we recognize that we have a perfect square minus x squared, we will always say, let's let x equal a, which is the square root of the 25, 5 sine theta. We know that means x over 5 equals sine theta, which means we can build a triangle to represent our angle, theta. X over 5 is the sine, and the adjacent side then is 25 minus x squared. We'll come back to that triangle in just a minute. Dx is the derivative of 5 sine, which is 5 cosine theta, d theta. There should be a d theta up above, too. That's an error up there. D theta is important, so we know what variable we're working with. So when we make our substitution, we end up with the integral of x cubed. X is 5 sine theta. So when we cube 5, we get 125 sine cubed of theta over the square root of 25 minus x squared. Square the 5, we get 25 sine squared of theta dx. The dx also gets replaced by multiplying by 5 cosine theta d theta. What's really nice is that square root is going to simplify very beautifully. If we factor out a 25, you get 1 minus sine squared theta. And 1 minus sine squared theta is cosine squared theta. And what's nice is this is all under a square root. And the square root of 25 is 5. The square root of cosine squared is cosine theta. So all of this is going to simplify to the integral of 125 sine cubed theta over 5 cosine theta times 5 cosine theta d theta. And then the magic happens. The 5's divide out, the cosines divide out. Really, all that we are left with to actually take the integral of is, I'm going to pull that 125 out, 125 times the integral of sine cubed theta d theta. Much easier integral to take than the original integral. We did this yesterday. We know with an odd sign, we're going to pull out sine squared. So we have 125 times the integral of sine squared theta times sine of theta d theta. Because that sine squared is 1 minus cosine squared theta times sine theta d theta. So that u can be the cosine of theta. Du is sine theta d theta. And so we end up with the 125 times the integral of 1 minus u squared du, which is 125 times u minus 1/3 u cubed. U is cosine, so we have 125 times the cosine of theta minus 1/3 cosine cubed of theta. Now that we finally got our answer, not forgetting our plus c, we can go back to x's finally. And that's where our triangle comes in handy. So now if I scroll, we're going to be scrolling back and forth. We've got 125 times the cosine of theta. Going to my triangle, cosine is the adjacent divided by the hypotenuse. So it's the square root divided by 5. The square root of 125, the square root of 25 minus x squared divided by the hypotenuse of 5 minus 1/3 times the cosine cubed, which is the square root of 25 minus x squared all over 5 cubed plus a constant. Extra parentheses that I missed there. So we're going to clean this up a bit. Technically that's correct, but it's really hard to see what's going on. Let's cube top and bottom. So we have 125 times the square root of 25 minus x squared over 5 minus 1/3 times, let's write this as a fractional exponent, 25 minus x squared to the 3/2 power over 5 cubed is 125 plus a constant. And if we distribute the 125 through onto both parts, it's going to reduce quite nicely. We end up with 25 times the square root of 25 minus x squared minus 1/3 times 25 minus x squared to the 3/2 power plus a constant. And let's actually settle there. That looks pretty clean to me for our final antiderivative. So it took a little bit of paper to get there, but the key that made everything possible was we let x equal a sine theta, and then everything simplified out quite nicely, giving us an integral that was much easier to solve. Notice the only thing we took an integral of was a simple polynomial, 1 minus u squared. And that was possible because of that trig substitution. So that is our strategy when we have a perfect square minus the x squared, the difference of squares. What is our strategy, though, if we're adding a squared plus x squared? See. Square root of a squared plus x squared. If we've got a squared plus x squared, we're going to do a very similar thing. This time we're going to let x equal a tangent of theta, which means x over a equals the tangent of theta. So if we build our triangle, x over a is opposite over adjacent, so the hypotenuse is the square root of a squared plus x squared. But what's nice about letting x equal a tangent of theta, then we know that dx is going to be a times its derivative secant squared of theta, d theta. This will allow us to use the other Pythagorean identity to simplify and clean up the problem quite nicely. Let's take a look at the integral of x cubed times the square root of 4 plus x squared dx. Notice we see the sum of squares, 4 plus x squareds, inside that square root. That is our key, that we're going to let x equal the square root of 4, which is 2, and tangent theta, because we're adding, which means x over 2 is equal to the tangent of theta. And so we can draw our little triangle from theta. X over 2 is the opposite and the adjacent. Square root of 4 plus x squared is the hypotenuse. Again, we'll come back to that picture when we get to our final substitution step. And now let's see how this cleans up our problem. Dx then is 2 secant squared theta d theta. And so we have the integral of x cubed. 2 cubed is 8, tangent cubed of theta, times the square root of 4 plus x squared. 2 squared is 4, tangent squared of theta, times dx. That dx becomes the entire thing, times 2 secant squared theta d theta. Again, that square root is going to simplify quite nicely. Following much the same process, if you factor out the 4, the square root of 4 is 2. Then we'll have 1 plus tangent squared, which you should know is secant of theta. So that square root is going to simplify to 2 secant theta, giving us the integral of, let's multiply these numbers, 8 times 2 times 2 is 32. And let's pull that 32 out front. 32 times the integral of tangent cubed theta times secant cubed theta d theta, combining those secants together. When we look at this expression that has a tangent cubed and a secant cubed in it, we know with an odd power of tangent, we can pull one tangent and one secant out, and then we'll end up with something we can do a secant substitution on. Keep the 32 out front. Careful not to lose the 32. And we're left with tangent squared theta and a secant squared theta times a secant theta tangent theta that we pulled out, d theta. Keeping the 32 out front, tangent squared. We know that tangent squared is secant squared minus 1 times secant squared theta times the secant theta tangent theta d theta, which is equal to, keeping the 32 out front and distributing the secant squared through, secant to the 4th theta minus secant squared theta times, I'm going to have to write small here, secant theta tangent theta d theta. All that stuff at the end, though, we know is going to become our du as we make our substitution. U equals secant of theta du then is secant theta tangent theta d theta. And so we end up with 32 times the integral of u to the fourth minus u squared du. And finally, after all the trig and all the algebra, we're ready to actually do calculus on a very easy, simple problem. 32 out front times 1/5 u to the fifth minus 1/3 u cubed plus a constant. Now, before we start substituting back, I'm going to do a little cleanup. I'm going to factor out a u cubed. And I'm also going to factor out a 15, 1/15. Gets rid of the fraction and combines as many of the u's together as possible. So we have 32 over 15 u cubed. And we factor a 15 out of 1/5. We're left with 3 u squared after 3 of them came out. Minus 1/3. Factor out a 15th. We're going to have 5. And all the u's came out. Plus a constant. And now we'll start substituting back until we end up with our x's. So we have 32 over 15 times u, which is secant cubed of theta, times 3u, which is secant squared of theta, minus 5 plus a constant. But now we can go back to our triangle. Secant is the hypotenuse divided by the adjacent. It's the reciprocal of the cosine. So the secant is just the square root of 4 plus x squared divided by 2. And so when we plug that in, we get 32 over 15 times secant, which is the square root of 4 plus x squared divided by 2, cubed, times 3 times the secant, which is the square root of 4 plus x squared divided by 2, squared, minus 5, plus a constant. Cleaning up then, let's do those exponents. 32 over 15 times, let's write the 4 plus x squared with a fractional exponent 3/2. Over 2 cubed is 8. Times 3 times the square root squared just gives us 4 plus x squared. Over 2 squared is 4. Minus 5. Plus a constant. And a little bit of cleanup. 32 over 8 reduces down to 4. And then I'm going to distribute that 4 onto both parts. So we're left with 1/15 times 4 plus x squared to the 3/2 times, and the 4's divide out, and we're just left with the 3. And I'm going to also distribute the 3 through. 3 times 4 is 12 plus 3x squared minus, distribute the 4 through. 4 times 5 is 20 plus a constant. And let's just combine our final like terms together, the 12 plus the 20, to get our final answer of 1/15 times 4 plus x squared to the 3/2 times, we've got a 3x squared minus 8 plus a constant. And we have our antiderivative. Again, it followed much the same strategy as before. We'll do a substitution where x is equal to a times the tangent of theta. Simplify the trig. And then it should simplify to something we can take, again, a very easy integral. The only actual integral we took was u to the fourth minus u squared. They should simplify to something we know how to integrate. Now, the one we just looked at here, the sum of a squared plus x squared, addition works both ways. So this would also work for x squared plus a squared. However, the first example we did, subtraction, the order does matter, and it does make a difference. So with the first example, it has to be the perfect square minus x squared. If the order is switched, and we have the square root of x squared minus the perfect square, we can still use a trig substitution, but this time we're going to let x equal a secant of theta and follow pretty much the same pattern. X over a then is equal to the secant of theta, so we can draw a triangle to represent our theta angle. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so x is the hypotenuse, a is the adjacent, square root of x squared minus a squared is the other side then. And we also can calculate our dx is a times secant theta tangent theta. Let's take a look at an example of what this looks like. Let's do the integral of dx over the square root of x squared minus 4. Again, we see that x squared minus 4 under the square root. That is our key that we are going to let x equal, square root of 4 is 2, secant of theta. Well, that tells us that x over 2 is equal to the secant of theta. So we can draw a triangle where x is the hypotenuse, 2 is the adjacent, and the other side is x squared minus 4. dx we also know is 2 times secant theta tangent theta d theta. Never forget the d theta, which I did on number 1 there. Now that we've got our setup done, we're ready to actually make our substitution. The integral of dx becomes 2 secant theta tangent theta d theta over the square root of x squared, but x is 2 squared is 4, secant squared theta minus 4. We should recognize that that's going to simplify with a 2. Square root of 4 is 2. Secant squared minus 1 is tangent of theta, which becomes very nice because the 2's divide out, the tangent divides out, and this equation simplifies to the integral of the secant of theta d theta. And we already know the integral of secant of theta is the natural log of the secant theta plus the tangent of theta plus a constant. This one simplified very nicely for us. So now to simplify back, we have the natural log of the secant. Secant is the hypotenuse divided by the adjacent, x over 2, plus the tangent. Looking at our triangle, the tangent's the opposite over the hypotenuse. The opposite over the adjacent. X squared minus 4 over 2 plus a constant. And now we have our antiderivative, or integral of dx over the square root of x squared minus 4. So all the trig substitution follows generally the same pattern. We need to identify which type we're talking about. If we've got a difference of squares, where the x comes first, we'll let x equal a secant theta. If we have a sum of squares, we'll let x equal a tangent of theta. And if we have a difference of squares where the perfect square comes first, we'll let x equal a sine of theta. And then all the problems solve pretty much identical from there. So take a look at practicing some of these, and we will talk about these in class as we look at them a bit closer. Good luck. Continuing to work on advanced integration techniques, we're going to answer the question, how do we integrate a fraction? Probably more appropriate to say, how do we integrate a rational function, which is basically just a fraction. And the idea behind what we're going to do is this. If you had to choose to integrate 3x over x squared minus x minus 2 dx, or to integrate 1 over x plus 1 plus 2 over x minus 2 dx, which one seems the easiest to do? Well, the first one, we don't really have a way to integrate. We could try to use u substitution with u equals x squared minus x minus 2, but then du would be 2x minus 1 dx. The numerator's 3x. There's no minus 1. That's not going to work. Versus the second integral here, we know the integral of 1 over anything is the natural log of that stuff, as long as the derivative's 1. We have to divide by the derivative of the inside if there was something in there. Plus 2 times the natural log of the x minus 2 plus a constant. And that quickly we're done, because the natural log is just 1 over the stuff. That integral is much easier to take. And that's the idea behind what's called partial fractions. The idea of partial fractions says I can take a fraction like 3x over x squared minus x minus 2, and that's going to be equal to some other sum of fractions. If we factor that denominator, we'll end up with x plus 1 times x minus 2. The numerator is still 3x. And the idea behind partial fractions is this fraction is the sum of some numerator, we'll call it a, over the first factor, x plus 1, plus another mysterious numerator, we'll call it b, over the second factor, x minus 2. So if we can solve this for a and b, we'll find out what values break this fraction down from one complex fraction to two simpler fractions. Well, we can solve rational equations by multiplying by the common denominator of x plus 1 times x minus 2 on each factor, x plus 1 times x minus 2 and x plus 1 times x minus 2. When we do that, the denominators divide out with several of the numerators, and we're just left with 3x equals a times x minus 2 plus b times x plus 1. And what's important about this equation is this equation has to hold true regardless of what value x is equal to. That means I can just pick any value for x I want and solve what we end up with. So let's pick something convenient. Let's pick something that'll make either a or b go to 0. Notice if we let x equal 2, that first factor on a will go to 0. So we have 3 times x, or 3 times 2 is 6, equals, the a part goes to 0. b is times x plus 1. 2 plus 1 is 3. Divide both sides by 3, and now we see b is equal to 2. We can do the same thing on the other factor. Let's let x equal -1, because that makes the last factor equal to 0. 3 times -1 is -3, equals a times x minus 2. -1 minus 2 is -3. And if we divide both sides by -3, we find out a is equal to a positive 1. So back on our original fractions, we have a over the x plus 1, or 1 over the x plus 1, plus b, which we found out was 2, is over the x minus 2. And this fraction is what we said was easy to integrate. Much easier to integrate than the original fraction. So that's what we're going to do today, is we're going to break up the hard fraction to integrate into smaller pieces that are easy to integrate into its parts, into the partial fractions. There's really three cases under partial fractions that we want to look at. Partial fractions. The first case is the case we've already seen when we have what we'll call non-repeated linear factors. For example, if we have the integral of x plus 1 over x plus 3 times x minus 2 dx. We're going to split this up so that we have some mysterious numerator over the first factor, x plus 3, plus the other mysterious numerator over the second factor, x minus 2. Now, we know when we multiply both sides by the least common denominator, we'll end up with the first one already has both factors, so they'll divide out. X plus 1 equals. The a fraction is missing the x minus 2 factor, plus the b fraction is missing the x plus 3 factor. Now we can pick convenient values for x to make each of those values go to 0. So we'll start with letting x equal 2. Plugging 2 in, 2 plus 1 is 3, equals, first group goes to 0. On the b, 2 plus 3 is 5. So if we divide both sides by 5, b is the fraction 3/5. Then we'll do the second factor. Let's let x equal negative 3. Plugging negative 3 in, we get negative 3 plus 1 is negative 2, equals. The a, negative 3 minus 2 is negative 5. And the second group goes to 0, so a is equal to a positive 2/5. So we can rewrite our integral now. Instead of x plus 1 over the product, we'll write our integral as a, which is 2/5, over the x plus 3, plus b, which we just found out was 3/5, over the x minus 2 dx. And that's a real quick antiderivative. Pull the constant of 2/5 out. We have the natural log of x plus 3. Plus, pull the 3/5 out front. We have the natural log of x minus 2, plus a constant. And we've got our antiderivative. So if there's non-repeated linear factors where we don't have anything squared, we don't have anything cubed in the denominator, it's just x plus 3, x plus 2, really simple. We just decompose the fractions to the pieces we need. But what if one of them is repeated? What if we have a repeated linear factor? For example, we might have lowercase ax plus b squared in one of the denominators. If that's the case, we'll use a denominator for ax plus b, and we'll use a denominator for ax plus b squared. And if it was cubed, we'd count up to cube. So we're going to need one denominator for each power of the factored result. So if we want to find the integral of x minus 2 over 2x minus 1 squared times x minus 1 dx, we'll think of this as something over the 2x minus 1 plus something else over. And because the 2x minus 1 has an exponent, we need to count up. We'll do 2x minus 1 again, but this time with the squared. And then we'll have a third one times the x minus 1. Now when we multiply by the least common denominator, when we multiply by what's missing, the original problem, the x minus 2 has nothing missing, equals a times, it only has one of the 2x minus 1, so it needs another one, so there would be two of them, times an x minus 1, plus b. B's already got two of the 2x minus 1s. It's only missing the x minus 1. Plus c times it's missing both of the 2x minus 1s, so 2x minus 1 squared. Now we can pick convenient values to try and get at the values of a, b, and c. Let's start by letting x equal, looking at the first factor, the 2x minus 1, which shows up twice. Solving that, we get 1/2. When x is 1/2, the first factor and the last factor, the group with a and the group with c, they all go to 0. So if x is 1/2, 1/2 minus 2 is negative 3/2, equals, first group goes to 0, b times 1/2 minus 1, which is negative 1/2. And so if we multiply both sides by negative 2, we end up with 3 equals b. Now let's pick another value for x. Notice two of the groups have an x minus 1, which means if x equals 1, both of those will go to 0. Plugging that in, 1 minus 2 is negative 1, equals, first factor goes to 0, the second factor goes to 0. The third factor, though, 2 times 1 minus 1 is 1, squared is 1. So we end up with c. c equals negative 1. Didn't have to do any work for that one. Now that accounts for all of our factors. Those are the easy ones that we've tried. We still are missing our letter a. We don't know what a is. So to get a, we're going to pick another value for x. It's not going to be as nice, but it's not very bad either. I always pick easy, convenient things like 0, 1, and 2. 0 is a beautiful number because it's really easy to do math with. Let's start with 0. If we plug 0 in, 0 minus 2 is negative 2, equals a times, when we plug 0 into this first group, we'll end up with negative 1 times negative 1, which is positive 1, plus b times, plug 0 in, we end up with negative 1, plus c times, plug 0 in, we end up with positive 1. But we already know what the value is for b and c. We found b and c. So let's plug those in, and we have negative 2 equals a minus b, which is 3, plus c, which is a negative 1. If we add 4 to both sides, we end up with 2 equals a. So sometimes we're going to have to do a little bit of algebra to get at the piece we need. But once we've done that, now our integral is going to be much easier to take. We've got the integral of a, which is 2 over the 2x minus 1. And let's split this up to one integral per piece, dx, plus b, which is the integral of 3 over the 2x minus 1 squared dx, plus the integral of c. c we found out was negative 1 over the x minus 1. And now we're really just taking these three simple integrals. Using a little u substitution, let u equal to 2x minus 1. du is equal to 2 dx. So we've got, on this first one, the integral of 1 over u du. That's nice because that's just going to be the natural log of u, or the natural log of 2x minus 1. For the second part, if we let u equal 2x minus 1, du is equal to 2 dx. So I'm going to pull the 3 out, multiply by a 2 and a 1/2 inside. So we've got 3 halves on the outside times the integral of u to the negative 2 du. And when we integrate u to the negative 2, we get the u to the negative 1. But u is 2x minus 1. And we multiply by that negative 1 out front. So 3 halves times 2x minus 1 to the negative 1. And the last one, pulling the negative out front. And the derivative of the denominator is just 1. So we have the natural log of x minus 1 plus a constant. So that's kind of our second case of taking integrals of rational expressions. If we see an exponent, like squared, we need the factor repeated as well, with every exponent counting up. The third case that we'll look at is what's called an irreducible quadratic. Let's say we end up with an ax squared plus bx plus c. Those are lowercase. Some denominator like that. What we have to do in that case is we have to account for the fact that the numerator might have an x in it as well. So we'll have a numerator of ax plus b over that irreducible quadratic ax squared plus bx plus c. Notice I've got lowercase, and capital letters. Don't confuse those. Those are different values. Let's take a look at what that looks like as we find the integral of x squared plus 8 over x cubed plus 8 dx. Now, the denominator is not factored, so if we do factor the denominator, leaving the numerator as x squared plus 8 over, we have a sum of cubes. So that's x plus 2 times x squared minus 2x plus 4 dx. And so when we set up our partial fractions, we'll have a over the first factor of x plus 2 plus, notice the second factor is x squared minus 2x plus 4. Because there's an x squared in that denominator, we have to account that there might be an x in the numerator. And so we'll have bx plus c in that numerator. Now, when we multiply by missing factors, the first part still is x squared plus 8 equals. The a is missing the x squared minus 2x plus 4 factor. Then there's the bx plus c group that's missing the x plus 2 factor. And we can solve for this much the same way. The easy one to find is we know when x is negative 2, what happens there? Negative 2 squared is 4. 4 plus 8 is 12. Equals. Negative 2 squared is 4. Minus 2 times 2 is a positive 4. So 4 plus 4 plus 4 is 12. A in the second group goes to 0. And so we see pretty quick that a must equal 1. Don't want to lose that as we keep working, so I'll put stars next to it. Now, there's no number that we can put in the second factor to make it equal to 0. But what's nice is whenever we have a bx, or one of our unknowns times x, that one will go away if we make x equal to 0. Another nice number. Let's look at what happens when we make x equal to 0. On the left, we have 0 squared plus 8, which is 8, equals the first factor, if x is 0, leaves behind 4a, plus b times 0 is 0. We're just left with the c, times, leave a little space here, we're left with the c, times, when x is 0, we're left with 2. So we have 8 equals 4a plus 2c. But what's nice is we already know what a equals. A equals 1. So 8 is equal to 4 times 1, or 4 plus 2c. And if we subtract 4 and divide by 2, we'll find out that c equals 2. So if we're just careful in how we select our numbers, they'll start to fall out pretty quick. Now, when we go after our last one, there's no trick that makes everything else goes away. But if we pick an easy number, we can get at our remaining variable, get at the b. So let's pick the number 1, because that's also easy to do math with. On the left, 1 squared plus 8 is 9, equals, when x is equal to 1, we have a times 1 minus 2 plus 4 is 3, plus b times 1 is b plus c, times x plus 2. 1 plus 2 is 3. So 9 is equal to 3a plus 3b plus 3c after we distribute. But we know a is 1 and c is 2. So when we plug that in, 3 times 1 is 3, plus 3b, we're still looking for b, plus 3c. 3 times 2 is 6. If we subtract 3 and 6, we get 3b equals 0. And so b is equal to 0 in this case. Which means our original integral can be rewritten as the sum of two fractions. Or let's actually break it down into two integrals. A is 1 over the x plus 2 dx, plus the integral of bx, which is 0 times x, or just 0, times 2 over our x squared minus 2x plus 4 dx. Now all we have to do is just solve the resulting integrals. The first integral is easy. That's the natural log of x plus 2. The second integral is not as easy, though. And so what we're going to do is we're going to employ two tricks to force us to integrate this, because we've got a constant over a denominator. First trick we're going to do is we're going to complete the square on that denominator, where we want the first two terms to become a perfect square. Remember, to get that perfect square, we need to add half of the middle number squared. Half of 2 is 1. 1 squared is 1. So we're going to add 1. But to stay balanced, if we add 1, we have to also subtract 1. When we do that, we have the integral. Let's actually pull the 2 out front. It's not going to be useful to us. Of 1 over x squared minus 2x plus 1, which factors to x minus 1 squared, plus 3 dx. Now we can take this integral quite nicely, because we're going to recall that the integral of 1 over u squared plus a squared du is 1 over a times the tangent inverse of u over a plus a constant. But this time, u is going to be that whole x minus 1. And since that derivative is 1, that's easy to handle. We still have the natural log of x plus 2. Plus, we've got a 2 in front of the radical, or in front of the integral. Then our formula says we have to divide by a. A is the square root of the other number. So 3 is really the square root of 3 squared. So we'll divide by the square root of 3 times the tangent inverse of u. That's the x minus 1 over a, which is the square root of 3, plus a constant. And this becomes our antiderivative of our original problem. So if we have an irreducible quadratic, some piece that can't be factored nicely, we'll end up keeping that quadratic. Just need to make sure the numerator has that 2 terms in it, 1 term for the x and 1 term for the constant. So let's actually take a moment to summarize the complete process for partial fractions. What have we seen today? Well, the first thing we need to do, if we're taking some p of x over q of x, the first thing we need to do is make sure that the degree of the numerator is smaller than the denominator. So if the degree of p of x is greater than or equal to the degree of q of x, maybe the p of x has a cubic in it and q of x only has a square in it. First thing we want to do is use long division to break that out. Once we've done that, we can factor the q of x, factor that denominator, and we'll have one of 3 things happen in that denominator, maybe 2 or 3 of them together. If we have all linear factors, no exponents, then we'll rewrite p of x over q of x as equal to our first value over ax plus b, a1x plus b1x. And then we'll just kind of work our way across all the factors. Let's call it a2 over a2x plus b2. Plus, and we keep going, 1 fraction all the way down to the last factor, a n x plus b n. If we have a repeated factor, let's say we see some ax plus b to the n power. It's repeated. We need to then include in a1 over just the ax plus b, plus an a2 over the ax plus b, and square it, plus, and keep going all the way up until we get to our exponent, ax plus b to the n. So if there's a factor repeated, we use it multiple times in our setup. If we have a quadratic factor, something that can't factor any further, maybe that's ax squared plus bx plus c, we need to include an ax plus b over that linear factor, ax squared plus bx plus c. So we've got to account for those 3 cases. Once we have it set up, the third step is to solve for the numerators. That's where we pick the easy values for x. Most of the time, that'll come out really nicely with those easy values. Sometimes you'll end up with a simple system of equations you can solve. Sometimes not so simple of a systems of equations, but definitely something we should be able to manage. And then we can finish the process by integrating the resulting expression. Usually we'll end up with logs. Sometimes we'll end up with inverse tangents. Sometimes we'll end up with just fractions. But the resulting expression is always going to be easier to integrate. And so that's the process for partial fractions. The big challenge is breaking up into those linear repeated factors and quadratic factors. So take a look at the homework assignment so you can try some of these. Practice several of them. These are kind of fun. It's a game to find A, B, and C. And we'll talk about them more when we get to class. As we work with integrals, often we come up with an integral that we cannot solve using our various integral tricks. So we're going to talk about another strategy for integration we can use, and that's going to be the question of how do we use a table of integrals. And what I want to notice is that our textbook has in its appendix a table of integrals that will help us out. It starts off with some basic integrals. Most of these integrals we already know, followed by some trig integrals. Most of these we can solve using our trig tricks that we talked about in the past couple lessons. Some exponential integrals. It includes hyperbolic integrals, which we didn't really talk about in this course, but there they are. Inverse trig integrals. And then the next ones, starting with number 68 here, are the ones we'll probably use the most. And these are various places where we see a sum or a difference of squares. So if we have a sum of squares, some of these formulas will help us out. If we have a difference of squares where the variable u comes first, these formulas can help us out. If we've got a difference of squares where the constant a squared comes first, and then it includes some weird ones where we've got a linear term and a quadratic term together, and then just linear integrals that can help us out. So a whole bunch of integrals in there that can help us out. And just to kind of summarize our tables then, start out with the basic integrals, then the trig integrals, the exponential and the log integrals, inverse trig integrals, and also the hyperbolics, which I skipped because we're not spending time on that in this course. And then we see a bunch that are called a squared plus u squared. These are problems like if you see a 25 plus x squared, because 25 is really 5 squared. So that's the a squared. Or you could even see one sometimes that'll look something like x squared plus 7. With addition, the order doesn't matter. The 7 might not look like a perfect square, but technically it is. We can say 7 is the square root of 7 squared, and then we could use the square root of 7 in those formulas. After that, there's the difference formulas where we've got u squared minus a squared. Notice the u, the variable, appears first. Those are different than if we have the a squared minus u squareds, which come next. Then they have some that are called 2au minus u squared. Those would be examples like if I had 6x minus x squared. You see the 6x can be rewritten as 2 times 3 times x. And so the 3 would be the a in those formulas. But we could even see something like 5x minus x squared. In that case, we'd still have to do 2 times the a, so a would be 5 halves times x, and we'd use 5 halves for the a. And then it wraps up with a plus bu. To practice using these tables, the best thing to do is just try problems. Problems can look like a lot of different ways. And then if we manipulate them a little bit, massage them to be in the format we want, we'll find that we can actually use those formulas in some unexpected places. So let's do a couple examples. Let's call this B. Examples. So for our first example, we're going to do the integral of 4x squared times the square root of 5 plus 4x squared dx. Now, one thing I notice about this problem is we've got something, the 5, plus an x squared. That kind of feels like one of the a squared plus u squared problems. So we need to identify what a and u are going to be. Now, a is going to be pretty straightforward, that a is going to be the square root of 5, so that a squared is 5. But for the u, we're going to do a little bit of work with it, because we just want to have one variable squared, and we have 4x squared. So we're going to let u equal the square root of 4x, which is 2x. Which means if we're going to make this substitution, du has to be equal to 2 dx. So we're going to need to multiply by a 2 and a 1/2 so that we have that 2 dx we want. Also noticing we've got the 4x squared there. That's going to become our u squared. So now the formula becomes 1/2 times the integral of u squared times the square root of 5 plus u squared du. And now we're ready to go after one of those formulas that has a squared plus u squared. The formula we look at is going to need to have a u squared and then the square root of our a squared plus u squared. Let's see if we can find it. So I'm going to start with the a squared plus u squared because that's what's under the square root. And one thing I notice is number 69 there actually is very similar, exactly identical, to the one we're looking for. So 69 is going to be our formula. So I've copied formula 69 on here. What we see is we've got a u squared. U we've identified as 2x. And we've got an a squared. A we've identified as the square root of 5. And so all we need to do is go into this formula that says it's going to be equal to u over 8. Well, u is 2x over 8 times a squared, the square root of 5 squared, plus 2u, which is 2x squared. Let's put square brackets on that. Times the square root of a squared. A is the square root of 5 squared, plus u, which is 2x squared, minus a, which is the square root of 5 to the 4th power, divided by 8, times the natural log of u, which is 2x, plus the square root of a, which is the square root of 5 squared, plus u, which is 2x squared, plus a constant. And so this formula has helped us build the antiderivative of our expression. We're going to do a little cleanup, though. Let's say 2 over 8 is 4, so we have x over 4, times the square root of 5 squared is 5, plus 2 squared is 4. 4 times 2 is 8, x squared, times the square root of root 5 squared is just 5, plus 2 squared is 4, x squared, minus the square root of 5 to the 4th power is 25 over 8, natural log of 2x plus the square root of 5 plus 4x squared plus a constant. And we've got our antiderivative using that table formula. Now, as I said, these come in many shapes and sizes. The trick is to massage them to get them in the format that matches the table. So let's try another one, and then I'll leave you after that to practice some of these, because that's the best way to get really good at these. We're going to do the integral of x minus 3 over the square root of x squared plus 6x plus 25 dx. Now we've got all of our tools at our disposal to find this integral. And one thing we might be tempted to do is try u substitution, because if we can get this to simplify to 1 over the square root of u, or u to the negative 1/2, this will simplify really nicely. And notice what happens if we make u equal to x squared plus 6x plus 25. Du becomes 2x plus 6. Well, we've almost got that. If I multiply by 2 inside, 1/2 outside, that'll give us 2x minus 6. Well, we want to have 2x plus 6. So let's massage a little bit more. To massage a little bit more, to get that minus 6 to become a plus 6, we could add 12 to it. But to stay balanced, we're going to add 12 and subtract 12. That way, the first part becomes the 2x plus 6 that we want. The second part, the minus 12, will take care of that separately. Let's divide that square root by both parts. When we do, we end up with 1/2 times the integral, the left part in red simplified to the 2x plus 6 that we wanted, over the square root of x squared plus 6x plus 25 dx. The right side minus, we still have the 1/2 in front of the integral. We have 12 over that denominator of the square root of x squared plus 6x plus 25 dx. So we split it into two integrals on that minus sign. The nice part about that is the left integral we can actually solve using our old methods. Using that exact u substitution that we just talked about, we have 1/2 times the integral of u to the negative 1/2 du, which we know the integral of that is going to be u to the positive 1/2 times 2 with a 1/2 out in front of it. Well, the 2's divide out. We just have u to the 1/2, which is the square root of u, which we know is x squared plus 6x plus 25. So that first integral becomes really nice when we break it up. The second integral does not become as nice, though. We don't really have a formula in our integral table for x squared plus 6x plus 25. But we do have formulas if we can simplify what's under the square root, simplify it to u squared plus a squared. So what we're going to do is we're going to take the left parts that have the variable, and we're going to complete the square on those parts. To complete the square, we take the 6 divided by 2 and square it. We're going to add 9 to get that to be a perfect square. But to stay balanced, we also have to subtract 9. So looking at what that gives us, if we pull the constant of 12 out front, that becomes 12 over 2, or minus 6, times the integral of 1 over the square root of the left stuff now is a perfect square, x plus 3 squared, plus 25 minus 9 is 16, and now we've got that u squared plus a squared feeling, where u is going to be equal to the x plus 3. Du is just the dx, which is nice. We don't have to do any substitution. And the a is the square root of 16 or 4. Again, we're using a squared plus u squared. Let's look at our integral tables. What you see is number 72. Number 72 is exactly what we want. We've got a perfect square plus our variable squared. So let's grab that one. All right, I put 72's formula on the screen here. It's going to be equal to the natural log of our u, which is x plus 3, plus the square root of a squared. A is 4, so 4 squared is 16, plus our u squared, x plus 3 squared. Don't lose that negative 6 out front. And doing a little cleanup, we have negative 6 natural log of x plus 3 plus the square root of, and if you multiply out that x plus 3, you get x squared plus 6x. Plus 9 and 16 is 25. And when we put it all together, the left half was just the square root of x squared plus 6x plus 25. The right integral became negative 6 natural log of x plus 3 plus the square root of x squared plus 6x plus 25. Always plus a constant at the end. And we have our antiderivative. And so that's how we can massage these problems. You have to be a little creative with the algebra to get them into the format we want. Then we can use the table to help us integrate. Take a look at these on the assignment, practice several of these, and we will talk about them more in class. We will see you then. One thing we haven't talked about with integrals is what happens at infinity. The question we're going to answer today is, how do we integrate at infinity? And before we actually get to integrating with infinity, I want to do a little bit of review of limits and infinity. First property we need to remember is that the limit as x goes to a from the left of 1 over x minus a. If we think about the graph of 1 over x minus a, it's something like this happening, where that vertical asymptote happens right at a. If we're coming in from the left side, that limit is going to be equal to a negative infinity. Now, if we want to take the limit as x approaches a from the right side of 1 over x minus a, when we come in from the right side, we're going up to positive infinity. Also, we talked about the limit as x goes to infinity of 1 over x, or really any exponent, so I'll say 1 over x to the n. If x goes to infinity, we end up with a very large denominator and a tiny numerator, which means taking a small number divided by a large number, we're approaching the number 0. And the other thing that I want to remember is that if we're interested in the limit as x goes to either positive or negative infinity of some function over another function, if we can't take the limit really directly of the overall fraction, what we can do is take the limit as x goes to the same direction, either positive or negative infinity, of the derivative of the numerator divided by the derivative of the denominator. And remember, we called that L'Hopital's rule. So these 4 properties around infinity are going to be useful to us as we work through problems that involve integrations at infinity. So first, what I want to do is I want to define how we do limits at infinity. And then we'll kind of talk through the logic of what that means and how we can apply it in some examples. So the first limit at infinity we might do is if we're integrating from some number a up to infinity of f of x dx. What we'll find we'll often do is find the integral as we go from a to t, some arbitrary value of f of x dx. And then we'll think, or write if it's easier, what happens as the limit of t as t goes to infinity. And if we're aware of what the limit is doing, we end up with what the integral is doing. Similarly, if I have the integral from negative infinity up to a b of f of x dx, we'll take the integral as we go from t to b of f of x dx. And then we'll think about what's happening as t goes to negative infinity. We can follow much the same logic if we have a discontinuity at one of our limits. Let's let f of x be discontinuous at b. If that's the case, and we want the integral as we go from a to b of f of x dx, what we can do is we can find the integral as we go from a to t, because remember we're discontinuous at b, of f of x dx. And then we'll take the limit as t goes to the value of b, but we're only going to be interested in as we come in from the left side. Because it's discontinuous at b, there's nothing actually at that point we can use. So we'll just consider coming in from the left side. And in fact, we can do a really similar thing if f of x is discontinuous at a. So then if we want the integral as we go from a to b of f of x dx, since we're discontinuous at a, we'll just go from t to b of f of x dx. And then we'll take the limit as t goes to b from the right side. And that'll give us a value. If there's only one point of discontinuity, we can actually integrate over a discontinuity. Let's let f of x be discontinuous at c. And now when I say c, I mean c is between a and b. So c is in between the a and the b. In that case, if we want the integral from a to b of f of x dx, if there's a discontinuity in the middle, what we'll do is we'll break it up into two integrals on that discontinuity. We'll find the integral as we go from a to c of f of x dx, and use number 3 to take the limit as t goes to c from the left side. And we'll add the integral as we go from c to b of f of x dx. And use step 4 in order to evaluate that integral. Really, the idea here between all of these formulas is if there's a discontinuity or if there's an infinity, we'll just take a look at the limit as we approach the value we want. And if we approach a value, that is the value of the integral. If we approach infinity or negative infinity, then what we'll do is we will say, let's just write this down. If we approach infinity or negative infinity, then we say the integral diverges, or has an infinite or negative infinity for its solution. Let's try an example where we can kind of see this work out. using this idea of if we can't actually hit the value, we'll see what's happening as we approach the values. I'm going to start with the integral from negative infinity up to 0 of 1 over x squared plus 4 dx. Now hopefully you recognize the sum of squares in the denominator, and you know this is a tangent inverse formula. It's going to be 1 over our a, the square root of 4, or 2 is our a, times the tangent inverse of x over a, which is x over 2 in our case. And we're integrating from 0 to negative infinity to 0. So first, when we plug 0 in, that's straightforward. We have 1/2 tangent inverse of 0 over 2, which is 0, minus 1/2 tangent inverse of, well, negative infinity divided by 2 is really negative infinity. Since we can't actually plug negative infinity into the tangent, we'll take the limit as tangent inverse goes to negative infinity. And if you remember, tangent inverse as a graph looks something like this, where it levels off at positive pi over 2 and negative pi over 2. So as the tangent inverse goes towards negative infinity, what we're going towards is negative pi over 2. So that right side is going to become negative 1/2 times, as we go towards negative infinity, we're going towards negative pi over 2. On the right side of this formula, the tangent inverse of 0. Tangent inverse of 0 is just 0, so we end up with a 0 minus 1/2 times negative pi over 2, and negative times a negative is a positive. And so we end up with pi over 4 is the area underneath our curve. So again, when we have these discontinuities, we're just saying what's happening as we approach that discontinuity. Let's do the integral from negative infinity to positive infinity of x e to the x dx. Now again, we're going to have to use negative infinity and positive infinity. We'll look at what's happening as we approach those values. But first we have to integrate, and we're going to integrate with u and dv, our integration by parts. We'll make u equal to x, dv equal e to the x. Therefore, du is just dx, and v, don't forget the dx on the du, or the dv. V is just e to the x, and so we have u times v, x e to the x, minus the integral of v du e to the x dx. So integrating e to the x is easy. It's just e to the x. And we're going to go from negative infinity up to positive infinity. Well, the problem is when we plug the infinities in for x e to the x and negative e to the x, it's hard to see what is that approaching. So to help us out, what we can do, we're looking at the limit as x goes to infinity of x e to the x. Well, L'Hopital says if we can write that as a fraction, we can take the derivative of the top and bottom and then find that limit. Let's leave the x on top and move e to the negative x down to the bottom. Because when we take the derivative of both the top and the bottom, the derivative of x is 1, and the derivative of e to the negative x is equal to negative e to the negative x. x goes to infinity of negative e to the negative x. And if x is going to a positive, sorry, e to the positive x, x is going to a positive infinity, we basically are doing e to some huge exponent. If we're doing e to some huge exponent, that's going to equal basically infinity. So this first term, when we plug the infinity in, we end up with infinity minus e to the x, which is infinity, minus, now we plug in the negative infinity. Negative infinity is a little nicer because if we change our problem up here that we just did, we're now taking x to the negative infinity all the way through. And so what we end up with is e to the negative infinity power. And e to the negative infinity is actually equal to 0. Thinking about the graph of e to the x. Well, on the right, positive infinity, it goes to positive infinity. On the left, we're going down to 0. So minus 0, minus, again, 0. And while it may seem intuitive to claim infinity minus infinity is 0, that's not always the case. Infinity actually can have several different sizes, and you can study infinity in more advanced math classes. But for now, we're going to say you can't just add and subtract infinities together. As soon as we have infinity in our solution, we could have stopped right there and said, hey, this integral is not going to approach any specific value. This integral is divergent, or it diverges. Meaning it does not approach any number. We have infinite area underneath the curve. Let's try another example. Let's do the integral from 0 to 4 of 1 over the square root of 4 minus x dx. The problem with this one is we have a discontinuity at 4, at one of those limits. In the denominator, 4 minus 4 is 0. The square root of 0 is 0. And we can't have 0 in the denominator of the fraction. So what we're going to do is when we get to the point to plug 4 in to our antiderivative, we're going to think, what's happening as we come into 4 from the left? First, though, let's actually take the integral. So to take this integral, I notice if we make u equal to 4 minus x, du is negative x, or negative 1. Let's just call it negative dx. So put a negative inside and outside, because then what we end up with is negative. The integral from, plugging the limits in, 4 minus 4 is 0 on top. Plugging 0 in, 4 minus 0 is 4. And we can actually switch that order of integration if I also change the sign. So I'm going to make it positive and go from 0 to 4. Of 1 over the square root of u, or u to the negative 1/2, du. So we have u to the 1/2 times 2, integrated from 0 to 4. And what's nice in this case is the discontinuity has been removed. So we can actually just plug in our values. 2 times u, which is the square root of 4, minus 2 times u, which is the square root of 0, which gives us 2 times 2, or 4, for our final area. Let's do one last example. Let's do the integral from 0 to 1 of the natural log of x dx. And again, what we see here is natural log is undefined at 0. If you remember the graph of natural log, it's got an asymptote at 0. hits 0, 1 comma 0, and then goes off to infinity really slowly, but it does get to infinity. So we're going to do the limit as we get approaching to 0 from the right side this time. But first we have to take our integral. If you remember, we've done the natural log of x. We use integration by parts, where u is the natural log of x and dv is just the dx. That way du is 1 over x and v is x. And so we end up with u times v, x natural log of x, minus the integral of v du, which is just 1 dx. And then integrating that 1 dx, we end up with x natural log of x minus x. And we're going to integrate from 0 to 1. This time we still have that discontinuity. We can't plug 0 in to that x ln x. So if I think off to the side here, we're interested in the limit as x goes to 0 of x natural log of x. Well, if we can make that into a fraction, we can use L'Hopital's rule. If we make x to the negative 1 in the denominator and the natural log of x in the numerator, L'Hopital will let us take the derivative of the numerator and denominator. The derivative of natural log of x is 1 over x, or x to the negative 1. The derivative of x to the negative 1 is negative x to the negative 2. Doing a little simplifying as x goes to 0. It's negative. Bring the x squared up to the top. The x to the negative 1 to the bottom. We have x squared over x, which is just x. And now we can plug 0 in to get negative 0, or just 0. So as x approaches 0, x ln x is also going to approach 0. So when we get to our step where we plug in our values, first plugging 1 in on top, 1 times the natural log of 1 minus 1, minus plugging 0 in. We can't exactly plug 0 into the first term, but we found out from L'Hopital's rule that that's going to simplify to 0 as we approach 0 from the right. Plus x, which is just 0. And what's really nice is the natural log of 1 is 0. And so we're just left with negative 1 for our solution. So to answer our question, how do we integrate at infinity? What we do is we consider what is the value approaching as we approach infinity. If we're approaching a value, then we use that value. If we're not approaching a value, we say the integral diverges. Take a look at the homework assignment and try a few of these, and we will take a closer look at these in class. And good luck to you. Up until this point, we've been integrating with just one variable, either dx or dy, with just the one variable we're interested in. Today we're going to extend that and answer the question, how do we integrate with respect to two variables? And this is going to be really similar to when we did partial derivatives, just in the x direction or just in the y direction. Just as we did with partial derivatives when we treated the other variable like a constant, we're going to do the same thing with two variables. We're going to treat the other variable as a constant. So, for example, you'll see something like the integral from maybe a to b of the integral from c to d of some function that has two variables in it, f of x, y. dx dy. When we see this, there's actually going to be an implied parentheses around the center integral. What that's really telling us to do is we're going to take that center integral and do this part first, with the other variable treated as a constant. So here, since it says dx, we're integrating with respect to x. And we'll do that first, treating all the y's like they're a constant. Then when we're done, we'll put the integral from a to b dy around that. And we will do that part second. And actually, there's no reason we have to do the dx first. We actually could see something like the integral from c to d of the integral from a to b of our f of x, y. And we can do the dy first, and then the dx. And just as before, there's an implied parentheses around the inside saying we're going to do that part first, and then we will do the outside integral second. But in this case, in example number 2, we integrate with respect to y first, and then we integrate with respect to x second. So the order is determined by whether we see the dx first or the dy first. And just as before, when we were taking an integral, when we took the integral from a to b of f of x dx, what that meant is there was some graph that went from a to b, and we were finding the area underneath that curve. Well, now we're taking the integral from a to b of the integral from c to d of some function f of xy dx dy. Because we have two variables, we're going to add another dimension. And so there's going to be this two-dimensional shape, which I will try to draw, this two-dimensional shape that is hanging out over three-dimensional space. And that two-dimensional shape is going to drop down and give us this three-dimensional volume that we're finding the area on, as our x-axis goes from a to b, and the y-axis goes from c to d. And that's that three-dimensional volume we're finding underneath a curve. We'll spend a lot more time in Calc 4 really digging into the meat of what's behind this concept. But here in Calc 2, we're just going to be interested in, can we take the double integrals? Can we do the inside integral first and the outside integral second? So let's try a few examples and see if we can do just that. Let's take the integral from 1 to 2 of the integral from 0 to 2 of xy minus 3xy squared dx dy. And what we know is that there is an implied parenthesis saying we're going to do that center integral first, dx. Because we're integrating with respect to x, we will treat the other variable, the y, as if it was a constant. So when we see xy, we know we raise the exponent by 1 and multiply by the reciprocal. So we get 1/2 x squared times the constant of y. Minus, again, x becomes x squared times 1/2. So we end up with 3/2 times the constant of y squared. And then we're going to integrate this from 0 to 2. And what I usually do with a double integral is I'll also put equals x. That way I remember I'm plugging 2 and 0 in for the x. Leave the y alone, as a constant. So plugging the 2 in, we end up with 1/2 times 2 squared times y minus 3/2 times 2 squared times y squared. And then we'd subtract and plug 0 in. But what's nice is when we plug 0 in, we get 0. So we're subtracting 0 and then adding 0. Simplifying then, 2 squared is 4, divided by 2 is 2y, minus 2 squared is 4, divided by 2 is 2, times 3 is 6y squared. Now we're ready to do the outside integral. We're taking the integral from 1 to 2 dy to finish this off. And this way, it almost becomes 2 integration problems in one. We now have y squared, divide by 2, divides out that 2, subtract, y cubed, 6 divided by 3 is 2. And we're integrating from 1 to 2. And this time, that 1 to 2 is equal to our y, because we're integrating dy. So we plug 2 in, we get 2 squared minus 2 times 2 cubed. And then we'll subtract and plug the 1 in. 1 squared plus 2 times 1 cubed, which is 4 minus 16 minus 1 plus 2 equals negative 11. So this is actually below the x and y axes. Negative 11 is going to be the total volume underneath this curve, xy minus 3xy squared. As I said before, we can integrate with respect to x first and then y, like we did in this example. Or we can switch the order of integration and actually do the dy first and then the dx. What I can do is if I switch the order of the integration, I just have to switch the order of the integrals, and I should still get the same exact thing. So I'm going to switch that for number 2 here and see if we get the same exact thing. We're going to do the integral first from 0 to 2, then the integral from 1 to 2 of our function, xy minus 3xy squared. And then we're going to switch the integration order, dy dx. So the same problem, but we've switched the order of integration. Again, we're going to start by doing the inside integral, but this time it's dy. This time we'll treat the x's like a constant. So we have our constant of x. The integral of y is y squared times 1/2. Minus, the integral of y squared is y cubed, divided by 3, gets rid of the 3. So we have xy cubed. And this time we're going to integrate from 1 to 2, but that's going to be equal to our y, because we were integrating first with respect to the y. So plugging 2 in for the y, we get 1/2 x times 2 squared minus x times 2 cubed. Then subtract, we'll plug the 1 in, 1/2 x times 1 squared, and then finally plus x times 1 cubed. Simplifying that, 2 squared is 4, divided by 2 is 2x, minus 2 cubed is 8x, minus 1/2 x plus 1x. And this is really nice for us because those are all like terms. We have 2 minus 8 is negative 6. Negative 6 plus 1 is negative 5, or negative 10 halves. Minus 1/2 is negative 11 halves x. And now that we've simplified dy, we're ready to take our last integral, dx, the integral from 0 to 2 dx, which gives us x squared times negative 11 over 4. And this time we're integrating from 0 to 2 equal to our x. Plugging 2 in, we get negative 11/4 times 2 squared. Minus, plugging 0 in, we get 0. 2 squared is 4, divided by 4, times negative 11. We get the exact same solution, integrating in the opposite order. Let's take a look at another example that sets up a nice property that can help us as we are simplifying our integrals. Let's take the integral from 0 to 1 of the integral from 0 to pi over 2 of e to the y cosine x dx dy. Off to the side here, I'm going to write an important property that's going to help us is if we have the double integral of a function with respect to x times a function with respect to y dx dy. Because the y's are a constant when we're integrating with respect to x, we can pull those out of that integral. Same with the dy. In other words, we end up with the integral of g of y dy times the integral of f of x dx. And we can do those integrals individually and then multiply the product, because we know we can pull a constant out in front of the integral. And that's exactly what we have here. You see we've got an e to the y and a cosine x multiplied together. So let's separate those. dx is first, so the x part stays in the first integral of 0 to pi over 2 of cosine of x dx. And then we multiply, pulling the other one through, the integral from 0 to 1 of e to the y dy. And now we can integrate those individually. The integral of e to the y is e to the y, integrated from 0 to 1 equals y. And the integral of cosine is sine, integrated from 0 to pi over 2 equals x. So we end up with e to the first power minus e to the 0 power, which is 1, times the sine of pi over 2, which is 1, minus the sine of 0, which is 0, which ends up simplifying to 1 minus 0 is 1, and 1 times anything just gives us the e minus 1 for our total volume under this curve. So it's a really nice, powerful trick that we can pull the product apart and just focus on the x's and the y's if they're separated. I want to be careful not to confuse this, though, with problems like this. Let's do the integral from 0 to 1 of the integral from 0 to 2 of 2x minus 2y dy dx. Here, yes, the x's and the y's are separate from each other. The problem is that they're not multiplied by each other. We do not have a product of a constant and our variable. So we cannot pull this one apart. We have to solve this one integral at a time. So first, we're integrating dy. 2x is just a constant. If we were integrating 2, the antiderivative of 2 is 2y. Similarly, the antiderivative of 2x, a constant, is 2xy. Minus y squared times a half gets rid of the 2. Integrated from 0 to 2 is equal to ry. Plugging 2 in for the y, we have 2x times 2 minus 2 squared, or 4x minus 4. We don't have to plug the 0 in because that gives us 0 when we plug the 0 in this time. Now that we're done with the inside integral, we're ready to do the outside integral, and we'll integrate from 0 to 1 dx, which gives us x squared divided by 2, leaves behind 2, minus 4x. And this time we're going to integrate from 0 to 1 equals x. Plugging 1 in, we get 1 times 1, 2 times 1 squared, minus 4 times 1, which is 2 minus 4, which gives us negative 2. Again, we didn't have to subtract the 0 because that gives us just 0 behind. And we end up with our final solution. So that's all it takes to integrate with respect to two variables. We start with the inside one, treating the other variable as a constant. And then we work on the outside one, treating the other variable as a constant. Some of these can get a little messy with the arithmetic and algebra, so it's important that you get really good at practicing these. Take a look at the homework assignment, and then we'll take a look at these problems in more detail in class. We will see you then. One last thing that I want to do before we wrap up derivatives and begins to take a preview of what is coming in our second quarter of calculus is looking at what is called the antiderivative, or really how we answer the question, how do we find derivatives in reverse? And that derivative in reverse is what we call the antiderivative. And we say that the antiderivative of f of x, lowercase f of x, is the function f of x, but notice it's capital F of x, whose derivative is the lowercase f of x. In other words, if capital F of x, the derivative of that is lowercase f of x, then the capital F of x is the antiderivative of the f of x. Maybe it's better with an example. How about we consider f of x equals 3x squared. Now, based on our power rule, which we know, but we're going to do it in reverse, we can conclude that capital F of x, the antiderivative, must be equal to x cubed. Because notice the derivative of x cubed is 3x squared. So the antiderivative of 3x squared is x cubed. It's the process in reverse. However, there's something we need to note. What if capital F of x equaled not just x cubed, but x cubed minus 1? Or if capital F of x equaled maybe x cubed plus 7. If we took the derivative of both of these, the derivative of the x cubed is the 3x squared we want, and the derivative of the negative 1 is 0. Similarly, with the other equation, with the plus 7, the derivative of x cubed is 3x squared, and the derivative of the 7 goes to 0. So we actually ended up with 3 potential antiderivatives of 3x squared. We've got just x cubed minus 1, or x cubed plus 7. And actually, you can see that we could extend that concept to basically say we could add any constant number to the x cubed, and we would still have an antiderivative. Let's note that we can add any constant, and we'll call that constant c, to any antiderivative. That means we're going to have to note that in our final solution. So when we say the antiderivative, actually, let's write this down. Different color. So the antiderivative of 3x squared is x cubed plus any constant. So let's see if we can kind of use what we know about derivatives and apply those rules in reverse. Let's see if we can do a few examples. Let's say f of x equals 5x to the 4th. Capital F of x, the antiderivative, then, we know that with the power rule, the exponent moves out front and reduces by 1. So we can see the power of 5 moved out front, and then it shrunk 1 from 5 down to 4. So capital F of x, the antiderivative, must be x to the 5th plus any constant. Let's try another one. Let's say f of x is equal to 1 over x. Well, we recognize 1 over x as the derivative of one of our special functions. 1 over x is the derivative of the natural log of x. So the antiderivative must be the natural log of x plus any constant. What about trig? Let's do f of x equals sine of x. What is the antiderivative? We're really asking whose derivative is the sine of x? Well, we know the sine of x is the derivative of cosine of x, but there's that extra negative. The derivative of cosine is negative sine, so we might assume the derivative of negative cosine then must be the positive sign. And of course, it's going to be plus any constant. What about f of x equals e to the x? Well, this is our favorite function because the derivative is itself, and so likewise the antiderivative will be itself plus any constant. So we've been kind of playing with this idea of an antiderivative, of just kind of thinking the derivative of what should equal this. What do we know about derivatives? What patterns can we notice to kind of come up with the solution? But let's formalize what we're doing here with the formal notation for these antiderivatives. The formal notation is we'll use this little squiggly sign. That squiggly sign we call the integral. The integral of f of x, and then we'll put a dx, so we know the variable we're taking the integral of with respect to x. The integral of f of x dx is going to be equal to that capital F of x plus a constant. That integral sign tells us find the antiderivative. And just like we have a bunch of derivative rules, like the derivative off to the side here, like if we want the derivative of x squared, that's equal to 2x. we've got those derivative rules. We also have integral rules as well. And we have one for powers, the power rule. The power rule says the integral of x to any exponent, dx, is equal to, well, let's see if we can piece this together. The derivative makes the exponent shrink by 1, so we need the exponent to go up by 1. Of course, the derivative says the exponent is multiplied out front, so we're going to divide by that new exponent. And with integrals, there's always a plus c. This is the power rule, a useful formula to be able to use quite quickly. And just like we use the power rule with derivatives a lot, we're going to use the power rule with integrals a lot. There's actually a whole lot of integral rules. Just to give you a taste here, this table is copied out of your textbook. So I'll put a number 2 here maybe. See textbook for more integral rules. And this table is in 4.10, and you can see this table, and it kind of takes the differentiation formula, which we're familiar with, and does it backwards with an integration formula. The second one is the power rule that we just solved. So there's lots of formulas in there, but we're going to focus mainly on the power rule. Let's see if we can find the integral of 7x cubed minus 5x squared plus 2x minus 7 dx. We'll take this one term at a time. With the 7x cubed, we keep the 7, the constant out front. The x cubed goes up to 4. And then we divide by that new exponent. Then we have minus 5 x squared. Now it goes up, because we're doing the antiderivative, goes up to 3. And we divide by that exponent. Plus 2 x, we increase the exponent by 1, so now it's squared. And we divide by the exponent. Minus 7. Increase the exponent by 1. Right now it was x to the 0. That's why it's not there. Increase it by 1. We have x to the first. And we divide by 1. We don't really need to say the divide by 1, but the 2 over 2 does reduce. And so our final integral is 7x to the 4th over 4 minus 5x to the 3rd over 3 plus x squared minus 7x. And don't forget, we always need, with integrals and antiderivatives, a plus c. We can use the power rule to even integrate some more interesting looking things. Like, for instance, the integral of x cubed minus 2 times the 4th root of x over x squared dx. Now, to help us out here, we're going to massage the function a little bit to make it something we can use in our power rule. One thing we can do, because of the minus in there, is we can distribute the divide by x squared onto both parts. So we actually have the integral of x cubed over x squared minus 2. And let's change that 4th root to an exponent, x to the 1/4 over x squared dx. Well, we can continue to simplify by subtracting exponents. X cubed over x squared is just x minus 2x to the 1/4 minus 2. Well, 2 is 8/4, so 1/4 minus 8/4 is negative 7/4 power dx. Moving up to give us a little more room, let's take the derivative now, or the integral. For the x, we raise the exponent by 1 to get x squared, and divide by 2, minus 2x, and then we raise the exponent by 1, or 4/4, to get negative 3/4, and divide by the new exponent of negative 3/4. Of course, there's going to be a plus c at the end. Never forget the plus c. Cleaning up a little bit, we've got a negative negative. That makes it positive. Dividing by a fraction means multiplying by the reciprocal. So let's multiply by 4/3 instead. So we have x squared over 2 plus 2 times 4 is 8. Negative exponent moves it down, x to the 3/4 plus a constant. And so we have x squared over 2 plus 8 over 3x to the 3/4 plus our constant. Let's try one more. Let's see if we can do a trig one. The integral of cosine of 3x dx. Now I know the antiderivative of cosine, or what's going to give me cosine when I take the derivative. That's going to be the sine. So I might think maybe sine 3x plus c is my integral. And you'd be very close if you said that. But remember, the chain rule says if we take the derivative of sine of x, the derivative of sine of 3x would be cosine of 3x times the derivative of the inside, which would be times 3. So we have to undo that times 3. And the best way to undo times 3 is to divide by 3. So the integral, or antiderivative, of cosine 3x is the sine of 3x divided by 3, plus a constant. Take a look at some of these in the assignment as you practice a few of these. These antiderivatives or integrals are really about pattern recognition, trying something out and seeing, that's close. How can I adjust to get closer until you get something that is correct? In Calc 2, we'll talk about a lot of strategies to make some of this easier. But for now, we want to kind of get some exposure and some experience with integrals and antiderivatives. So take a few of these, and we will see you in class to discuss them further. As we go into our second quarter of calculus, we need to make sure we're very comfortable with derivatives. So it's been a while since we've seen some of these derivatives, so we're going to do a quick review covering the question, how do we take a derivative? And we're not going to go in detail with this review. This is mainly to just make sure you remember all the pieces that are going to come into play as we get into antiderivatives here in Chapter 5. So to begin with, I want to review the basic formulas that we saw in our first semester of calculus. First, when we're taking the derivative of the most common function, something times x to an exponent. What we would do there is we would keep that constant out front, and then we would bring the exponent out front, and then we would reduce the exponent by 1. Next, we talked about some of the trig formulas. We could take the derivative of the sine of x, which we learned was the cosine of x. We could take the derivative of the cosine of x, which we know is the negative sine of x. we can take the derivative of the tangent of x, which becomes secant squared of x. We could also do the reciprocal formulas. Let me just put those to the right. The reciprocal of sine is cosecant. So the derivative of cosecant of x, we learned that was negative cosecant x cotangent of x. We can also do the derivative of the secant of x, which we learned was the positive secant x tangent x. And finally, we did the derivative of the cotangent of x, which we know is negative cosecant squared of x. A couple more formulas. We did exponentials. We took the derivative of e to the x. That's everyone's favorite because that's just e to the x. But if the base is something different, let's say we're doing the derivative of any base to the x, the derivative of that is still the same thing, a to the x, but now we need to multiply by the natural log of the base. We also can take the derivative of a natural log of x. With the natural log, we said it was the reciprocal function, 1 over x. And finally, we can take the derivative of the log base anything of x. That's simply the 1 over x, and then we need to multiply in the denominator by the natural log of the x. I'm sorry, the natural log of the a, the base. My number is not consistent. It went down and then over and then diagonal, but these 11 formulas should be very familiar to us as we take our derivatives. Now, with these formulas, we combine those 11 formulas with 3 main processes to take the derivative. The first process was the chain rule. And the chain rule said that if I want to take the derivative of some function with a function inside it, we would take the derivative of the outside function, leaving the inside the same, times the derivative of the inside function. That was the chain rule. Another rule we saw was the product rule. And the product rule said if we want to take the derivative of some product of f of x times g of x, we couldn't just take the derivative of the two pieces. We took the derivative of the first times the second plus the derivative of the second times the first. And very similar to the product rule was the quotient rule, which said if we want to take the derivative of a quotient, f of x divided by g of x, we would do a similar pattern. We'd take the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. And what we found we could do is we could combine quotient rule, product rule, chain rule, each of these 11 formulas that we saw up in Part A, and find all sorts of different types of derivatives. So let's try a couple examples of finding derivatives. Number one, we're going to look at just a basic example. Let's say y equals the natural log of x squared e to the x. Looking at the pieces here, we're going to have a chain rule going on because we've got the natural log of stuff, but then inside that stuff, there's a product rule going on. We've got the x squared times the e to the x. So we're going to use both the chain rule and the product rule here. So y prime, our derivative, the derivative of natural log is 1 over the stuff, 1 over the x squared e to the x. And then we multiply by the derivative of the inside. Now, the inside's a product, and when we multiply, it ends up in the numerator. Doing the product rule, x squared times e to the x, we take the product of the first, the derivative of the first, 2x, times the second, e to the x, plus the derivative of the second, the derivative of e to the x is e to the x, times the first, which is x squared. And this becomes our derivative. Now, a little variation on this derivative, we talked a bit about implicit differentiation as well, where we didn't just have y equals, but we had a function of x and y, a relationship. Let's say we've got x tangent of y equals the sine of y. Actually, no, let's just do y. Y minus 1. On the left side, you see we've got a product going on again. We've got x times the tangent of y. So when we take the derivative of x, we get 1 times the tangent of y, plus the derivative of tangent is secant squared of y. And then remember, whenever we take a derivative with y, we need to multiply by dy dx. And then don't forget the x times the first. So the derivative of the first times the second plus the derivative of the second times the first equals the derivative of y is dy dx, and the derivative of minus 1 is just 0. Let's get all the dy dx's on the same side by moving over to the right. So we have the tangent of y equals dy dx minus x secant squared of y dy dx. We're solving for, we want to know the derivative dy dx, so we'll factor that out. Tangent of y equals dy dx times 1 minus x secant squared of y. And to get our final answer, we'll divide both sides to get tangent of y over 1 minus x secant squared of y is equal to our derivative dy dx. Now, there was one other type of differentiation that we talked about, and that was logarithmic differentiation. Logarithmic differentiation was where we first took the natural log of both sides to get something that was easier to take a derivative of. We could use logarithmic differentiation if the variable was in the exponent, or if there's a lot of multiplying and dividing going on and we want to make the problem a little easier to work with. So for example, if we have y equals 3x plus 2 squared times x minus 4 to the 5th power over the square root of x plus 1 times x minus 5 to the 3rd power. Now, we could take this derivative using the product rule and the quotient rule and the chain rule all combined together. It's going to become huge and ugly. So to make life easier, we're going to take the natural log of both sides. On the left side, we just have the natural log of y. But on the right side, everything in the numerator is going to become a positive log. Everything in the denominator becomes a negative log. And all the exponents are allowed to move out front. Remember, the square root's a 1/2 power. So this gives me 2, moving the 2 out front, times the natural log of 3x plus 2, plus, moving the 5 out front, 5 natural log of x minus 4. Moving to the denominator, they're negative logs now. Negative, the radical's a 1/2 power, move that out front, natural log of x plus 1, minus, because we're still in the denominator, move the 3 out front, natural log of x minus 5. This derivative is going to be much easier to do using implicit differentiation. The derivative of natural log is 1 over the stuff, dy dx, because there was a y in there, equals 2 times the derivative of the natural log is 1 over the stuff, 3x plus 2, times the derivative of the inside, times the 3, plus 5 over the derivative of natural log is 1 over the stuff, x minus 4, minus 1/2, that 2's in the denominator, and the derivative of natural log is 1 over the stuff, x plus 1, minus 3, the derivative of natural log is 1 over the stuff, x minus 5. And now all we have to do is solve for the dy dx part. And we can do that really quickly by just multiplying both sides by y. And so we get dy dx is equal to, in parentheses, 2 times 3 is 6, over 3x plus 2, plus 5 over x minus 4, minus 1 over 2 times x plus 1, minus 3 over x minus 5, times y. But remember, back at the beginning, y is equal to the original problem. So let's just plug that in. We have 3x plus 2 squared times x minus 4 to the 5th over the square root of x plus 1 times x minus 5 to the 3rd. It's ugly, but it's our derivative, and we're ready to move on. So hopefully this short 15-minute video allowed you to review and remember all the log properties. Take a look at the homework assignment to practice all sorts of different types of problems, and in class we can discuss if you have any questions. Calculus 2 is obsessed with the question, what is the area underneath this curve? And so as we start out, we're going to talk about a general strategy about approximating areas as we attempt to answer the question, how do we estimate the area under a curve? And before we can actually answer that question directly, first we're going to spend a little bit of time talking about what is called sigma notation. And sigma notation, you're going to see something that looks like this funky letter E. It's actually the Greek letter sigma, a capital sigma. And then you'll usually see something like I goes from 1 to n of some expression, maybe a sub I. And what this tells us, the sigma says that we are going to add a bunch of things together. What we're going to add together is this function. The way we're going to do it, though, is the variable I is going to keep changing. I is going to start at whatever the bottom number is, and end at whatever the top number is. So, for example, if I wanted to find the sum as I goes from 3 to 5 of 2i, what that means is the variable I is going to be replaced with everything counting from 3 all the way up to 5. In this case, 3, 4, and 5. So we start at the bottom. The bottom number is 3, so it's 2 times 3. And the sigma says we're going to add 2 times the next number, which is 4. And then we'll add 2 times the next number, which is 5. And then if I put that all in my calculator, 2 times 3 plus 2 times 4 plus 2 times 5, we end up with our sum, which is 24. And so that's the idea of this sum, is we're going to take our expression and add together every number between the bottom and the top value. Now, there's several properties that can help us do these sums a lot quicker. Because if I asked you to find the sum from 1 to 100 of some expression, you don't want to write out all 100s. So if there's some shortcuts we can take, that would be wonderful. So our first property is the sum as I goes from 1 to any number of a constant, where c is just a number. That is always going to be equal to the top number, the stopping number, times the constant. Speaking of constants, if we want the sum as I goes from 1 to n of a constant times some expression, that constant actually can be multiplied by the sum going from 1 to n of the expression. Another nice property is that the sum as I goes from 1 to n of some expression plus or minus another expression, similar to limits, we can take that sum through to each part. So we can take the sum of the first term and either add or subtract the sum of the second term and evaluate the pieces individually. One last property I want to note is if we want the sum as I goes from any number besides 1 up to n of the expression, what we can do is we can think about that as the sum from 1 to n, adding up the 1, the 2, the 3, the 4, the 5, and then we can subtract off the sum of the pieces we don't want from 1 to d minus 1. 1 less than d, because we actually want to start at d. So we're going to cut off everything less than d of the expression. So these 4 properties help us break down sigmas or sums into their pieces. But once we have their pieces, we're going to need some rules to help us actually evaluate. So I've got 3 rules for us today. The first is that the sum as I goes from 1 to n of I. What that really means, if we plug I in, we start with the number 1, then we add 2, then we add 3, then we add 4, 5, 6, all the way up to our stopping number of n. You may remember from pre-calculus we proved with induction that this sum is equal to the top number times 1 more than the top number divided by 2. Similarly, we can add the sum as I goes from 1 to n of the squares. This means if we plug 1 in, we get 1 squared, which is 1, plus 2 squared, which is 4, plus 3 squared, which is 9, plus 4 squared, 5 squared, 6 squared, all the way up to our stopping number of n squared. We saw this one in pre-calc also. This ends up being n times n plus 1 times 2n plus 1 divided by 6. And one more just for fun. Let's do the sum as I goes from 1 to n of I cubed, We don't use this one as often, but we can. 1 cubed is 1, plus 2 cubed is 8, plus 3 cubed is 27, plus 4 cubed, 5 cubed, 6 cubed, all the way down to n cubed. And this one we don't use as often, but it is n squared times n plus 1 squared divided by 4. So these are some formulas that you might want to know. The sum of the i's is n times n plus 1. The sum of the I squareds is n times n plus 1 times 2n plus 1 over 6. We won't use I cubed as much, but it's there. I won't make you memorize that one, but the I and the I squared you should know. And also how to use them with the properties. The last few properties kind of come out of it naturally, but these first two properties you should really, really know. You should know them all, but those two properties I think are going to be what makes it all come out. So let's try a few examples. Let's actually calculate some sums. Let's start by finding the sum as I goes from 1 to 20 of 3i squared minus 4i. To break this down into manageable pieces, we'll use some of our properties that say the constants of 3 and 4 can end up in front of the sum that'll sit on the I squared and the I. So when I break this up, we'll pull the 3 out front times the sum as I goes from 1 to 20 of I squared minus 4 out front times the sum as I goes from 1 to 20 of I. Now we can go to those properties that we have. So we have a 3 times I squared. Remember, I squared is the sum of n times n plus 1 times 2n plus 1 divided by 6. So our n, the top number, is 20 times n plus 1 is 21 times 2n plus 1, 2 times 20 plus 1 is 41, all divided by 6. And that's the first term. Minus 4, and now we have the sum of the i's. But we have our rule that says the sum of the i's is n times n plus 1 divided by 2. So n, my top number, is 20. n plus 1 is 21. Divided by 2, and I can plug all of that in my calculator in one keystroke, just 3 times 20 times 21 times 41 divided by 6, minus 4 times 20 times 21 divided by 2, and when I put that in my calculator, I think we get 7,770. So that's what we would get if we added up all these pieces individually. Plug 1 in, plus plug 2 in, plus plug 3 in, plus all the way up to 20. It would add up to 7,770. Let's do one more example before we get away from these sums. Let's find the sum as I goes from 10 to 15 of 2i squared minus 7. Now, our properties that we have a starting number of 1. They always start with 1. But the problem we're looking at here does not start with 1. This one starts at 10. So what we're going to do is look at the sum to 15 and then subtract off the ones we don't want, 1 through 9, because we want to start at 10. So again, using our properties, the 2 comes out front. But we'll look at the sum as I goes from 1 to 15. That covers everything of the I squared. Minus the sum as I goes from 1 to 15 of just the 7. And then we'll subtract off the ones we don't want. We'll subtract 2 times the sum of I squared of the ones we don't want, as I goes from 1 to 9, because we want to start at 10. For the next term, be careful, we're subtracting a negative, which means we're going to add the sum as I goes from 1 to 9 of the 7. So what we did is we went all the way to 15 and subtract off everything through 9, so the count actually starts with 10. Now we can use our formulas. We've got 2 times. The I squared formula says n, or 15, times n plus 1, 16, times 2n plus 1, which is 31, divided by 6, minus, this time we don't have any n's or any i's, but remember that very first property says that if we have the sum of a constant, it's the stopping number times the constant. So my stopping number is 15 times the constant of 7, minus 2 times I squared. Again, the I squared formula is the top number 9. It's 9 plus 1, which is 10, times 2 times 9 plus 1, which is 19, divided by 6, plus, again, it's just a constant, so we take the top number of 9 times the 7, and we can plug that all into our calculator in one foul swoop, and I think we get 1,868. I typed it all in my calculator correctly. So that's a brief review of sums and sigma notation. You probably saw that in pre-calculus. But that's not the question we're attempting to answer. The question we want to answer is, how do we find the area under a curve? So let's take a look at that, first with some theory behind it, and then we'll look at some practical applications, finding the area under a curve. And to set this up, we're going to do a little bit of a graph. And let's just take a graph that curves down. And we're going to find the area from A to B. We want to find how much area is under that curve. But it's not a straight line, so what we're going to do is we're going to cheat. We're going to put little rectangles under this line, because rectangles are very easy to find the area of. The area of a rectangle is just base times height. So what we're going to do is we're going to move over some space. We'll call it delta x. Delta means a change in x, to get to our first point, x1. And if we go up and hit the curve, that has a height of f of x1. The area of that rectangle is base times height. The base is delta x, and we're going to multiply it by its height, which is f of x1. Then we'll move over delta again. Delta means change, to get our x2 point. That's going to give us a height of f of x2. And now we have a little rectangle whose area is base, delta x, times its height of f of x2. If we go over delta x again, that gets us all the way to b at x3. And its height is f of x3. So we've got our delta x as the base times the height of f of x3. And if we were to add these three rectangles together, that would approximately equal the area under that curve. Now we're short a bit, right? We've got these pieces that are missing, so it's a little bit short. But what we have done is we've made sure that the right corner of each of those rectangles hits the graph. So we're going to call this our right rectangle. And on the right, we'll always use a subscript to represent the number. I'll go ahead and put 3. the number of rectangles I broke it into. So right 3 means we had right corners hit the curve, and there were 3 rectangles on the right. To summarize that, you notice we're doing a sum. We're doing a repeated addition. We're going to take the sum as I goes from 1 to n of f of x sub I, whatever the height is of that rectangle we're talking about, times delta x, or times the width, the change in x. And we can kind of expand this to come up with our general formula that we can break into any number of rectangles. We split into 3 last time. I went from 1 to 3. We can split into any number of rectangles as I goes from 1 to n of f of xi times delta x. This formula is going to be very important to us. Probably the most important formula of the day. There's 2 of them. This is one of the 2. The second one's very similar. But the way we can find out the area of the right rectangles, the rectangles that hit the curve on the right, is we take f of x sub I and multiply by the width. Width times height. Width times height. Now, as you noticed, we did do a little bit of an underestimate because that curve had those spaces underneath it. And that happened because we hit on the right side of the rectangle. I want to look at what happens if we hit on the left side of the rectangle. What I'm going to do is I'm going to try and make this exact same graph as it curved down. We're still going to find the area from A to B. We're still going to have the same delta x, splitting it into 3 pieces, giving us x1, x2, and x3. And we still want that area under the curve. But this time, instead of having the rectangles hit the graph on the right side, we're going to have the rectangles hit the graph on the left side. So I'm going to come out from the minimum point this time and make my first rectangle. And then come out from my graph to make my next rectangle. And come out from the graph to make my next rectangle. And really similar, this time, though, our first point for our height starts over here all the way on the left. We'll call that x0. We'll call that height f of x0. So we're really doing f of x0 times the width of delta x. Then the second rectangle is f of x1 times the delta x. And the third rectangle is f of x2 times the delta x. And so what we end up with is rectangles that hit the graph on the left. 3 rectangles that hit the graph on the left. We still are going to do the sum from 1 to 3, but this time we didn't use heights 1, 2, 3. We used heights 0, 1, 2. So we're going to say we're going to take f of x sub I minus 1, which moves us over to the left 1 point, times the width of delta x. Or generalizing it for n rectangles, the sum as I goes from 1 to n of x sub I minus 1, and then times the same delta x. This is that second important formula I told you about. It's very, very similar. But for these 2 formulas, instead of memorizing the formula so much, it's more important that you learn the idea behind it. What we're really doing is we're finding areas of rectangles and just multiplying the base times the height. The base times the height. We just need to know if that height is coming off the left or right side. But there's one little thing I've kind of scammed over, and that is this delta x guy. I just kind of talked about delta x, how much we move over. We can kind of pick delta x arbitrarily and actually the smaller delta x is, the more accurate our estimate's going to be. Because as you saw in the second estimate, we still weren't totally accurate. I still have these extra spaces. So one I'm too low, one I'm too high. The truth is probably somewhere in the middle. But how do we find delta x? There's a very simple formula for delta x. So let's put that in here. To find delta x, what we do is we take the top value and subtract the bottom value, the left and right sides, and then we divide by the number of pieces that we want. So in the examples I did above, we'd be dividing by 3, because I wanted 3 rectangles. If I wanted 10 rectangles, we divide by 10. This formula is another one that's going to be very important, but by the time we're done, this one becomes almost second nature. All right, enough theory. Let's actually do some examples where we calculate some areas under the curve. What we're going to do is we're going to find L4, meaning we're going to split into 4 rectangles and hit the graph on the left for the function f of x equals x squared minus 3x. And we're going to do that on the interval from 3 to 5. First thing we need to know is how big is our delta x going to be? How wide is each rectangle going to be? This is where we use that delta x formula, where we take the high number minus the low number and divide by the number of rectangles that we want. So 5 minus 3 divided by the 4 rectangles. And let's go ahead and do this as a decimal. Delta x is 0.5. Going back to our theory up here, we want left rectangles. Notice the left rectangles started at f of x sub 0. We start at that minimum value. We start at the minimum. With left rectangles, we start at the minimum. So our minimum, that's the low value of 3. Let's start there. We need to find our height at 3. Then we'll move over delta x. We'll move over 0.5 to get the height at 3.5 for the next rectangle. Move over another 0.5. The next rectangle is going to hit at 4. Move over another 0.5. The next rectangle is going to hit at 4.5. And that'll give us our 4 rectangles. We're going to use the calculator to help us with these tedious calculations. On the calculator, what I'll do is I'll first hit y equals, clear out any junk that's in here. And then I will type in the function we're working with, x squared minus 3x. Then we'll go to the table function, which we used a lot last quarter, second table. Delete out these numbers I don't need. And we're interested in f of 3, f of 3.5, f of 4, and f of 4.5. And notice that gives us our numbers of 0, 1.75, 4, and 6.75. So 0, 1.75, 4, and 6.75. What we've done is we have found the heights of each of our rectangles. Remember, delta x, that's our width of each of our rectangles. So to find our area under the curve, estimating with left side rectangles, 4 of them, we take our height times the width. The first height is 0 times a width of 0.5, plus the second height is 1.75 times the width of 0.5, plus the next height is 4 times the width of 0.5, plus the next height is 6.75 times the width of 0.5. Then all we have to do is stick all this in our calculator. multiply, add, and we'll get a total area of 6.25. So we're going to estimate using 4 left rectangles that the area under this curve between 3 and 5 is about 6.25. Let's do one more example before we wrap up. Very similar, but I want to do 4 right rectangles and see how that compares. So for the same function, f of x equals x squared minus 3x, on the same interval from 3 to 5, we still want to know delta x, which still has the same formula. We take the high minus the low, divide by the number of rectangles. 5 minus 3 divided by 4. So our delta x is still 0.5. But a little different this time is we count off our heights because we're doing right-sided rectangles. With right-sided rectangles, notice the first rectangle started at x sub 1. It did not start at the minimum. It started over a delta from the minimum. So we need to make sure we do the same thing. We're going to start at delta x from the minimum. So going back down to our example, our minimum's 3, but we don't want to start at 3. We want to start delta x away from 3. So we'll start at 3.5. And then we'll count up. The next rectangle, 0.5 over is 4. 0.5 over is 4.5. 0.5 over is 5. And notice because we're doing right rectangles, it's going to end at the maximum. Again, we'll have our calculator do all the work for us. We've already got 3.54 and 4.5 in there. That's nice. We just need to figure out what 5 is. 5 hits at 10. So if we fill in, f of 3.5 was 1.75. F of 4 was 4. F of 4.5 was 6.75. And f of 5 is 10. And again, what we've done is we have found the heights of our 4 rectangles. And delta x is the width of the 4 rectangles. So the 4 right-sided rectangles, multiplying the height times the width, 1.75 times 0.5, plus 4 times 0.5, plus 6.75 times 0.5, plus 10 times 0.5. And when we add all that up on our calculator, we get about 11.25. So estimating with 4 rectangles on the right, we think we have an area actually of 11.25. The truth is somewhere in the middle between 6.25 and 11.25, and we'll talk about how to find the actual exact value in future lessons. But for now, what you need to know is how to partition up the rectangles, either for the left or the right side, and multiply the height times the length, to get a good estimate for our area. Take a look at the homework assignment. It reviews the sums, and it also reviews these problems of finding area under a curve, estimating with the rectangles, and in class we'll talk about it some more. Good luck! In our last video, we took a look at a way to approximate the area under a curve. Today we're going to attempt to answer the question, how do we find the exact area under a curve? No more estimating. We want an exact area. And the answer to this is going to be what we're going to call the definite integral. And the idea of the definite integral is we're trying to find the area under some function f of x from a point A to a point B. And the way the definite integral is defined comes from that area formula we were using in our previous section. In the previous section, we said that the area was equal to the sum as I goes from 1 to some number of rectangles n of each of the heights, f of xi, times the delta x. And what we discussed was that as we do more and more rectangles, the more and more exact this definition becomes for the area. So in theory, if we take the limit as n goes to infinity, and we have an infinite number of rectangles, there should be no more air, and that's going to give us the exact area. And we will represent this exact area with what's called the integral, which is kind of a stretched out s from A to B, from the lowest point to the highest point, of the function dx. So let's take a look at how we can use this definition to find an exact area or an exact definite integral. Let's take the integral from 0 to 2 of 3x squared dx. And we're going to keep in mind this formula that the limit as n goes to infinity of the sum as I goes from 1 to n of f of x sub I delta x is going to equal that integral. Let's break down the pieces of this. First, let's look at the delta x. That delta x, we know from our work on the previous lesson, is the high minus the low divided by the number of rectangles. Or in this case, 2 minus 0 divided by the number of rectangles, which we're going to eventually take to infinity. So delta x is 2 over n. That's the delta x piece, 2 over n. The x sub I piece, x sub I, the way we calculate that value of the x value, we start at the initial x point. Let's say we're doing left boxes. And we add some number of delta x's. And that's that I that counts up. So if I is 1/2, we move over 1/2, and then 2/2, and then 3/2, and then 4/2. What's nice here is that the left endpoint of x is starting at 0. So really, this is just I times delta x. But we know what delta x is. Delta x is 2 over n. So that's really I times 2 over n. Or we like to put the number in front, 2I over n. That is our x sub I value, 2I over n. Going out then, let's see if we can figure out what f of x sub I is. F of x sub I, remember x sub I is 2I over n. And the function we're talking about is 3x squared. So we have 3 times our 2I over n squared. Well, 2 squared is 4, times 3 is 12, I squared over n squared when we simplify. So the f of xi is equal to 12i squared over n. Let's then take this to the next step. Don't worry about the limit yet. We're just going to see if we can calculate the sum of all the pieces. The sum as I goes from 1 to n of f of x sub I, we just found out in purple, that's 12i squared over n squared, times our delta x. Well, our delta x, we said, was 2 over n. So now if I simplify this a bit, I get the sum as I goes from 1 to n of 24i squared over n cubed. And technically, 24 and the n cubed are constants, because only the I is changing. So I can pull those out. 24 over n cubed times the sum as I goes from 1 to n. And we have a formula for the sum of I squared. So if we have that 24 over n cubed, the I squared formula is the top number n times n plus 1 times 2n minus 1. I'm sorry, 2n plus 1, all over 6. We can do a little simplifying here. 24 over 6 is 4. N over n cubed is n squared. So now we've got 4 times, if I FOIL this out, I have 2n squared plus 3n plus 1 over, all that's left is n squared. And if I distribute the 4 through, we end up with 8n squared plus 12n plus 4 over n squared. But we've missed one piece of our formula, the limit as n goes to infinity. So let me see if I can buy myself a little bit of space. The limit as n goes to infinity of that 8n squared plus 12n plus 4 over the n squared. We know from our previous quarter of calculus that the largest exponents take over. It really becomes 8n squared over n squared, which reduces to just 8. Which means the integral that we started with from 0 to 2 of 3x squared dx, the area underneath 3x squared between 0 and 2 is equal to 8 square units. Now, that was quite an involved process. We try and avoid this process as much as possible. Sometimes geometry is easier. For example, if I wanted to find the integral from -2 to 6 of the square root of 16 minus x minus 2 squared dx, it would be quite ugly to go through that entire process. But if we were to graph this function, clear out the old function, we want the square root of 16 minus x minus 2, close the parentheses, squared. And I'm going to hit z squared, which is number 5, so it's to scale. What we end up with is this semicircle. This semicircle that's kind of centered at 0, 2, and it's got a radius of 4 each direction. Let's go ahead and draw that. So it was centered at 0, 2, radius was 4, so it has a height of 4, and it was this semicircle going through the points. We want the area from -2 to 6, which happens to be this entire semicircle under that curve. Well, rather than going through that process we just did up above, let's just know that the formula for the area of a circle is pi r squared. And since this is a semicircle, we'll divide that by 2. We said the radius here was 4 units. So we've got pi times 4 squared over 2, which is equal to 8 pi. 8 pi is our area. Or if you like a decimal, it's about 25.13. So sometimes knowing some of these geometry formulas are going to make life a lot easier for us, and we don't have to go through that whole process. For example, if I want the integral from 1 to 3 of 4 minus x dx, we know 4 minus x has a y-intercept of 4 and a slope of down 1 over 1. So we end up with this type of shape going on. But we want the area between 1 and 3. We want the area underneath that blue line in green there. Well, we know that's a trapezoid. The trapezoid's tipped sideways, but if you remember, the area for a trapezoid is 1/2 times the first base plus the second base. And remember, the bases are the parallel parts, not the bottom and top, the parallel parts, times the height. Well, if we count, the first base is 1, 2, 3 tall. The second base is 1 tall. And the height that connects them is 2 long. So for our area, it's 1/2 times the first base of 3 plus the second base of 1 times the height of 2. And when we calculate that out, we end up with an area of 4 units. So geometry does make finding some of these areas a lot easier. Another thing that we can use to help us is we can use, we'll call this part B, we can use the properties of definite integrals. And these properties really come from the summation formula, the definition. So let's look at the properties. You're going to see these properties are very similar to the sigma properties we saw in our previous lesson. Our first property is quite simple. If we take the integral from any point to itself of f of x dx, because there's no width here, we're just going from any point to itself, back to itself. No width, we end up with the width of 0 times any height. That's just going to be 0. That property is almost too boring to even talk about. A more interesting property, though, would be if I take the integral from a to b of f of x dx, and I find it easier to switch the order of integration and instead integrate from b to a of f of x dx. It turns out that that is the opposite. So if we switch the integration, we just end up with a negative out front. Also, the integral from a to b of f of x, either plus or minus some other function g of x dx. Just like we can take the sigma through addition and subtraction, we can take the integral through as well. And we have the integral from a to b of f of x dx, either plus or minus the integral from a to b of g of x dx. Our fourth property, if we have the integral from a to b of some constant times a function, just like we had before with summations, if there was a constant, we could pull the constant out of the summation. We can pull this constant out as well. And we have the integral from a to b of f of x dx, which might be easier to evaluate. One last property to talk about today. If we have the integral from a to b of f of x dx, we can actually split it into multiple parts. Let's say the number c is somewhere between a and b. We can take the integral from a to c of f of x dx and add to it the integral from c to b of f of x dx. Similar to how we did the sums, if we want to get rid of the bottom part, we could subtract off the bottom part, or whatever piece we're looking for. So these 5 properties will help us also evaluate several definite integrals. Let's take a look at practicing a few of these. with some examples. The first example, I'm going to tell you that the integral from 1 to 4 of some function f of x dx is equal to 3. And the integral from 1 to 4 of some function g of x dx is equal to -1. And we need to find the integral from 1 to 4 of 3 times f of x minus 2 times g of x dx. Well, we know from our properties we can take the integral through the addition and subtraction. And we also know that the constants of 3 and 2 can move out front. So what we really have is 3 times the integral from 1 to 4 of f of x minus 2 dx minus 2 times the integral of from 1 to 4 of g of x dx. And then we can substitute what we know. We know f of x dx is equal to 3. And we know that g of x dx is equal to -1. So plugging that in, we have 3 times the f of x integral, which is 3, minus 2 times the g of x integral, which we know is -1. Gives us 9 plus 2, which is 11. We can even do this, use these properties more specifically with maybe a function we know. Let's say the integral from 1 to 3 of e to the x dx. I found this for you. It's approximately, not exactly, but approximately 17.4. And I also calculated the integral from 1 to 2 of e to the x dx. It's approximately equal to 4.7. And we're going to find the integral from 2 to 3 of 4 e to the x dx. Well, one problem we have here is we're taking the integral from 2 to 3. We know 1 to 3 and we know 1 to 2. We want what's in between those, the 2 to 3. So what we can do is we can break this up and say we want the integral from 1 to 3, the whole thing, of 4 e to the x dx, and subtract off the integral that we don't want, the 1 to 2 stuff, of 4 e to the x dx. What we can also do, though, is we can pull those constants out front. So we really have 4 times the integral of 1 to 3 of e to the x dx, minus 4 times the integral from 1 to 2 of e to the x dx. And now we can plug what we know in. 1 to 3, that's 17.4. Minus 4, 1 to 2, that's 4.7. And now all we have to do is plug that into our calculator. And we'll get 50.8. The integral from 2 to 3 of 4 e to the x dx is 50.8. One last thing, then, that I want to talk about along with this line of finding exact values of integration. I want to talk about finding what's called the average value of a function. In other words, what's the average height this function has over a range? Let's say that we want the average value of f of x between the points a to b. Well, the reason we talk about this here is the formula falls right in line with finding areas. We'll say the average f value is equal to 1 over b minus a, or dividing by the width, times the integral from a to b of that function f of x dx. So if I wanted to find the average value or the average height of f of x equals 6 minus 2x on the interval from 0 to 3, what we're really saying is the average is equal to, using our formula, 1 over b minus a, 3 minus 0, of the integral from 0 to 3 of 6 minus 2x dx. So all I really need to do is figure out what is the integral from 0 to 3 of 6 minus 2x dx. Let's use geometry. Six minus 2x dx, we know that has a y-intercept of 6 and a slope of minus 2 over 1, minus 2 over 1, minus 2 over 1, and we end up with this nice little triangle. We want to go from 0 to 3 to get that area underneath. Well, the area of a triangle is 1/2 times the base times the height. So 1/2 times our base is 3, and the height of this rectangle or triangle is 6. So 1/2 of 3 times 6 is 9. So to calculate our average, we get 1 over 3 minus 0 is 3, times the integral, or the area, under 0 and through 3. We just found out that area is 9, and 1/3 of 9 is 3. That means the average height of this function is 3 units high. We could even, if we wanted to know when that occurs, when does the average occur? What we're really saying is we want to know f of c. What value of c allows it to equal that average height of 3? Well, f of c, that would be 6 minus 2c equals 3. And this becomes a real easy algebra problem for us to solve. We'll subtract the 6 to get -3 and divide by divide by -2, and we get a positive 3/2. And so what we'll find is at 3/2, this function hits the average height of 3. So the average value, not really difficult to calculate, but it does give us another context in which to practice finding these exact values of area under a curve. So take a look at the homework assignment today, practice a few of these, and in class we'll discuss it further and answer any questions that you might have. Today we're going to talk about one of the most important theorems of calculus. And to set it up, we are going to answer the question, how do we calculate the value of an integral? And to set this up, we're going to talk about what is called the fundamental theorem of calculus. And actually, the fundamental theorem of calculus comes in 2 parts. So first here, we're talking about part 1. We'll get to part 2 in just a minute. And to set up the fundamental theorem in calculus, I want to remind us about the mean value theorem that we talked about in our previous video. So this is technically a review of the mean value theorem. We said that the average value of a function is equal to 1 over b minus a times the integral from a to b of some function f of x dx. And what we also found out is if that average exists, there is also some point c such that f of c is equal to that average for a c that's in between those two values of top and bottom, minimum and maximums, the a and the b. We're going to use this to set up the fundamental theorem of calculus, at least part 1. To set this up, let's let f be a continuous function such that capital F of x is equal to the integral from some minimum value up to a variable x of f of t dt. So we've got this continuous f. And we're going to consider capital F prime of x. Now, the definition of a derivative is that we take the function at x plus h, and we subtract the function at x over h, and then take the limit as h goes to 0 of that result. Well, let's play with that a bit. We're still going to take the limit as h goes to 0. Let's pull that h out front, that 1 over h times. And for f of x plus h, that means we replace the variable in f. That's the x at the top of the integral. We're going to replace it with x plus h. So we have the integral from a to b of, the integral from a to x plus h of lowercase f of t dt minus the regular function f of x, which is just the integral from a to x of f of t dt. Now we're going to massage this a bit. I should have it in parentheses because that 1 over h goes through everything. We're going to massage this a little bit. First thing we're going to do is we're going to change the subtraction to addition. And we have a property that says we can switch the order of the integration to change the sign in front of it. So when we do that, we get the limit as h goes to 0 of 1 over h times the integral of a to x plus h of f of t dt plus now the integral in the opposite order, x to a, of f of t dt. But what's nice about this is you see if we start on the right with a bottom of x, we're going up to a. And the next one starts at a and goes up to x plus h. There's no gap between them. So we know we can write that as a single integral, which gives us the limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of d dt. And this is very interesting because we note from the mean value theorem, which we have up above here, if I took 1 over the x plus h minus x of the integral from x to x plus h of f of t dt, the mean value theorem says that that is going to equal f of c for some c that's an element of, or it's in between the bottom and top values, between the x and the x plus h. Notice that the x and the minus x there in purple subtract out to 0. So what we really have is 1 over h times the integral, just like is inside that limit. Which means that the limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of t dt is equal to the limit as h goes to 0 of the f of c. Making that substitution from the integral to the f of c. But what's interesting is h is going to 0, which means as h goes to 0, this interval is going to shrink and shrink, and c is going to get closer and closer to the x because that plus h is disappearing. There's less and less space. C gets squeezed down until c starts to approach x, which means this is really saying the limit as c approaches x of f of c. But we also know that this is a continuous function. What's nice about a continuous function is with a limit, we can just plug that value for x into c. And so what we end up with is simply f of x. Why is this important? Remember, we started with capital F prime. The derivative of the integral we found out is equal to f of x, the inside function. Let me summarize that with another point here. Number 3, and this is actually part 1 of the fundamental theorem of calculus. If capital F of x is equal to the integral from a to x of f of t dt, then the derivative is simply equal to the f of x function inside that integral. This is part 1 of the fundamental theorem of calculus, that the derivative is the opposite of the integral. The derivative gets rid of the integral. What does this look like? Well, let's do some examples of how we can do this. Let's find the derivative of the integral from 3 to x of cosine of 4t dt. What the first part of the fundamental theorem of calculus tells us is this top value, as long as the bottom value is a constant number, this top value, all it needs to do is get plugged in for the t, because the derivative of the integral is just the inside stuff. It's just the cosine of 4t. I'm sorry, it's just the cosine of 4x. Plug that x into the t. And that's all we have to do to take the derivative of the integral. Now we can make it a little more interesting and say take the derivative of the integral maybe from 1 to x squared of the square root of t dt. The derivative of the integral still says, as long as the bottom number is a constant, that we can plug that variable in for t. But remember, we have a chain rule. The chain rule says we have to take the derivative of the inside stuff. We still have to take the derivative of that x squared. Chain rule. When we plug that x squared in, then we have to take the derivative of the x squared. So we get the square root of t, which now becomes x squared, times the derivative of the x squared, which is 2x. Well, the square root of x squared is x, times 2x becomes 2x squared. Let's do one more where we have to use the chain rule as we take the derivative. Let's take the derivative of the integral from 5 to the cosine of x of 1 minus t squared dt. Again, we're taking the derivative of an integral. So we just plug that top value in for the variable. And so what we end up with is 1 minus cosine squared of x. But then we have to multiply, using the chain rule, by the derivative of the inside, the derivative of the cosine, which is just the sine of x. This one actually simplifies quite nicely because 1 minus cosine squared should look familiar to us. Actually, it's negative sine of x. I lied. The derivative of cosine is negative sine. Okay, going back to that 1 minus cosine squared then. 1 minus cosine squared should be familiar because that's equal to the sine squared of x. So sine squared times negative sine squared is, times negative sine is negative sine cubed of x for our final result. So that's part one of the fundamental theorem of calculus. It states that the derivative of the integral is the inside function. Derivative and integral undo each other. If that's part one, let's look at part two, the fundamental theorem of calculus. Part two. And this actually is probably the most important part. This is the most powerful theorem of all of calculus. So to set this up, let's let g of x equal the integral from a to x of f of t dt. And then by part one of the fundamental theorem of calculus, the derivative of g of x, g prime of x, is equal to the inside function f of x. Part one says just take that x and plug it in. Gives us the f of x. What we're going to do is we're going to make up another function. Let's let capital F of x be another antiderivative of f. And if you remember in Calc 1, when we talked about antiderivatives, we said that every function has an infinite number of antiderivatives. They all just differ by a constant. We always needed that plus c at the end when we evaluated them. So g of x and f of x, capital F of x, differ by a constant c. In other words, we could say that capital F of x is equal to our g of x plus a constant, because they're both antiderivatives of the f of x function. We're going to consider two cases. We're going to first consider letting x equal a in the g of x function. If x equals a in the g of x function, going back to the original function, plugging a in for the x, we get the integral from a to a of f of t dt. But the integral from a to a from anything to itself is always equal to 0. Actually, probably better if I wrote in two steps here. Then g of a is equal to the integral from a to a of f of t dt. And we know that's equal to 0. Because integrating from anything to itself is always equal to 0. There's no width. Let's consider another case. Let's let x equal b in g of x. Then g of b is equal to the integral from a to b of f of t dt, which we don't have any way to simplify. So g of b is just that stuff. And then here's where the magic happens. We're going to consider capital F of A. I'm sorry, capital F of B. We'll do the B first. Minus capital F of A. Remember we said that f is g of x plus c. So f of b is going to be g of b plus c. And then we subtract f of a, which is g of a plus c. However, this is where it becomes interesting. G of a we said is equal to 0. And we've got a positive c minus c is equal to 0. So all that's left is g of b. Or what we're really saying is capital F of b minus capital F of a is equal to g of b. Well, g of b is the integral from a to b of f of t dt. This result is the most powerful result in all of calculus. This is part 2 of the fundamental theorem of calculus, which says that the integral from a to b of f of t dt, the way we evaluate that is we find the antiderivative at the top value, b, and subtract the antiderivative of the bottom value, a, and then we can evaluate any integral. We can find any area between 2 points. Part 2 of the fundamental theorem of calculus. It's the most important theorem of all of calculus, because let's look at what we can do now that we know part 2 is true. First, a quick aside, I want to recall antiderivatives. Antiderivatives are the opposite of a derivative. So if you remember, for example, the derivative rule for an exponent, x to the n, what we would do is we'd pull that exponent out front and then reduce the exponent by 1. Similarly, we can take the integral of x to the n dx by doing the opposite operation for the antiderivative. Instead of decreasing the exponent by 1, we increase it by 1. And then instead of multiplying by the exponent, we divide by that new exponent. And of course, we had that plus c. But what's nice about the fundamental theorem of calculus, as we saw in that proof up above in number 1, the c's are going to subtract out. So we don't really need to worry about the c as long as there's numbers plugged into the integral. There's all sorts of other antiderivatives we can review. For example, the antiderivative of cosine is sine. It's basically all those derivative rules that we saw before work backwards. So if we want to take some examples and say find the integral from 1 to 2 of x squared plus 4x minus 5 dx. We can find the area under this curve between 1 and 2 using the second part of the fundamental theorem of calculus. First, with the x squared, we know we can raise that exponent by 1 and divide by the new exponent, x cubed over 3, plus 4. For the x, we raise the exponent by 1, x squared, divide by 2, minus 5, Right now there's an x to the 0, so we raise the exponent by 1 and we get x to the first. Now, if we were just doing antiderivatives like we did at the end of Calculus 1, we'd do a plus c and stop there. But what we're going to do now is we're going to actually evaluate it between 1 and 2. So we'll put this vertical bar. It's not squiggly anymore like the integral. Vertical bar from 1 to 2, meaning we're going to plug in these values. The f of v is that top number being plugged in for each of the x's. So plugging 2 in, we get 2 cubed divided by 3, plus 4 times x, which is 2, squared divided by 2, minus 5x, which is 2. Then we will do a subtraction. Be very careful with this subtraction. What that subtraction is really saying is we're going to change the signs all the way through. Plus becomes minus, and minus becomes plus. Most common error here is people don't switch the sign. So instead of a positive x cubed, it's now a negative, and we're going to plug the bottom number in. 1 cubed over 3. The plus now becomes a minus, 4 times 1 squared divided by 2. And the minus now becomes a plus, 5 times 1. And so what you can see, if I can color code this, the top number got plugged into the original function. The bottom number got plugged into the function with the signs changing. That's what the fundamental theorem of calculus says, is the top number minus the bottom number. From here, we can simplify this using our calculators, which is really nice. Just plugging in what we have here into our calculator, I've got 2 cubed divided by 3 plus 4 times, whoops. Make sure you have the exponent here. 2 cubed out of the exponent divided by 3 plus 4 times 2 squared divided by 2 minus 5 times 2 minus 1 cubed divided by 3 minus 4 times 1 squared divided by 2 plus 5 times 1, enter, and I get this ugly decimal 3.33333, which is not exactly accurate. I want you to change this into a fraction for me, and the calculator does it really nicely. If you hit the math button and hit enter, enter, it changes that to a nice fraction of 10/3. And so that tells us that the area here underneath our curve between 1 and 2 is exactly 10/3. It's kind of nice that we didn't have to use Riemann sums, and we didn't have to use geometry. We just calculated it using the antiderivatives and the fundamental theorem of calculus. Let's try another example. Let's do the integral from 1 to 4 of x squared plus x divided by the square root of x dx. Well, part of the problem with this one is the ugly form. But if we massage this a bit, it becomes very easy to just use that exponent property on. Remember, the 1/2 power is just, the square root is just x to the 1/2. And then we can divide it by each term, subtracting our exponents. So we have the integral from 1 to 4, and 2 minus 1/2 is 3/2, plus x to the 1 minus 1/2 is 1/2 dx. And now we can use our exponent property to find the antiderivative. With x to the 3/2, we raise the exponent by 1, or 2/2, gives us 5/2. And then we divide by the new exponent, but dividing by the fraction 5/2 is like multiplying by the reciprocal 2/5, plus x to the 1/2, raise the exponent by 1, and we get 3/2, multiplying by the reciprocal 2/3, and we're going to evaluate that from x going to 1 to 4 to find our area. First, plugging 4 in, we've got 2 times 4 to the 5/2 over 5, plus 2 times 4 to the 3/2 over 3. And then we subtract the bottom value. Subtract 2 times 1 to the 5/2 over 5, plus becomes minus 2 times 1 to the 3/2 over 3 to get our area between 1 and 4. On the calculator, 2 times 4 to the 5/2 power divided by 5 plus 2 times 4 to the 3/2 power divided by 3 minus 2 times 1 to the 5/2 is multiplying by 1, so that doesn't really do much. Divide by 5 minus 2 times 1 again divided by 3. And we get this nice ugly decimal, but if I hit math and enter, we'll change it into a fraction, 256/15. And that's the area between 1 and 4 underneath our curve. Part 2 of the fundamental theorem of calculus. Take a look at the homework assignment and try some of these problems, practice a few of these, and then we will discuss them more in class and answer any more questions that you may have. But with the fundamental theorem of calculus, practice is the best way to master how to use it. Good luck. Today we're going to take a look at an interesting application that comes out of the fundamental theorem of calculus. And that's going to be to answer the question, how do I find the net change over time? Calculus is the study of change. And with derivatives, we talked about the rate of change. But if this thing is changing at some rate that we can calculate, we should be able to figure out how much change happens over time. And there's actually a relationship between the rate of change and the net change. But before we get into that, first I want to do a quick review of some integration formulas that are very important. You should know these formulas by now. The first one is the integral of x to the n dx. The exponent rule we should be familiar with. We just need to raise that exponent by 1 and then divide by the new exponent. Also remember that we need the plus c whenever we have an indefinite integral. We don't have limits of integration in there. We're not integrating between 5 and 7. We're just doing in general, so we're going to have a constant that could be added to our antiderivative. One interesting result, though, coming out of this is the integral of 1 over x dx. We can't use the exponent formula on this because the exponent's -1. And if you increase that by 1, you get 0. And the formula asks us to divide by that new exponent of 0, which we cannot do. You cannot divide by 0. So we need another formula specifically for 1 over x. But what's nice is the integral is the inverse of the derivative. So we just have to ask ourselves, is there a derivative that equals 1 over x? And we should remember that the derivative of the natural log of x was 1 over x. So the integral of 1 over x is the natural log of x plus c. Speaking of natural logs, what about the exponential? What's the integral of e to the x dx? Well, you may remember from your derivative formulas, the derivative of e to the x is e to the x. So going backwards, the integral of e to the x is just e to the x plus the constant. A little variation on that, what would be the integral of e to the nx dx, where we've got some number multiplied by the x? Well, if you think off to the side for a minute, I'll just move up here. When we were doing the derivative of e to the nx, we got e to the nx, and the chain rule said we had to multiply by the derivative of the inside, which was just n. So doing the integral, working backwards, instead of multiplying by that n, we're going to divide by that n. We get e to the nx divided by n plus the constant. What about the integral of sine x dx? Well, again, we think about our differentiation rules. The derivative of what equals sine? Well, the derivative of cosine equals negative sine. So to account for that negative, we'll say the integral of sine is negative cosine of x plus a constant. And similarly, the integral of cosine of x dx, we know the derivative of sine is cosine, so the integral of cosine must be the sine of x plus a constant. Those formulas you should get really familiar and comfortable with taking those integrals quickly without any problem. Now, let's talk application of the fundamental theorem of calculus, and that comes with the net change. And the idea of net change is if I've got some relationship or some function f of x gives the relationship between f and x, then the derivative of x gives the rate of change between f and x. And we saw that in Calculus 1 when we did rate of change problems. We found a relationship. We took the derivative of the relationship to determine the rate of change. Well, the fundamental theorem of calculus says we can go backwards and take the integral of the derivative between a and b, and that will give the net change in f over some interval from a to b. How much does the function change between a and b? But the fundamental theorem of calculus says that the integral of the derivative is just the function evaluated between a and b, or more specifically, take the original function at b and subtract the original function at a. So if we want the net change over some interval, the fundamental theorem of calculus says all we have to do is just calculate the low value and the high value of the original function and subtract them. Let's take a look at an application of net change. Let's see. The area of a regular triangle is the area of a being the side length, equals the square root of 3 over 4 times a squared, where a is the side length. We're going to write an integral to represent the net change of the area as the side increases from 2 inches to 3 inches. Net change is the integral of the derivative. So we're taking the integral as it goes from 2 to 3 inches of the rate of change. So to do that, we're going to take the derivative of our area formula, dA, or the integral from 2 to 3 of, looking at our area formula, it's just a constant times a squared, so we bring the 2 out front. It would be 2 root 3 over 4, which reduces to root 3 over 2 times a dA. This integral represents the net change. However, it's really easy to evaluate because we know we just need to plug in those limits into the original function and subtract. So really, we're taking a of 3 minus a of 2, or root 3 over 4 times 3 squared minus root 3 over 4 times 2 squared, which is equal to 5 root 3 over 4 after we simplify. So the way we calculate net change is we take the integral of the derivative, but it's easier to simplify by just plugging in the extreme values into the original formula to calculate our net change. Let's try one more example, maybe one that's a little more general. The volume of a cylinder with height of 4 inches is V of r is equal to 4 pi r squared. As the radius changes, the height's going to stay fixed at 4. We want to know what is the net change as the radius increases from r, capital R, to 3, capital R. In other words, the radius is going to triple. What's the net change? Well, if we wanted to make an integral, we would take an integral from those radiuses, from r to 3r, of the derivative of the function. Bringing the 2 out front, it gives us 8 pi r dr. But we don't really need to calculate that because the fundamental theorem of calculus says I just have to plug these extremes into the derivative, or into the integral of the derivative, which is the original function. So doing that, we get 4 pi times the top number, 3r squared, minus 4 pi times the bottom number, r squared. 9 minus 1 is 8, times 4 is 32 pi r squared is how much the volume is going to increase by, a net change in the volume, when the radius triples. Net change. Another nice application that we can use the fundamental theorem of calculus for comes from physics. Physics with a P. And that is the relationship between acceleration, velocity, and displacement. Displacement is how much you move. Velocity is how fast you move. Acceleration is how that speed is changing. And those are all related by integration. If we know the acceleration with respect to time, then the velocity with respect to time is just going to be the integral of the acceleration, dt. And the displacement with respect to time is going to be equal to the integral of the velocity with respect to time. As we do these integrations, though, we end up with a plus c, or plus a constant. And what's really nice about velocity is the c will be the initial velocity. And with the displacement, the c will be the initial height or position. So, for example, we know that gravity is negative 9.8 meters per second squared. Gravity is really acceleration. Acceleration. How fast things are moving towards the Earth. They're speeding up at 9.8 meters per second squared. So if that's true, and a ball is thrown up vertically at 18 meters per second from a height of 3 meters, we should be able to calculate when does the ball hit the ground. When we're talking about the ball hitting the ground, we're talking about the location, the displacement, how much has it moved. And so we need to derive that displacement formula. But now we can. Starting with the acceleration of the ball. Actually, let me match the colors here. I'll do this in brown. The acceleration of the ball is going to be affected by gravity, negative 9.8 meters per second. The velocity, then, is simply going to be the integration of that acceleration. You should put that in brown. Try and color code this. The integral of the acceleration dt. Well, that's just a constant, so we end up with negative 9.8 t plus a constant. But that constant is going to be the initial velocity, or the initial speed at which the ball is moving. It's moving up positively at 18 meters per second. And now we have an equation for the velocity. For the displacement, or the position, we take the integral of the velocity equation, the negative 9.8 t plus 18 dt. Well, with the t, it becomes t squared, and then we divide by 2. Negative 9.8 divided by 2 is negative 4.9, plus 18t plus a constant. The constant, again, is that initial position. That initial height is 3. And now we have a formula that we can use to calculate when the ball hits the ground at a height of 0. Well, we'll use the good old quadratic formula to solve for t then. The opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a And if I were to plug that into my calculator, be careful with parentheses around the numerator and the denominator, and depending on the calculator you have, possibly in the square root as well. 1 time is negative, but we do end up with a positive 3.83 seconds. And so this ball is going to take 3.83 seconds to reach its maximum height and then come crashing down to the ground. So these have been some applications of the fundamental theorem of calculus, allowing us to integrate using the derivative and the relationship between the two, net change and these physics applications. So go ahead and take a look at the homework assignment, practice a few of these, and let me know if you have any questions. We will see you in class. As we continue to work with integration, we're going to answer the question today, how do we integrate the chain rule? Remember, the fundamental theorem of calculus tells us that integration and derivatives are inverses of each other. So if we take a derivative with the chain rule, how do we integrate and use that chain rule in reverse? The answer to that question is a process we call substitution. And here's the idea behind this substitution idea. If we let the integral of lowercase f of x dx equal capital F of x plus a constant, in other words, capital F is the antiderivative of lowercase f of x, then we know a couple things are true. If I wanted to take the derivative of capital F of x, that would be lowercase f of x by the fundamental theorem of calculus. But if we take it one step further and ask to take the derivative of capital F of another function, let's say of g of x, we could use the chain rule to take this derivative. The chain rule says we take the derivative of the outside. The derivative of capital F is lowercase f of g of x. But then the chain rule says we multiply by the derivative of the inside, so whatever g prime of x is. Well, then let's continue with this fundamental theorem of calculus. If I integrate that solution, if I integrate lowercase f of g of x times g prime of x dx, that has to equal, then, the stuff we had before. That has to equal the capital F of g of x plus some constant. But what's interesting here is, what if we take another approach? What if in this original integral we let u equal that g of x function? And if I scroll down to buy myself some space, if I let du equal the derivative of g of x times dx, the integral then changes. Notice what pieces I have here. The g of x becomes u. Du becomes g prime of x dx. So now I have the integral of f of u times all the rest of that stuff becomes du. Notice the du and the u, a substitution has been made. And we know what the integral of f of anything is. It's capital F. So what we end up with is capital F of the u plus a constant. But remember that u is equal to the g of x. So really we're saying capital F of g of x plus a constant, which is exactly the same thing that we got by breaking apart the pieces. This middle step, where I let u and du equal the pieces of the function, that is what we call the substitution step. If we can simplify a function by identifying the inside function, identifying that g of x function, the entire integral becomes much, much simpler. That's what we're going to try and do. So to summarize that process, define the inside, whatever that is, as u, such that the derivative of u is part of the function. Here's what I mean by that. Let's say if I had the integral of 5x to the 4th times x to the 5th plus 3 cubed dx. Notice if I look at this inside function, its derivative is 5x to the 4th, which is part of the function. Let me use blue. Which is part of the function with the dx. So what I'm going to do is I'm going to define u to be that inside stuff, x to the 5th plus 3. That is my u. Du, then, is its derivative, 5x to the 4th, and then we always multiply by a dx. Notice that is the remaining part of the function. So now what's left is the integral. All the blue stuff, 5x to the 4th dx, is going to become du. The yellow stuff just becomes u, and we still have that third power on it. And what we've done is we've simplified the complex integral to a much simpler integral of u to the 3rd. We know the integral of u to the 3rd is u to the 4th divided by 4 plus a constant. And what's nice here is we have this u that we know is equal to x to the 5th plus 3. So we substitute back x to the 5th plus 3 to the 4th power divided by 4 plus a constant becomes our antiderivative, or our integral. This process of substitution is what we're looking at today, seeing if we can identify this u that's part of the function such that its derivative du is also part of the function, to hopefully give us a simpler integral that's really easy to calculate. And then we just substitute back to x's at the end. Let's take a look at a few examples and see if we can get good at this process, and also see some of the intricacies that might come up out of this. So B, examples. First example we're going to do is we're going to find the integral of x divided by the square root of x squared plus 3 dx. We don't really have any antiderivative that looks familiar from. So we might try our u substitution, looking for u to be the inside stuff so that its derivative is kind of everything else around it. Notice inside the radical, we've got x squared plus 3. That x squared plus 3 then can become our u. Du then is the derivative of u. Du is 2x times the dx. Now this is interesting, because we want 2x times dx to be the du part. We only have 1x times the dx. We're going to make a little adjustment to our problem. We may need to multiply by a constant inside and its reciprocal outside the integral. This is our first little nuance. What I mean by that is we're missing the number 2. Since that is a constant, just the number 2, I can multiply by a 2 inside the integral as long as I multiply by its reciprocal outside the integral. Because you see, what's possible is the 2's would divide out and it still has the same value. We're not going to divide out the 2's, however, because now 2x is what's needed. 2x dx is what's needed to make that du. We're ready to make our substitution. We still have the 1/2 outside times the integral. The 2x dx is just going to become a du. And we have left over 1 over the square root of all the stuff that becomes u. Now, we like square roots to become 1/2 powers, and denominators really become negative exponents. What we're really saying is u to the negative 1/2 power. And this is an integral that's much easier to take. Keeping the 1/2 out front, times negative 1/2 increasing by 1 becomes a positive 1/2, multiplying by the reciprocal of 2. And then we add a constant. Now this is nice because the 2's are going to divide out. So what we really have is u to the 1/2 plus a constant. But then let's go back and change that u back into the x. So u is equal to x squared plus 3. All that to the 1/2 power plus a constant. We have our solution. Let's try one with some trigonometry in it. Let's take the integral of sine theta cosine to the 4th theta d theta. And this doesn't look like any antiderivative that we've seen before, so we might think substitution's a good solution to make this into something easier to work with. Do we make the u equal to the sine, the cosine, the 4th power, or some combination thereof? Remember, we want the u to be the inside function. The only thing I see inside is there's a cosine inside of a 4th power. So let's make u equal to the cosine of theta. And then du would be its derivative, which is negative sine theta d theta. But we have a problem again, because this is negative sine theta d theta. We have a positive sine theta d theta. So what we can do, though, is multiply by a negative 1 inside the radical and a negative 1 outside the radical, so that we have that negative inside that we need to complete that du. Now we have a negative integral. The negative sine theta d theta becomes a du. The cosine becomes a u, and now we just have a 4th power. And this integral now is very easy to evaluate. It's u to the 5th divided by 5. Don't forget the negative out front, plus c. And of course, we're going to substitute that u back into a cosine, 5th power. So negative 5th cosine of theta divided by 5 plus a constant. We have our integral. Let's do one more that has a very interesting nuance to it. Let's do the integral of x divided by the square root of x minus 1 dx. Hopefully we're getting good at identifying u as the inside function. What I see inside is an x minus 1. That means du, its derivative, is just 1 dx. So x minus 1 is u, and dx is our du. But we've got a problem in that there is an x left over. We don't like having an x left over. We need to go all the way to u's, or not at all. We can't just go halfway. So there's another nice little trick that we can use. Is if we have an x left over, we can solve the u equation for x to substitute. What I mean by that is this: if u equals x minus 1, adding 1 to both sides, x is equal to u plus 1. And so we can make another substitution to replace the x with u plus 1. And let's see what type of integral that gives us. So the x becomes u plus 1 over the square root, which is a 1/2 power. The x minus 1 becomes a u, and the dx becoming du. We can do a quick division. Divide both sides by u to the 1/2, and that gives us the integral of u to the positive 1/2 plus u to the negative 1/2 du. And we have an integral that we can solve. Raise the exponent by 1, we get u to the 3/2 times the reciprocal of 2/3. Plus, raise the reciprocal by 1, we get u to the 1/2 times the reciprocal of 2, plus a constant. And now all we have to do is replace those u's with what they equal. 2 times x minus 1 to the 3/2 divided by 3, plus 2 times x minus 1 to the 1/2, plus a constant, and we have our integral. So far, we've been working with these indefinite integrals that don't have limits of integration. If there's limits of integrations, this process actually becomes easier. So let's take a look at definite integrals. The nice part about definite integrals is when we do the substitution step, we can replace the limits with whatever u equals. I'll say the u equals solution. So for example, we have the integral from 0 to 1 of x squared plus 1 e to the x cubed plus 3x dx. And to do our u substitution, we look for an inside function. And you might see an inside function, x cubed plus 3x, is inside e to the x. So that's going to be our u, x cubed plus 3x. That's our u. Du, then, is its derivative, 3x squared plus 3 dx. But do we see 3x squared plus 3 in our integral? Well, kind of. If we were to factor a 3 out, it would be x squared plus 1 dx. And now you see we have x squared plus 1 dx. X squared plus 1 and a dx multiplied together. We just need to account for that 3 by multiplying 3 inside and 1/3 outside. So now we've got the 3 that we need for both parts. Now we have 1/3 times the integral from 0. Here's where it becomes nice. We're going to take that 0 and plug it in for our x. Plugging 0 in, we'd have 0 cubed plus 3 times 0 equals u, or u equals 0. So our lower limit is going to be 0. For the upper limit, we plug the upper limit of 1 into the u equals equation. 1 cubed plus 3 times 1 equals u, or u equals 4. So my upper limit is 4. All right, new limits. Going back to my function, the 3x squared plus 1 dx all became a du. We're just left with e to the u, which is the easiest integral to take. We have 1/3 e to the u. But we don't have to substitute back because now we have limits for u going from 0 to 4. Plugging 4 in, we get 1/3. Let's put the e to the u in the numerator. E to the 4th over 3 minus e to the 0, which is 1 over 3, or e to the 4th minus 1 over 3 is the area under this curve between 1 and 0. So with definite integrals, it's nice because we can do this extra step to plug the limits in for u to get our new limits, and we don't have to go back to x's. We now just can work with the u's. Let's do one more that I think is just a fun problem that we can now do. We're going to take the integral from 0 to pi over 2 of sine squared theta d theta. This one, you might be tempted maybe to make u equal to the inside function of sine theta. The problem is du, its derivative is cosine theta, and there is no cosine theta in this integral. We can't make one either. But we do have another nice trick. You remember your double angle formula from trig? The double angle formula says that sine squared is equal to 1 minus the cosine of 2 theta all over 2. So let's integrate that from 0 to pi over 2 d theta. I'm going to divide this 2 into both sides. And while I'm at it, I'm going to split into 2 integrals on that negative sign. So when I do that, I have the integral from 0 to pi over 2 of just 1/2 d theta minus the integral from 0 to pi over 2 of 1/2 cosine of 2 theta d theta. Now, on the left side, this is really nice. The left side is an easy derivative, or an easy antiderivative. It's 1/2 theta. And then we just have to integrate that from 0 to pi over 2. The right side, though, takes a little bit more work because we need to use u substitution to actually solve it. We're going to make u equal to the inside stuff, which you can see is 2 theta. And du is equal to its derivative, which is 2 d theta. So we've got 2 theta for our u. Our du is 2 d theta. We've already got the d theta, but I've got 1/2 instead of 2. So if I multiply by 4, 4/2 will equal 2, and we'll do a 1/4 on the outside. So now my integral becomes the integral from, let's plug 0 into theta. 2 times 0 is 0. Plug pi over 2 into the u equation. 2 times pi over 2 is pi. And then the 2 d theta became r du. And we're just left with the cosine of u du. Which means we are subtracting, bringing down that subtraction, we are subtracting the antiderivative of cosine is sine of u. And the u's we're going to integrate from 0 to pi. So plugging pi over 2 in, we get 1/2 of pi over 2. Minus 1/2 of 0 is 0. Minus, plugging pi in, sine of 0 is 0. And then we subtract a negative, which makes it a positive. Sine of 0 is 0. I'm sorry, sine of pi is 0. Sine of 0 is 0. It's all the same. Simplifying this out, we end up with a single pi over 4 is the area underneath sine squared between 0 and pi over 2. This one was kind of fun because we had to use a trig formula to make it work. What you really want to focus on is the substitution step that we did on that second integral there, or on all the other integrals up above. Doing that substitution step of identifying u, the inside function, du, the outside function, to give us an easier integral that we can solve. Take a look at that on the homework assignment. Try a few of those. Come to class with questions. We'll talk about it more and continue to work on these problems. As we continue to work with integration, and specifically with substitution, we're going to address the question, how do we integrate with exponents, or with exponentials, and logarithms? To set this up, we basically are working with a couple new formulas that often are seen within the context of substitution. First one, we already know that the integral of e to the x dx, that's going to be equal to e to the x plus c. We can extend that a little bit and take the integral of a to the x dx. Now, if you remember, the derivative of a to the x is a to the x times the natural log. So the antiderivative is going to be a to the x divided by the natural log of the base plus a constant. Another formula, oops, I didn't number that one. That's number 2. Another formula, formula number 3, is the integral of 1 over x dx. And we've talked about this one very briefly. We know that the derivative of natural log is 1 over x. So the integral of 1 over x must be the natural log of x plus a constant. I'm going to put 4 below it because 4 and 5 go together. 4 and 5 take a look, though, at how we can actually integrate the natural log of x dx. The integral of the natural log is going to be x times the natural log of x minus x plus a constant. Or you could factor out the x and say x natural log of x minus 1 plus a constant. And then another formula, generalizing our integral of the log base a of x dx. Very similar, we're just going to divide by the natural log of a. It's x over the natural log of a times the natural log of x minus 1 plus a constant. So 5 more formulas for us to play with in integration. Quite often these formulas come up within the context of substitution. So that's why we do this after substitution, even though the formulas are straightforward. Let's try a couple examples, as these are often seen with substitution. It becomes a good review for the process of substitution. So the first one we're going to do is we're going to take the integral of x squared e to the negative 2x cubed dx. And what I see is the inside function of negative 2x cubed is an ideal candidate for our u, the negative 2x cubed, because du, its derivative, is negative 6x squared. So while our u is negative 2x cubed, du is negative 6x squared dx. We've got the dx, we've got the x squared, so we need to bring in a negative 6 and multiply by negative 1/6 on the outside. So that negative 6 can become part of the integral. And so we end up with negative 1/6 times the integral of e to the u du. And that's a very easy integral to calculate. We have negative 1/6 e to the u plus c, or negative 1/6 e to the negative 2x cubed plus c. And you might want to simplify that if you want. You could say that's negative 1 over 6 e to the 2x cubed plus c, if you decide to simplify that. Let's try another example. Let's do a definite integral. Let's integrate from 1 to 2 e to the 4x to the negative 2 all over x cubed dx. Now, before we get too far into this, that over x cubed, we could write that as x to the negative 3 times e to the 4x to the negative 2 dx. And when we do that, we end up with a very similar look. We've got an inside function of negative 4x, or 4x to the negative 2. And so if that becomes our inside function, our du becomes negative 8x to the negative 3 dx. We're missing the negative 8, so we'll multiply by negative 8 and negative 1/8. And that way, we've got the 8x to the negative 3 dx. That's going to become our du. And now our integral is negative 1/8 times, let's put these limits on here. We can plug these limits into the u function. 1 to the negative 2 is 1, times 4 is 4. Plugging 2 in, 2 to the negative 2 is 1/4, times 4 is 1. And then we're left with e to the u du. Now, I do notice that the integration's kind of backwards here. We like the small number to be on the bottom. But when we switch them, we just have to change the sign of the front number. So we can say this is actually equal to a positive 1/8 times the integral from 1 to 4 of e to the u du. And now we can evaluate that as saying it's e to the u divided by 8, integrated from 1 to 4. So we have e to the 4th minus e to the 1st all over 8 for the area underneath this curve between 1 and 2. Let's try another example. Let's do the integral of 1 over x plus 2 dx. Sometimes you'll see this written with the dx in the numerator, the integral of dx over x plus 2. They both mean the same thing. And you might notice that we're inclined to say the inside function is that x plus 2. So u is equal to x plus 2. du, its derivative is 1 dx, or just dx. So x plus 2 and 1 dx. So what we end up with is the integral of 1 over u du, which is really nice because we know the integral of 1 over u is the natural log of u plus a constant. Should be in red. Natural log of u plus a constant. Going back, substituting that u, we get the natural log of x plus 2 plus a constant is our antiderivative. Let's try one that's kind of similar in nature, but maybe a little more complex. Let's do number 4. The integral of 2x to the third plus 3x all over x to the fourth plus 3x squared dx. Lots of pieces going on here. One thing we can hope is if the denominator is our inside function and the numerator is the outside function, we end up with 1 over u, which is the natural log. Let's see if that works. If u is equal to x to the fourth plus 3x squared, du then is 4x cubed plus 6x. That doesn't quite seem to match the numerator. But look, oh, I forgot the dx. But look what happens when we factor out 2 from that du. We have 2 times 2x cubed plus 3x dx. And it turns out that's quite similar to the numerator. We just need to multiply by a 2 on the inside and a 1/2 on the outside. And then we end up with 2 times 2x cubed plus 3x dx becomes the du. The denominator becomes the u. And we end up with a real nice integral, 1/2 times the integral of 1 over u du, which is just the natural log of u over 2 plus a constant. Substituting back, we get the natural log of x to the fourth plus 3x squared all over 2 plus a constant. And we have our final antiderivative. Let's do an example with a logarithm in the integral. We'll keep this one simple, number 5. Let's do the integral. Let's just do log base 3 of 4x dx. Our inside function looks to be 4x inside the logarithm. So if I let u equal 4x, du is equal to 4 dx. So we're going to need to multiply by a 4 on the inside and a 1/4 on the outside. So we have our u. Our 4 dx is our du. This becomes a real nice integral of 1/4 times the integral of the log base 3 of u du. Using our formula then for a log base 3, we would have 1/4 times x over the natural log of the base, which is 3, times the natural log of x minus 1 plus a constant. Oops, but we don't have x's, we have u's. So if I replace those u's with what they equal 4x, we get 4x over 4 natural log of 3 times the natural log of 4x minus 1 plus a constant. those 4's reduce out. So for my final answer, x over natural log of 3 times the natural log of 4x minus 1 plus our constant. Let's try one last example as we wrap up here today. Example number 6. Let's do a definite integral from 0 to pi over 2 of sine x over 1 plus cosine x dx. Well, again, we like to see if that denominator can become our u of 1 plus cosine x. If that's our u, the derivative du, the derivative of cosine is negative sine of x dx, which means we need to introduce a negative inside and outside the radical so that negative sine x dx becomes that du. And again, the integral becomes a nice, beautiful integral from, let's plug these limits into our u equation. Cosine of pi over 2 is 0. Plus 1 is 1 for that top limit. Cosine of 0 is 1. 1 plus 1 is 2 for the bottom limit. And then we're left with 1 over u du. But again, I like to have the limits of integration in order. So let's switch the order. As we do that, we'll switch the signs. So we have the integral from 1 to 2 of 1 over u du. And 1 over u becomes the natural log of u integrated from 1 to 2. So that's the natural log of 2 minus the natural log of 1. But you may remember that the natural log of 1, log base anything of 1, is always equal to 0. So really all we have left is the natural log of 2 for our answer. So today what we're really doing is working more with substitution, practicing that substitution process and that substitution step. We're just doing it in the context of these logarithm and exponential formulas that we're adding to our repertoire, but not too difficult to add them to the repertoire. Good to continue practicing, though, with this substitution. Take a look at a couple problems, practice them tonight, and we will see you in class to work on them further and answer any questions that you may have. As we continue to take a look at substitution, we're going to take a look specifically with inverse trigonometric functions, answering the question, how do we take integrals resulting in the inverse trig functions? And we'll start off with some formulas that we're going to work with. And what you'll find is these formulas really are the inverse trig derivatives written in reverse, because the fundamental theorem of calculus tells us that the derivative of the integral is the function itself. So if I wanted to integrate du over the square root of, let's call it a squared minus u squared, you should recognize that from the sine inverse function of u over a plus c. If I wanted to take the integral du over a squared plus u squared, that should look familiar as the tangent inverse function. But we have to do a little bit of manipulation to it first. For the tangent inverse, we're going to do 1 over a tangent inverse of u over a plus c. And the third formula we're going to recognize is the integral du over the absolute value of u times the square root of u squared minus a squared. And that one, similar to tangent, we'll have to do a divide by a to get rid of that a issue. And then we'll have the secant inverse of the u over a plus a constant. We are still missing 3 of the inverse trig formulas, but if you remember with the derivatives of the inverse cosine, inverse cotangent, and the inverse cosecant, they're the exact same formulas with just a negative sign. Which means we don't really need another formula with integration, because that negative sign can come outside of the integral, and then it becomes one of these 3 formulas. So that reduces the amount of things we have to keep track of, which is quite nice. Let's take a look at how we can use these 3 formulas then to do some examples. Starting with taking the integral dx over 36 plus 4x squared. Now, noticing in the denominator we've got 2 perfect squares added together. That looks a lot like that second formula, the tangent formula. So let's see. We just need to identify what a and u are, and that u kind of hints at what we want to make our substitution. Because we'd like to see just u squared, but we have 4x squared. So we're going to do a u substitution where we want the u squared to be 4x squared. Well, if u squared is 4x squared, taking the square root, u is just 2x, and its derivative is just 2 dx. So to make the substitution work, we'll multiply by 2 inside and 1/2 outside. And now we've got the u of 2x, or 4x squared being u squared, and the 2 dx becomes our du, and our new integral is now 1/2 times du over 36 plus u squared. In fact, we can even rewrite that 36 as 6 squared so that it's in that tangent format. So to begin with, as we take this integral, we've got the 1/2 out front times, using our tangent formula, tangent says we're going to take 1 over the a term. So 1 over 6 tangent inverse of u divided by the a term of 6 plus a constant. Now going back and putting that u in, we'll end up with our final answer, multiplying the fractions to get 1/12 tangent inverse of u, which is 2x, divided by 6 plus c. Well, actually, not quite final answer, because we can reduce that 2 over 6 to get 3. So for our final answer, we'll say 1/12 tangent inverse of x over 3 plus c is our antiderivative. Let's try another one. Let's try one that's a little different. Let's do the integral of secant inverse of t over the absolute value of t times the square root of 1 minus t squared dt. What you might notice here is we seem to have this inside function that's throwing off everything else. So let's call that inside function of secant inverse, let's call that our u. U is secant inverse, and then we can calculate our du, which is the derivative of secant inverse, which you remember is dt divided by the absolute value of t times the square root of 1 minus t squared. And fortunately, all of that already sits in my function. So this is going to clean up really nicely. The secant inverse of t becomes just u. And the dt over the absolute value of t minus the square root, or times the square root, becomes our du. And this is a very easy integral to take. We end up with u squared divided by 2 plus our constant. Or substituting back that u, the secant inverse of t squared divided by 2 plus our constant. Let's do one last problem as we wrap up these inverse trigs integrals. Let's do a definite integral. Let's take a definite interval from 1/3 to the square root of 3 over 3 of dx over the square root of 4 minus 9x squared. In a way, this is very similar to our first problem. We want to have subtracting u squared. And if we are subtracting u squared, that becomes the sine formula, subtracting u squared. So let's use that to help with our substitution. We'll make the u squared equal to 9x squared. Therefore, u is the square root, just 3x. And du, the derivative, is 3 dx. So multiply by 3 1/3. Also, we're going to multiply the limits of integration by 3 as we set this up. Keeping my highlighting in check here, we've got the u is 3x, the du is 3 dx. So what we end up with is 1/3 times the integral. We're going to multiply the limits by 3. 1/3 times 3 is 1. Root 3 over 3 times 3 is the square root of 3. 3 dx becomes our du over the square root of 4 minus u squared. So we end up with 1/3 times, this is the sine inverse of u over 2, because we divide by whatever squared, whatever that a squared is. A squared, 2 squared is 4. Integrated from 1 to the square root of 3. So we end up with 1/3 times the sine inverse of root 3 over 2 minus the sine inverse of 1 over 2. So we have 1/3 times, if you remember our unit circle, sine is the y-coordinate, that's root 3 over 2 at pi over 3. Minus, sine the y-coordinate is 1/2 at pi over 6. So we end up with 1/3 times pi over 3 when we subtract, or pi over 9, is the area under our curve between 1/3 and square root of 3 over 3. So we've got 3 new formulas today. The sine inverse, tangent inverse, and secant inverse results. Those 3 formulas are what we're going to be using, still working with our substitution strategies as we take integrals that result in inverse trig functions. Try some of these. We'll talk about them more in class and answer any questions you might have. Good luck. We're going to work towards setting up applications of integrations, first by talking about finding areas between curves, which is exactly our question. How do we find the area between 2 curves? And we'll start out by kind of mapping out the idea behind what we are doing. If I've got some graph let's say there's some function f of x going from a to b. And beneath it, there's some other function, we'll call it g of x, between a and b. What we're trying to do is find the area between those two curves. Now, if I were to just integrate from a to b of f of x dx, that would give me the entire area down to the x-axis. But we don't want that. In fact, what we don't want is the g of x part, the underneath part. We want to get rid of that part. So what we'll do is we'll subtract the integral from a to b of the g of x dx. And when we do that, it will give us, in red here, the area in between f of x and g of x. Now we can clean that up a little bit and bring that together because we're integrating from a to b on both of them. We could just write that as a single integral of f of x minus g of x dx. In other words, we find the area underneath the top curve and subtract the area underneath the bottom curve. I should have numbered that, number 1. For number 2 here, though, just to give a little bit of a special case here, let's say my f of x is decreasing and my g of x is increasing. But we still want the area from a to b. We still want the area between these two curves. What happens here, though, is they cross, the two curves cross at some middle point. I'll call that middle point C. And what happens is now the top function is the bottom function, and the bottom function is the top function. And we have to account for that in our integration. So first, we'll integrate just from a to c, where they intersect. And we'll take the top function f of x and subtract the bottom function g of x dx. Then we'll add to it the right side. But on the right side, as we go from c to b, you'll notice the g of x function's on top. So we'll start with g of x and then subtract off the bottom function f of x dx. And so sometimes what we have to do really is we divide the graph into two parts and find the area of the left part separate from the area of the right part, and then add them together, so that way the top function is always positive and the bottom function is always negative. So that's kind of in theory what we're doing. Let's work out some examples so we can get good at finding the area between two curves. Let's start with a simple one. We're going to find the area between f of x equals x plus 5 and g of x equals 2x plus 1. And we're only going to be interested in the values between 0 and 4. So x plus 5, that's this first function, x plus 5. And then the 2x plus 1's got a lower y-intercept, but it's steeper. And we're interested in going from 0 to 4. Now, I want to know, do they actually intersect at 4? One thing we can do to figure out where these intersect is we'll set the x plus 5 equal to the other function, 2x plus 1. And sure enough, if we subtract x and subtract 1, we find out x equals 4 is where they intersect. So we really are finding the area of this triangle between our two graphs. Let's move the x plus 5 on top. The blue graph, x plus 5 is on top. So, to do that, we will take an integral. We're integrating as x goes from 0 to 4, and we'll take the top function, which is the x plus 5, and we'll subtract the bottom function, as we subtract, it's going to change the sign in front of each term. So we'll have negative 2x and negative 1 dx. Combine like terms on this before we solve. From 0 to 4 of negative x plus 4 dx. And now we're ready to actually integrate. When we integrate it, we get negative x squared divided by 2 plus 4x integrated from 0 to 4. So first plugging the 4 in, negative 4 squared is negative 16 over 2 plus 4 times 4. And then we would subtract plugging 0 in. But if we plug 0 in, 0 squared over 2 plus 0 times 4 is just 0. So that's kind of nice. It's all 0. So what we end up with is negative 8 plus 16, or just an area of 8 square units between x plus 5 and 2x plus 1. Now that one's probably a little simple because those were all straight lines. Let's do one a little more interesting. Let's find the area between f of x equals x squared minus 4 and g of x equals x plus 2. Now, if you remember your properties of graphs, x squared minus 4 we'll know is a parabola that comes down 4 units. That's the f of x. And for the g of x, x plus 2, that's going to have a y-intercept of 2, and it's going to have a slope of 1. And so it's going to look something like this. We're being asked to find the area between the two curves. How much area is there in that space? Now, if you forget exactly how the graphs look, or if some of the graphs are more complex, don't hesitate to use your graphing calculator to help you graph the different functions. Or I also highly recommend the online graphing calculator or the app on your phone, Desmos. They're really good for graphing and zooming in on certain areas of the graph, so you can see exactly what you're taking the area of. Now we can see our x values are going to range down to this bottom point off to the left, and then x is going to grow up to this top point off to the right, but we don't know exactly what x values those are yet. The way we can find them is we will set the functions equal to each other to see when they cross. X squared minus 4 equals x plus 2. Subtracting x gives us x squared minus x. Subtracting 2 gives us minus 6. Factoring to x minus 3, x plus 2. So we can see that x is equal to a positive 3 and a negative 2. So the one to the left must be negative 2. And the one to the right is when x equals 3. So that tells us we're integrating from x starting at negative 2. It's going to move off to the right all the way up to 3. To find our area, we just subtract the functions. Notice the green function, the g of x is on top, so that's our positive x plus 2. The blue function, the x squared minus 4, is on the bottom. That's what we're going to subtract, which changes the sign. Negative x squared plus 4 dx. And so if we combine like terms, we're going from negative 2 to 3 of negative x squared plus x plus 6 dx. Now that we have the function, it should integrate really nicely. We end up with negative x cubed divided by 3 plus x squared divided by 2 plus 6x integrated from negative 2 to 3. All right, let's plug in those limits of integration. We have negative x cubed. Negative 3 cubed is 27 thirds. Plus 3 squared is 9 halves. Plus 6 times 3 is 18. Then we subtract off the lower limit. When we plug negative 2 in, negative 2 cubed is negative 8. The opposite of negative 8 is positive 8, but we subtract it off, so we have negative 8/3. Negative 2 squared is 4. Divided by 2 is 2. Subtract 2. And negative 2 times 6 is negative 12. Opposite of that's a positive 12. And so when we plug all that in our calculator, negative 27/3 plus 9/2 plus 18 minus 8/3 minus 2 plus 12, change it to a fraction, we end up with 125/6 is the area between these two curves. Let's try another example that's a little more interesting. Let's find the area between f of x equals the square root of x, g of x equals 3/2 minus x over 2, and h of x equals 0. So f of x equals the square root of x is going to be this blue function. G of x starts at 3/2 and has a slope of negative 1/2, so it's this green function. And h of x is 0. That's just the x-intercept, so we don't need to really draw it. The x-intercept is kind of our bottom limit. We're finding our area of this shape. What's nice about these shapes is the bottom half is not another function. The bottom half is just 0, so we don't really have to subtract anything off. But what you notice is we really have two different parts to the function. The left part of the function, that I'll highlight in yellow here, is under the square root of x. The right part of the function, that I'll highlight in pink, is under that linear equation, 3/2 minus x over 2. So we're going to need a separate integral for both halves. First, we'll take the integral. Actually, we need to know a couple things. We need to know where the graph starts, where they intersect, and where we hit the ground. Where the graph starts on the left, that's where the square root of x hits the x-axis of 0, and if you square both sides, we see x is equal to 0 at that point. On the right side, that's where the green line hits 0, so we could say 3/2 minus x over 2 equals 0. Multiply everything by 2 gives us 3 minus x equals 0. Add x to both sides, and we get x equals 3. So we've got an x-coordinate of 3 on the right. In the middle, this is going to take a little bit more work. We want to know where the green and the blue line intersect. So we'll set them equal to each other. 3/2 minus x over 2 equals the square root of x. Let's get rid of the fractions by multiplying by 2. Gives us 2 square roots of x. Square both sides gives us 9 minus 6x plus x squared equals 4x. Subtract the 4x from both sides, putting it in order. X squared minus 10x plus 9 equals 0. Factoring. X minus 9, x minus 1 equals 0. So x is either equal to 9 or 1. Well, we know we have to be less than 3 because we've got that point of 3 on the right, so it must be the 1. If I wasn't sure, though, we could plug them back into the original equation, and we'd find out that that 9 is an extraneous root. So 1 must be our solution. All right, now we have everything we need to know. Now we're ready to set up our integrals. First, we're going to integrate from 0 to 1. This is that yellow part. And notice the blue line is on top. That's the f of x function, the square root of x, or x to the 1/2, dx. And I'll put a yellow line over it so we know that's the yellow part. But in addition to that, we've got the right part, which is the green line. So we're integrating now, as x goes from 1 to 3, of the green line, which is 3/2 minus x over 2 dx. I should probably write that in green because that's the green function. 3/2 minus x over 2. And I'll put a pink line over that to say that represents the pink part of that shape. And now we're ready to start solving. X to the 1/2, that becomes x to the 3/2 times 2/3, integrated from 0 to 1, plus we have 3/2 x minus x squared over 4, and that's integrated from 1 to 3. I'm going to scroll down a bit to give me some space, because this is going to be a little bit longer. So first, plugging 1 in to x to the 3/2 gives us just 2/3. Minus, plugging 0 in gives us 0. Plus, plugging 3 in, 3 times 3 is 9/2. Minus 3 squared is 9/4. And then we'll subtract, plugging the 1 in, which gives us minus 3/2 plus 1/4. And so we have 2/3 minus 0 plus 9/2 minus 9/4 minus 3/2 plus 1/4. Plugging that into our calculator, we get a total area of 5/3. Let's try another one that we have to partition, but for slightly different reasons. Let's find the area between f of x equals x cubed plus 3x and g of x equals 4x. I would use a graphing calculator on this or use Desmos. And the scale's not too important in our picture as long as we get an idea of what's happening. The cubic, you'll see, comes up. Actually, let's do that in blue. The cubic, you'll see, comes up, levels off, and then goes back up. The linear function g of x comes in diagonally, hits the x-axis, and comes out diagonally. And so the area between the curves, there's two parts. A part on the left and a part on the right. We're going to need a different integral for each part. So first, maybe if I highlight in yellow the first part and in pink the second part, because there's a different function on top for each one. That's going to change our limits of integration. We also need to know the intersection points. We have a pretty good idea that the first intersection point is 0, but for the other ones, we'll need to set the functions equal to each other. X cubed plus 3x equals 4x. Subtract 4x, we get x cubed minus x equals 0. Factor out an x, leaves behind x squared minus 1. Factor the difference of squares, we have x plus 1, x minus 1. And so we know our values are 0, as expected, -1, and +1. So x is -1 on the left, +1 on the right. We now know what limits we have to take of our integration as x increases from left to right. We're going to integrate from -1 to 0. This time the blue function's on top, the cubic, so we'll start with that, x cubed plus 3x. And we'll subtract the lower function, the minus 4x, dx. That will give us the yellow piece. Then we'll add to it the integral as x goes from 0 to 1. But now the green function's on top. So we'll start with the 4x, and we'll subtract off the x cubed plus 3x. Oops. X cubed minus 3x, because we're subtracting the whole function, dx. And that will tell us the pink piece. Then we're ready to actually evaluate those integrals. We know that's going to be x to the 4th divided by 4 plus 3x squared divided by 2 minus 4x squared divided by 2. Actually, 4 divided by 2 is 2, so I'm just going to say 2x squared. That's being integrated from -1 to 0. Plus, the second half, we get x squared divided by 2, which makes it 2x squared, minus x to the 4th divided by 4, minus 3x squared divided by 2, and that's integrated from 0 to 1. So on this first part, if we plug 0 in, nothing exciting happens. Then we're going to subtract the -1 plugged in. So we have -1 to the 4th power is 1, but we're subtracting, so 1/4. -1 squared is 1 times 3/2, but we're subtracting the 3/2. -1 squared is 1 times -2, but we're subtracting, so it's going to become a +2. On the right side, we're plugging in, starting with the +1. So if we plug in +1, we get +2 minus 1/4 minus 3/2. Oops, that should have been 3/2 on the left side. And then when I plug 0 in, everything goes to 0, so there's nothing exciting left. And so what we have is -1/4 minus 3/2 plus 2 plus 2 minus 1/4 minus 3/2. Use the fraction button on the calculator, and we find out that that area is 1/2. And so that's how we can split up the functions to find the areas of the individual pieces. When the top function switches with the bottom function, we need to set up another integral. But there's actually another way to solve this problem that would have saved us quite a lot of grief. Let's take a look at that. Number 5. Sometimes we can use symmetry to our advantage. So we're doing the same functions, f of x equals x cubed plus 3x, and g of x equals 4x. And trying to draw that same graph here, the cubic came up, leveled off, and took off. The linear function came down, hit 0, and continued out. And what you notice, if I had drawn this to scale, if you graph it on Desmos or on your calculator, you'll see it a little clearer, is the left and right side are exactly the same shape and exactly the same size. Because they're exactly the same shape and same size, we only really need to find the area of one of the pieces. And then we'll double that area to account for the other piece. So I'm just going to do the integral from 0 to 1 of that right side. The integral from 0 to 1, and then we'll multiply the result by 2. So 2 times the integral, with the green on top, would be 4x. Let's do that in green. Minus the bottom function, minus x cubed minus 3x dx. That becomes 2, let's do this in purple, times 2x squared minus x to the 4th divided by 4 minus 3x squared divided by 2, integrated from 0 to 1. So we have 2 times, plugging 1 in is really nice. We're just left with 2 minus 1/4 minus 3/2 And when we plug 0 in, everything goes to 0. And now I can plug this in my calculator, multiplying by 2 out front, and we end up with the same answer of 1/2. And that symmetry made solving the problem a lot easier. So always be aware of looking for symmetry as you solve these problems. Symmetry can simplify the amount of integration we actually have to set up and evaluate. There is a slight twist we can do to this assignment that we're looking at today, and that is instead of just integrating as x moves from left to right, sometimes it's easier to integrate with respect to y. And the idea here, setting this up, is really similar. We're going to have some function, maybe it's g of y. And we'll have another function, maybe it's f of y. And we're interested in the area between them from a to b. But this time, a and b are y values. It's still the exact same idea. We're still integrating from a to b. And we still take the top function. You notice the f of y is higher. We're looking at it sideways. F of y is on top of the g of y function. And then we'll subtract off the g of y function. And we'll take that integral with respect to y this time. And that can give us the exact same area, but sometimes doing it with y's is much easier than doing it with x's. And the great example of that is the example that we did up above. I think we called it example 3 previously. When we found the area between f of x equals the square root of x, g of x equals 3/2 minus x over 2, and h of x equals 0. If you remember when we graphed that, we had our square root of x, we had our 3/2 minus x over 2, and then h of x at 0. And that gave us this. It's kind of like a triangle with one side's kind of curvy. And we wanted to find the area of that. We had to do it with 2 different integrals when we were integrating with respect to x, because there was a change in which function was on top. But if we integrate with respect to y, first we'll change all these functions to y functions. So y equals the square root of x. If I square both sides, we get y squared equals x. That's my new blue function. With the g of x function, y equals 3/2 minus x over 2. If I multiply both sides by 2, we have 2y equals 3 minus x. Add x and subtract 2y. We have a new green function. So the green function we can now think of as 3 minus 2y. The blue function we can think of as y squared. We still need to figure out where they intersect. We know they intersect when x is equal to 3. I'm sorry, when x is equal to 1. But we don't know what y equals necessarily yet. So let's set them equal to each other. Y squared equals 3 minus 2y. We'll add the 2y. We'll subtract the 3. We'll factor to y minus 3. I'm sorry, y plus 3, y minus 1. So y is negative 3 or positive 1. Well, if we had gone off with our y squared, we would have ended up with that negative 3 value down there. But we're interested, for our purposes, in just that 1. The y's are going from 0 up to 1. That's what we want to integrate. We're going to integrate the y's from 0 to 1. And if we look at it sideways, we see the green function's on top. That's the 3 minus 2y. And then we'll subtract off the blue function, the y squared. And we'll integrate that with respect to y. And now, rather than having two integrals like we did before, we only have one integral. Hopefully we get the exact same answer. Let's see. Taking the integral, we have 3y minus 2y squared divided by 2. The 2's divide out. Minus y cubed divided by 3. Integrating from 0 to 1. If I plug 1 in, we get 3 minus 1 minus 1/3. And then we would subtract, plugging the 0 in, but what's nice is all that goes to 0, and we end up with the exact same answer of 5/3. And so sometimes we're going to find it's easier to integrate with respect to y. Sometimes it's easier to integrate with respect to x. But the idea is exactly the same. If we want to find the area between two curves, all we need to do is take the integral and subtract the two functions. So take a look at trying some of these on the assignment. Come to class with any questions that you might have, and we will see you then to talk about these in more detail. Today we're going to look at a very common application of integration found in like mechanical engineering when we need to find a volume of an odd three-dimensional shape. Often we'll do it by a process called slicing. The question we're going to answer is, how do we find the volume of a curve rotated around an axis? And to set this up, we're going to look first at the idea of what's going on in the background, come up with a general form, and then we'll try several examples. So first, we're going to use what's called the disk method. And the idea of the disk method is we're going to have a curve. And we're going to take that curve and we're going to rotate it around the x-axis. And we're going to end up with this three-dimensional shape as a result. This three-dimensional shape that's rotated around the x-axis, taking that function f of x and say, let's spin it around the x-axis. If I can try and draw in 3D. We want to find the volume of that shape. And the way we're going to find that volume is we're going to cut a slice out of it. And that slice is going to have some thickness to it. We're going to want that thickness to be really small. So we'll call that thickness d of x. And notice that ends up, if I rotate it flat, what we end up with is a cylinder with a very thin height called d of x. The radius of that cylinder, you'll notice, is exactly the distance from the x-axis to our function f of x. In other words, the radius of that cylinder is f of x. So if I want to calculate the volume of that individual cylinder, the volume of a cylinder is the area of the base, pi r squared, times the height. Or in our case, pi times the radius, which is the function, squared, times the height, which is the small tiny d of x. And what you'll notice is if we cut cylinders like this all the way through the shape, kind of like slicing a loaf of bread, all the way from a low point of A to a high point of B, if we want the volume of all of them together, we'll just integrate that distance from A to B of each of those volumes of pi times f of x squared dx. And that gives us the volume of all of the slices that we've cut. Now, this pi is a constant, so let's move the pi out front. And so for our final volume formula, pi times the integral from a to b of the function squared dx is how we can cut our shape into disks, skinny little disks, and calculate the volume of all of the disks between A and B. That's the disk method. Now there's one variation of this disk method that can come up, and I want to look at that real quick. It's really based on the same idea. The idea is we've got some function, we'll call it f of x. But the problem is there's another function. Actually, let's color code this. We'll do f of x in blue. And I'll do g of x in green. Maybe it spins like this. And when I try and rotate this function around the x-axis, yes, we'll end up with f of x mirror down here, but also g of x is mirror down here. And what you see happens is we still end up with these circles going around the graph, but there's a hole down the center of our f of x function. So f of x is solid, but there's a hole down the center formed by that second function below the g of x. If we were to cut a slice out of this guy, our slice would have a hole in the center. So here's our slice. There's the hole in the center. It's still going to have some width to it. We'll call that width d of x still. But now we've got this hole in the center. And it almost looks less like a disk and more like a washer. So we'll call this the washer method. A washer has a hole in the center. So when we're finding the volume here, we've got to account for the fact that we've cut a hole out. And notice that hole, the height of that hole is that g of x function. And the radius of the big circle is the f of x function. So, again, if we want the volume of this entire shape, we'll still have to do pi times the big radius squared times the height, but then we're going to have to subtract off that hole cut out the center, which is pi times the little radius squared times the height. So plugging in our function, volume is equal to pi times the big radius, which is our f of x, squared, times the height, which is dx, minus pi times the little radius, g of x, squared, times the height of dx. Ran out of space. So give me a little more space. I'm going to factor out the pi out front, because they both have a pi. And I'm going to factor the dx out to the right, because they both have a dx, which is going to give us f of x squared minus g of x squared is the volume of one slice. But again, we want the entire volume. So if I slice this guy all the way through like I'm slicing a loaf of bread, all the way from a lower limit of a to an upper limit of b, what we're really saying is we want to integrate from a to b pi times the f of x squared minus the g of x squared dx. Or, because pi is a constant, we can pull it out front. Our volume is the integral from a to b, pi times the integral from a to b of f of x squared minus g of x squared dx. And so if we have a hole in the middle, we can use what's called the washer method. And very similar to how I found the area between two curves, where we took the top integral minus the bottom integral, we do the same thing with the volume and take the top function minus the bottom one and integrate over our distance to find the total volume of our shape with a hole down the center. All right, so this is the logic we're using. Let's actually try it and find some volumes. Let's do some examples. Let's find the volume of a solid of revolution formed by rotating f of x equals 1 over x over the interval from 1 to 2. So we've got our function 1 over x. We're going to go from 1 to 2. So we're going to rotate it. See how my 3D drawing does? We're going to rotate it around the x-axis. Notice this does not have a hole through it, so we're going to use our disk method to find its total volume. The volume is pi times the integral from a to b. Notice we have a lower limit of 1 and a upper limit of 2. Integral from 1 to 2. Of the radius, which is just the function, 1 over x, or x to the negative 1, squared dx. Pi times the integral of the radius squared dx. Simplifying a bit, multiplying the exponent through, we get x to the negative 2 dx. And this integral is really easy for us to take. We've got pi times x to the negative 1 divided by negative 1 makes it negative, integrated from 1 to 2. Plugging in, we have pi times negative x to the negative 1. 2 to the negative 1 is 1/2. Plus, plugging 1 in is 1. So when we simplify that, negative 1/2 plus 1 is just 1/2, or pi over 2. So the volume of this shape rotated around the x-axis between 1 and 2 is pi over 2 square units. Let's try another example. Let's find the volume by rotating f of x equals the square root of 4 minus x and y equals 0 over the interval from 0 to 4 around the x-axis. So we've got the square root of 4 minus x. And we've got y equals 0, which kind of provides the bottom of our shape. And we're going to go from 0 to 4. And then we'll rotate that around the x-axis. And we almost end up with this cone-looking thing that we're going to find the volume of. So volume is equal to pi times the integral of our distance from 0 to 4 of the function, the radius, the height of the function is the square root of 4 minus x squared dx. And that's really nice because when we square, we just get 4 minus x dx, which is an integral we can take very quickly. So we have pi times 4x minus x squared over 2, integrated from 0 to 4, which is equal to pi times, plugging the 4 in, 4 times 4 is 16, minus 4 squared is 16, divided by 2 is 8. And then we plug the 0 in, but that's just 0. And so we end up with 16 minus 8, or 8 pi, for our volume, formed by rotating the square root of 4 minus x around the x-axis between 0 and 4. 8 pi square units. We took these first two and we rotated around the x-axis. There's no reason we have to rotate around the x-axis. We can rotate around anything, although the axes are always easier. Let's find the volume by rotating y equals 2x over the interval from 1 to 4. But this time we're going to rotate around the x-axis. Oops, not the x-axis, the y-axis. We've already done the x-axis. So we know y equals 2x, starts at the origin and comes up with a slope of 2 over 1. We want to go from 1 to 4. And that's what's going to rotate around the x-axis. So it's going to kind of make this cone-looking shape with its top cut off. Well, if we're rotating around the y-axis, we have to change everything in terms of y so we can integrate as y goes up. So we need to know first what values are we integrating between. So when x is 1, what is our y value? Well, that's easy. Plug 1 into our equation, and y is equal to 2. So we've got a height of 2. When x is 4, what is our y value? Well, y is equal to 2 times 4, so y is equal to 8. So now we can see that the volume is equal to pi times the integral as our y's are climbing from 2 to 8. But our radius now needs to be in terms of y. So we also need to take our function and make it an x equals function. So if y equals 2x, x is equal to y over 2. Squared dy. So if we're rotating around the y-axis, the only difference is we have to change everything into y's. Sometimes you already have it in terms of y, which is the reason it's easier to do it around the y-axis. But if everything's in terms of y's, then we integrate from the low y to the high y. We take our y function and square it, take the derivative or the integral dy, and we're ready to go. Solving from here is simple. We're going from 2 to 8 of y squared over 4 dy. So that gives us a volume of pi times y cubed divided by 12 integrated from 2 to 8. Plugging in, we've got pi times 8 cubed divided by 12 minus 2 cubed divided by 12. And if I plug that parentheses in my calculator, I get 42. Don't forget the pi. 42 pi square or cubic units is the volume of this shape rotated around the y-axis. We haven't done any washers yet, so let's try a washer problem. Let's find the volume by rotating the region bounded by f of x equals the square root of x, g of x equals 1 over x, over the interval from 1 to 3 about the x-axis. So f of x is the square root of x. G of x is 1 over x. And we're integrating from 1 to 3. And now what's interesting to note is when x is 1, that's where they actually intersect each other. Because the square root of 1 is the same as 1 over 1. But then we're going to cut our slice. So let's see if we can make the same shape on the other side. I think the hardest part of today's lesson is drawing in 3D. So we're going to rotate at 1 and rotate at 3. That's what's going to create our hole. And we want to find the volume of this shape that has this hole in the bottom of it. We know our volume is equal to pi times the integral. X's are going from 1 to 3. And this time we're going to subtract the square of the functions. So first, the tall function. The tall function is the square root of x squared. And then we have to subtract out that whole, which is x to the negative 1 squared dx. Or simplifying, we have pi times the integral from 1 to 3 of x minus x to the negative 2 dx. We're really good at taking these integrals by now. We have pi times x squared divided by 2. When we take our antiderivative here, we get x to the negative 1 divided by negative 1, which is going to change that minus to a plus. And we're integrating from 1 to 3. Plugging 3 in. 3 squared is 9 halves. Plus, plugging 3 in, we get 1/3. Minus, plug the 1 in, 1/2, minus 1. Plug that into the calculator, hit the math button, we get 10/3 pi, or 10 pi over 3 cubic units is the volume of this shape that we get when we rotate around the x-axis by subtracting out the hole in the middle. Let's do one last example that's maybe a little more involved. But now we have all the tools we need to find the volume by rotating the region bounded by f of x equals x plus 2, g of x equals x squared, and x equals 0, we've already got the word rotated, about the y-axis. So this time we're doing the y-axis. X equals 0. That provides a nice boundary right on the y-axis. We've got f of x equals x plus 2, which we know is a straight line starting at 2. And then we've also got x squared, which curves up. And it gives us this weird shape. That's x squared. When we rotate that around the x-axis or the y-axis, we end up with this interesting shape. A hole down the center so solid, rotated around, kind of has this triangle dug out of the center, but that triangle doesn't go all the way down this time. It only goes part way down. Let's see if we can figure out our key points here. The obvious one is 0, 0. We're interested in the y-coordinate mainly. We want to know where that hole stops. How deep does that hole go? That's where that x plus 2 hits the y-axis. And you might remember that the y-intercept on x plus 2 is 2. Or if you weren't sure, we know the x-coordinate there is 0. So 0 plus 2 equals y, or y equals 2. We also need to figure out the height. And that's where the two functions hit each other. That's where the x plus 2 is equal to the x squared. So if I subtract it off, we get x squared minus x minus 2. Factoring, we get x minus 2 times x plus 1. Solving that then, we get x equals a positive 2 or negative 1. So we can see x is equal to a positive 2, not the negative 1, because that's not part of our graph. That's past our 0. We don't need to worry about that one. But if x is negative 2, we're revolving around the y-axis. We need to know the y-coordinate. So when x is 2, what is our y equal to? Well, we can plug it into either function. I'll plug it into g of x. G of 2 is 2 squared, or 4. So our final height there is 4. Now that we've found all the important features of this graph, we're ready to find the volume. First, let's think about just the outside. If there wasn't a hole cut into this graph, if that cone wasn't cut out of the graph, the volume would be equal to pi times the integral as y goes from 0 to 4 of that outside function. The outside function is y equals x squared. We need to put it in terms of y, so the square root of y must equal x. So the square root of y squared dy, because we always square the radius. That would give us the volume of the entire thing. The problem is the hole is cut out, but the hole doesn't go all the way down. So let's subtract the hole and just find the volume of that piece. The volume of that piece is pi times the integral, this time going from just 2 to 4. And now we need the function of the hole, which is the y equals x plus 2. But because we rotated around the y-axis, we have to solve for x. So y minus 2 equals x. Y minus 2 squared dy. And now we have our integrals that we can solve to find the volume. For our first one, actually let's just simplify this first by doing the squaring. Pi times the integral from 0 to 4 of y dy minus pi times the integral from 2 to 4 of y squared minus 4y plus 4 dy. We're going to move quickly through the integrating because we should be really good with this part by now. We have y squared over 2 integrated from 0 to 4 minus pi times y cubed over 3 minus 2x squared plus, oops, not x, y squared plus 4y integrated from 2 to 4. All right. Plug in what we know. We've got pi times, plug in the 4. 4 squared is 16, divided by 2 is 8. Plugging the 0 in gives us nothing. Minus pi times, plugging the 4 in, 4 cubed is 64 thirds. Minus 4 squared is 16 times 2 is 32. Plus 4 times 4 is 16. Then we'll subtract off, plugging the 2 in. 2 cubed is 8 thirds. Plus 2 squared is 4 times 2 is 8. Minus 4 times 2 is 8. And let's plug all that into the calculator. And when we put it all together, we'll end up with 16 pi over 3. So that's what I want you to take a look at today for our assignments. We are doing the disk method and the washer method as we find the volume of a region formed by rotating 1 or 2 or more graphs around either the x-axis or the y-axis. Our general formula is the same though, pi times the integral of the function squared dx. Try some of these and we'll talk about them more in class. Today we're going to take a look at continuing our work with finding volumes of revolutions, this time using a method called cylindrical shells. We're going to answer the question, what is another way to find the volume of a solid of revolution? We've already used the method of disks and washers. We're looking at another way, and that's using these things called cylindrical shells. So again, we're going to start with the idea behind what we're going to do, and then we'll work into some practice. These things called cylindrical shells. Let's say I've got some function from a to b, and we're going to revolve it around the y-axis. So it's kind of got this hole in the middle, rotated around as best as you can imagine my 3D drawing. What I want to notice, though, is if I cut one of these rotations around, if I took just a small rectangle, we'll give it a width of delta x, or dx, better said dx. And when that piece rotates around, we end up with this little cylinder. Let's pull it out. We end up with this little cylinder where the height of that cylinder, it goes up to the function, the curve. So the height is actually f of x. The radius of that cylinder going all the way to the outside is just whatever that x distance is that generates that f of x result. So the radius is x. And it has a width of delta x. And in fact, what we're going to do is we're going to slice it down the side and open it up. And when we slice it and open it up, lay it out flat like you're tearing off the label of a soup can and laying it flat, you get this rectangle, where the height of the rectangle is still f of x. The length of the rectangle is the same as the circumference of the circle. And the formula for the circumference of a circle is 2 pi times its radius. And the radius in our case was just x. And we know that this guy has a width of delta x, or dx. So if I wanted to find the volume of one of these rectangular prisms, we would take the length times the width times the height, multiply the 3 dimensions together. We would have 2 pi x times the f of x times the height of d of x. And now what I want to see is if I started from my A with that first cylinder, and I stretch across until I get to B with my last cylinder, I'll end up with all of the little tiny cylinders, the tiny cylindrical shells, all the way from A to B. And if I want to add them all together, we're really taking the integral from A to B of 2 pi x, that's the length, times f of x, the height, times the d of x. Well, the 2 pi is a constant, so that can come out. And what we end up with is a volume formula for our cylindrical shells of 2 pi times the integral from A to B of x times f of x dx. And that is going to be the formula we'll use to help us find our volume of our 3-dimensional solid of rotation by cutting into little cylinders that go all the way across. I want to note something also, what we did, that this example, I rotated around the y-axis, but we integrated with respect to x. When we did disks, everything went the same way. With disks, if you rotated around the y, you were probably doing disk and integrating with respect to y. But with shells, it's always the opposites. We always integrate in the opposite direction of the revolution. It's an important difference between the two methods. Okay, let's try some examples with some numbers to help us get our mind around exactly what we're doing. Let's say we take a shape that is bounded by f of x equals x squared above. So that's the top of the shape. And the x-axis below. On the interval from 1 to 2, and we want the volume when rotated around the y-axis. So drawing a picture to get an idea of what we're working with. We've got the shape x squared. But we only want to consider it between 1 and 2 as it drops down to the x-axis. And then we're going to rotate that around the y-axis. So let's see if I can draw my shape as it rotates around. So it's kind of got this hole carved out of the center that goes all the way down to the bottom. What we're going to do is we're going to put shells in the middle of it. Cylindrical shells, where the volume is equal to the 2 pi times the integral. We're going from 1 to 2 is where those edges go from, times x, that's our length, times the height, which is just our function, x squared dx. Well, we can simplify that to get 2 pi times the integral from 1 to 2 of x cubed dx. And we can integrate this really quick and find our area. 2 pi times x to the 4th divided by 4, integrated from 1 to 2, is 2 pi times 2 to the 4th is 16, divided by 4 is 4, minus the 1/4, which is 15/4 times 2 pi, which is 15 pi over 2 cubic units in the volume of our shape. What you might find is when we're using cylindrical shells, conceptually it's a little trickier to get our mind around where they start, where they end, and how they're formed. But the integration step quite often is much easier with cylindrical shells than it was with disks and washers. Let's try another example. Let's look at the shape that is bounded above by f of x equals 3x minus x squared, and below by the x-axis on 0 to 2. And we're going to find the volume when we rotate around the y-axis. Now, I'd suggest using either your calculator or Desmos to see what 3x minus x squared looks like. It gives us this nice little parabola. But we're only going from 0 to 2. So we're going to stop our rotation right there. Let's see if I can draw our same shape. And we'll rotate around the y-axis to get what's almost a perfect cylinder, but it's got this little curve coming in, and then the inside is cut out of it. And we're going to cut cylindrical shells on it. To find our volume. Volume is 2 pi times our integral. We're integrating from 0 to 2. The radius is just our x distance. The height is the function, 3x minus x squared dx. Distributing that x through, we'll have 3x squared minus x cubed dx. And our integrating from 0 to 2, when we integrate, we'll have x cubed divided by 3, clears the 3, minus x to the 4th divided by 4, integrated from 0 to 2. Plugging in those values, we have 2 pi times 2 cubed is 8, minus 2 to the 4th is 16, divided by 4 is 4. Plugging 0 in is just subtracting 0. 8 minus 4 is 4, times 2 is 8 pi for our volume, 8 pi cubic units. Let's try one where we revolve around the other axis. Let's bound on the right. By g of y equals 3 over y. And on the left, by the y-axis. For y is going to go from 1 to 3. So that's our y's going from 1 to 3. It's not our x's like normal. And we want the volume rotated around the x-axis this time. Three over y curves down, something like this. We want to go from where y is 1 to where y is 3. Y is going from 1 to 3. And that's the shape that we want to rotate around. So it's got a hole straight down the middle. And it's got this weird cone shape on top and a full cylinder on the bottom. And we're going to be drawing cylindrical shells in there. But this time, the edge of the cylindrical shell is going between 1 and 3 on the y-axis, because we always integrate with respect to the opposite variable. So we rotate around the x. We're going to integrate with respect to y. Our volume is 2 pi times the integral as y's go from 1 to 3. This time, the radius of our cylinder is just the height, or just the y. The distance, though, the height of our cylinder, that length, is our function in terms of y, which we already have, is 3 over y dy. And that's nice because those y's will divide out. So we really just have 2 pi times the integral from 1 to 3 of 3 dy, which is a real nice integral for us to take. 2 pi times 3y, integrated from 1 to 3. Or 2 pi times 3 is 9, minus 3 times 1 is 3. 6 times 2 is 12 pi for our volume when we rotate it around the x-axis. Let's try another example. This time we're going to increase our complexity. This time we're going to revolve around another line. When we revolve around another line, what that's going to do is it's going to move our circles. It's going to adjust the radius. So we're going to have to look at our radius of our circle, which is normally just x or just y, and maybe add or subtract something or take a number minus or plus that x. So let's take a look at this example. Let's look at the shape that's bounded above by f of x equals x squared, and below by the x-axis on the interval from 0 to 1. We're going to find the volume when we rotate around, this time, the line x equals -2. Not the x-axis, but x equals -2. How is that going to change things? So going from 0 to 1, x squared looks like this, from 0 to 1. But here is x equals -2 over here. So when we revolve around that, x equals -2, let's label that. When we revolve around that, we end up with this bigger shape. So now when we cut our shells, they're going to rotate around a different point. And the thing that changes is the radius. Normally, the radius is just our x, because it's our distance from the x-axis to our point. That's normally just x. But what we notice here is there's an extra distance of 2 units. So our new radius has to be 2 plus x. So it adjusts our formula slightly. We still have 2 pi times the integral. We're still going from 0 to 1, but our radius is no longer just x. Now it's 2 plus x times our function, the height of our cylinder. The height is still the function x squared dx. And now that we've set up our integral, now we're ready to solve it. Go ahead and distribute that x squared through. Gives us 2x squared plus x cubed dx. Integrating gives us 2x cubed divided by 3 plus x to the 4th divided by 4. Integrated from 0 to 1. It's always nice when we have 0 because we're subtracting nothing. So we have 2 pi times, plugging 1 in, 2/3 plus 1/4. When we plug the 0 in, we're just subtracting 0. And this gives us 8 plus 3 is 11/12 times 2 pi is going to give us 11 pi over 6. For our volume, when we rotate around, x equals -2. So one thing we have to be careful of is if we revolve around another line, we have to adjust the radius by it's helpful to draw the picture. We might have to add a number, we might have to subtract a number, we might have to subtract x from a number. So draw a picture to see how we have to adjust that radius to get our new integration. But the radius isn't the only thing that might have to adjust. What if we are in between functions? The cylinder doesn't go all the way down to the x-axis or all the way down to the y-axis. If we're between functions, we need to adjust the height by subtracting the functions. So let's take a look at a shape that's bounded above by f of x equals x, and below by g of x equals x squared on 0 to 1. And we're going to revolve around the y-axis. I will zoom way in so I can see 1. Bounded above by y equals f of x, or y equals x, sorry. Bounded below by x squared. And it's going to rotate around the y-axis. So I can make that a little brighter. Now what you'll see is when we draw our cylindrical shells, they no longer drop all the way down to the y-axis or to the x-axis. The height has been cut off. So for our volume, our radius 2 pi times the integral, we're still going from 0 to 1 on the x's. The radius is still x because we revolved around 0. But for our height of the function, the height of the function is now the difference between the two curves. Just like when we were finding the area between two curves, we subtracted them. So we'll take our x and subtract the x squared dx. A little distributing to make the integration easier. We'll have x squared minus x cubed dx. And from here, it should solve quite nicely. 2 pi times x cubed divided by 3 minus x to the 4th divided by 4. Integrating from 0 to 1. 2 pi times, when we plug 1 in, we get 1/3 minus 1/4. Plug 0 in, we're subtracting 0. And that gives us 1/12 times 2 pi, or pi over 6, for our final volume, pi over 6 cubic units. So we have to be careful when we're between functions. We have to adjust the height. So when we revolve around another line, we adjust the radius, the x. When we're between functions, we adjust the height, the f of x. Let's wrap up by doing one example that combines both of those into one great problem. Let's look at the shape that is bounded by f of x equals the square root of 2x above, below by f of x equals, or g of x, we need a different letter, g of x equals 2x. And we're going to do this over the range, let's put it over here, over 0 to 1/2. And we're going to find the volume when rotated around y equals -1. So the square root of 2x, grab blue, looks something like this. 2x looks something like that. So we've got 2x on the bottom, square root of 2x on the top. Y equals -1, though, is what we're going to rotate around. So we end up with this big bowl-looking shape with a hole down the center. If I were to draw my cylinder in here, the top of my cylinder is going to touch the 2x function, but the bottom of my cylinder is touching the square root of 2x function. We're also rotating along the line y equals -1 instead of the y equals 0, or the x-axis. So it's going to change both the radius and the height. We have 2 pi times our integral. I want to be careful here. We're integrating as x goes from 0 to 1/2. What are those y coordinates? Well, fortunately, they both intersect here. So when we'll put in a g of x. G of 0 is equal to 2 times 0, or 0. So y starts at 0. G of 1/2 is equal to 2 times 1/2, which is equal to 1. So that height is 1. So we're really integrating from 0 to 1 as those y's climb up from 0 to 1. Our radius goes from -1 up to my height of y. So we've got a height of y, but then we've got this extra distance. That's got a measurement of 1. So the radius is actually y plus 1. For our height, it's the space between the two functions. But our functions are in terms of x. We need them to be in terms of y. So let's solve them really quick. y equals the square root of 2x, so y squared equals 2x. So y squared divided by 2 equals x. That's the bottom function, the curved one. The other function, 2x equals y. X is equal to y over 2. That's the top function, the straight function. So we multiply by our top function, the y over 2, minus the bottom function, y squared over 2 dy. And that's how we can set up our formula to integrate. From here, it's just basic calculus. From here, I might try and make this easier to solve, noticing that if I take this 2 and distribute it into the second factor, we can distribute it into either spot. But the advantage of the second factor is it clears out those divide by 2's. So we have the pi times the integral from 0 to 1 of y plus 1 times y minus y squared dy. A little bit of FOIL. Y times y is y squared minus y cubed plus y minus y squared dy. Combine like terms. The y squareds are gone, and we have y minus y cubed dy. That integrates quite nicely. Pi times y squared over 2 minus y to the 4th divided by 4, integrating from 0 to 1. Pi times, plugging in the 1, we have 1/2 minus 1/4. Oh, we've already integrated. And that's going to give us pi over 4 for the volume of that shape when it's rotated over y equals -1. So finding volumes by cylindrical shells, the general idea is we take 2 pi times the integral of x times f of x dx, where x represents the radius, and f of x represents the height. Knowing we might need to adjust the radius if we rotate around a different point. We might have to adjust the function if we're doing the difference between two functions. But this general process is how we're going to find volumes by cylindrical shells. So take a look at the homework assignment, practice several of these, and we'll discuss them more in class. We will see you then. We've spent quite a bit of time trying to find the volume of curves rotated around the x-axis. Today we're going to take a look at working in 1 dimension and also 2 dimensions, the surface area. We're going to answer the question, how do we find length and surface area? First, we're going to start by finding arc length. And we're going to start by setting up the idea behind what we're doing. I'm going to kind of oversimplify this just a bit, just to make a point of how this works. So if we've got some curve on here, if the curve is really windy, let's make it a little more windy than that. If the curve is really windy, it's difficult to actually measure how long that curve is. Well, one way we could estimate it is by drawing tangent lines that connect pieces together. And each of those tangent lines being straight can be measured a lot easier. In fact, if we pick one of those tangent lines and we zoom in on it, so that's the same tangent line zoomed in on, we'll notice that there is some distance of change in x, maybe we'll call it dx, and some vertical distance that's the change in y. We'll call that dy. Well, we know from the Pythagorean theorem that the hypotenuse, that length we're looking for, is equal to the square root of the first leg squared, dx squared, plus the second leg squared, dy squared. And I want to play with this formula just a little bit to make it a little more user-friendly to us. First thing I'm going to do is I'm going to factor out a dx squared from the expression. When I factor a dx squared out of the first term, we get 1, plus, when we factor a dx squared out of the second expression, we get dy dx squared. And this simplifies a little nicely because the square root of dx squared is just dx. And so what we have left under the square root is 1 plus, and you notice we have this dy dx. Well, dy dx is just the derivative, f prime squared. Well, that's the length of just one of the little tangent lines. If we wanted to get the length of all the tangent lines all together, we would need to add the pieces together. We would have to integrate all the individual ones. So all together, the arc length is equal to the integral from our lower limit of a to the upper limit of b, from a to b, of the square root of 1 plus the derivative of the function squared dx. It doesn't really look like a 2 on there. That's a 2. So this is going to be our general formula to find the length of any curve. So now that we have a nice little formula, the integral of the square root of 1 plus the square of the derivative, let's see if we can do a couple examples. Starting with f of x equals 4/3 x to the 3/2, and we're going to find its arc length between 0 and 1. Well, our formula, it's just off the screen here. Let me bring it back. Our formula says that arc length is going to be the integral from 0 to 1, those limits, of the square root of 1 plus the derivative squared. Let's come over to the side and see what the derivative is then. The derivative is 4/3 times, bring the exponent out front, 3/2, x to the, reduce the exponent by 1, 1/2. And that's nice because the 3's divide out and 4/2 is 2. So really the derivative is 2x to the 1/2. So that's the function, the derivative of the function, 2x to the 1/2. And we're going to square it dx. Well, if I actually do that square, we get the square root of 1 plus 2 squared is 4. X to the 1/2 squared is x, dx. And that gives us an integral we should be very comfortable solving using u substitution, where u is 1 plus 4x, and du is just 4 dx. So we're going to multiply by 4 inside and 1/4 outside. So we have 1/4 times the integral. Let's plug the limits of integration into our u. We plug 0 in, 1 plus 0 is 1. We plug 1 in, 1 plus 4 is 5. So we're integrating from 1 to 5 of the square root of u, or u to the 1/2 du. So that gives us 1/4 times u to the 3/2 times 2/3, integrated from 1 to 5. Let's go ahead and multiply the constants together. So we end up with 2/12 times 5 to the 3/2 minus 1 to the 3/2, which is just minus 1. And 2/12 we can actually reduce down to 1/6. So let's go ahead and do that. So we have 1/6 times 5 to the 3/2 minus 1. that is going to give us the length of the arc, 4/3 x to the 3/2 between 0 and 1. That's the length of that curve. We can also do this using our y's, much the same idea. Let's say we've got the function g of y equals y cubed over 3 plus 1 over 4y. Now, one thing you notice right away is we're going to need to bring that y, make it more user-friendly. So I'm going to rewrite this as y cubed over 3. Actually, let's even make it 1/3. 1/3 y cubed plus 1/4 y to the negative 1. Because we know we need the derivative of this function in order to find the arc length. Oh, I didn't give a distance. Let's give the distance. Let's find it between, let's go from 1 to 3. And that would be the y's. Y's going from 1 to 3. So now to take the derivative, because we need that in our formula, we bring the 3 out front and it reduces, so we're just left with y squared. Plus, bring the negative 1 out front, makes it minus 1 over 4 y to the negative 2. Let's do some algebra and actually move that y to the negative 2 into the denominator. Y squared minus 1 over 4y squared. And let's actually make this into one big fraction by multiplying the left part by 4y squared over 4y squared. And that'll give us 4y to the 4th minus 1 over the common denominator of 4y squared. Now let's go to our arc length formula. We're doing it with y's. That's OK. We're going to integrate with respect to y. We're going to integrate from 1 to 3 of the square root of 1 plus the 4y to the 4th minus 1 over 4y squared squared dy. Here's where the algebra becomes very helpful, because this is going to simplify quite nicely for us. First, when we square, we get the integral from 1 to 3 of the square root of 1 plus. Squaring the numerator will give us 16y to the 8th minus 8y to the 4th plus 1 over. Squaring the denominator gives us 16y to the 4th dy. Let's get this all under a common denominator, so we're going to multiply the 1 by 16y to the 4th over 16y to the 4th. And that gives us the integral from 1 to 3 of the square root of 16y to the 4th plus 16y to the 8th minus 8y to the 4th plus 1 over 16y to the 4th dy. Combining like terms on those y to the 4ths, we get the integral from 1 to 3 of the square root of 16y to the 8th plus 8y to the 4th plus 1 over 16y to the 4th dy. We're almost done with our algebra. Still integrating from 1 to 3, that numerator can factor. It's actually a perfect square. Perfect squares are what we're looking for because we can take the square root of a square really easy. 16y to the 8th, the square root of that is 4y to the 4th plus 1 squared all over 16y to the 4th dy. And that is really nice because we can take the square root of the numerator and denominator. So we're integrating from 1 to 3. The square root of a square is just the stuff, 4y to the 4th plus 1, over. The square root of 16 is 4, and the square root of y to the 4th is y squared. dy, almost to the point where we can do some calculus. We're integrating from 1 to 3. Let's divide both parts by the 4y squared, and we end up with y squared plus 1/4 y to the negative 2 dy. These problems often require a lot of algebra to get us to a point where we can actually take the integral. Don't be afraid to mess with the algebra, work with it, and get us something that we can actually take the integral of. This integral is actually really easy to take. It's y cubed divided by 3. We're going to subtract, because when we increase the exponent by 1, we get y to the negative 1 over 4, integrated from 1 to 3. And I'm actually going to write that a little nicer. Y cubed over 3 minus 1 over, let's bring the y down, 1 over 4y, integrated from 1 to 3. Plug in the limits of integration. 3 cubed is 27, divided by 3 is 9, minus 1 over 4 times 3 is 12, minus, plugging the 1 in, gives us 1/3, plus, plugging the 1 in gives us 1/4. And this simply plugs into our calculator. 9 minus 1/12 minus 1/3 plus 1/4 gives us a total length of 53/6. Again, the integration's really simple, just using the formula. There's might be some algebra you need to do, though, to get yourself all the way through to a point where you can take the integral. So that's arc length. To find the arc length, we just take the integral from a to b of the square root of 1 plus the derivative squared dx. The other half of the question, though, was how do we find surface area? And again, we're going to set surface area up with the idea behind what we're doing. So let's say we have some function, some curve. And we're going to rotate it around the x-axis. And we want the surface area of that shape. Up to this point, we spent a couple days doing the volume of that shape using shells, discs, and washers. Now we want the surface area. We don't want to fill it with paint. We want to paint the outside. Well, similarly, though, we're going to take a cut out of it. Small little cut out of it. And when we lay it out flat, that ends up being a cylinder. And if I were to slice that cylinder and open it up, we end up with a rectangle. It's a two-dimensional rectangle because we're dealing with just the surface area, not the thickness. We don't care about the thickness. Now, the dimensions on this rectangle are interesting. First, let's take a look at this little thick piece. That thickness that we're looking at is really a piece of the entire arc length. So that height is really a piece of the entire arc length. The height of this rectangle is going to be the arc length as it goes across. The radius of this circle is simply the function, f of x. The base of this rectangle, then, is the distance around the circle as we open it up. That's the circumference, which is 2 pi times the radius of f of x. So if we put it all together, the surface area of just this piece is going to be 2 pi times f of x, the length, times the height, which is the piece of the arc length. Now, we want all of the surface area pieces, the entire surface area. So again, we're going to integrate from a to b to get all the pieces added together of 2 pi times f of x times the arc length. Well, 2 pi is a constant, so we can pull that out front. So the surface area is the 2 pi times the integral from a to b of f of x times our arc length. And this is the formula we've been using thus far. We already have it. It's 1 plus the derivative squared dx. And so this formula becomes the formula for the surface area of a curve rotated around the x-axis. And if we rotated around the y-axis, we would just switch all the x's for y's and do it with respect to y. So if that's our formula, let's do some examples to see if we can use this formula. See if I can leave the formula on the screen. See if I have enough space. Let's let f of x equal the square root of 1 minus x on the interval from 0 to 1/2. And we're going to rotate on the x-axis. We're going to find the surface area. Well, we know from our formula we don't just need the function, we also need the function's derivatives. So let's find those pieces first. So the function f of x is 1 minus x to the 1/2 power. Its derivative is, bring the 1/2 out front, times 1 minus x to the negative 1/2 times the derivative of the inside, which is negative 1. So let's write that as negative 1 over 2 times 1 minus x to the 1/2 power. Now we're ready to plug it into our formula for surface area. It's equal to 2 pi times the integral from our limits of 0 to 1/2 of our function, 1 minus x to the 1/2, times the square root of 1 plus the derivative, which is negative 1 over 2 times 1 minus x to the 1/2, squared dx. This integral is very easy to take. The algebra to get there will require some digging, though. So let's dig into this algebra. First, let's square that derivative. So we have 2 pi times the integral from 0 to 1/2 of, let's change this back to a square root. It's going to actually be easier that way later. Times the square root of 1 plus negative 1 squared is 1. 2 squared is 4. And when we square the 1/2 power, we're just left with 1 minus x dx. Let's do the common denominator thing again. I'm going to multiply by 4 times 1 minus x on top and bottom so that we can have a common denominator and write that out. When we do that, we get 2 pi times the integral from 0 to 1/2 of the square root of 1 minus x times the square root of, I'm going to go ahead and distribute, so we have 4 minus 4x plus 1 over our common denominator of 4 times 1 minus x dx. Continuing to simplify, we've got 2 pi times the integral from 0 to 1/2 of the square root of 1 minus x times, let's break that square root in top and bottom. 4 plus 1 is 5 minus 4x over, on the bottom, the square root of 4 times 1 minus x dx. And this is going to start to become really nice because we've got a 1 minus x under a square root and a 1 minus x under a square root. Those will divide out. Square root of 4 is 2, so I'll pull a 2 out. But that's really nice because we've got a 2 on top and a 2 on bottom, so those all divide out. So with all that said, our integral simplifies down to pi times the integral from 0 to 1/2 of the square root of 5 minus 4x dx. That's the algebra needed to get us down to an integral we can actually take. We're going to use u substitution of 5 minus 4x du is equal to negative 4 dx. So we'll multiply by negative 1/4 outside and negative 4 inside. And now we have negative pi over 4 times the integral. Plugging 0 in for u. 5 minus 0 is 5. Plugging the 1/2 into the u equation. 4 times 1/2 is 2. 5 minus 2 is 3. And we're just left with u to the 1/2 du. Seems like my integration's backwards between the 5 and the 3. So let's switch them. Remember, we can switch them as long as we change the sign on the outside. So we'll make it a positive pi over 4 times the integral from 3 to 5 of u to the 1/2 du. Integrating, we get u to the 3/2 times 2/3. Integrated from 3 to 5. 2 over 4 will reduce with a 2 in the denominator, so we're left with pi over 3 times 5 to the 3/2 minus 3 to the 3/2. And this will be the surface area of our curve between 0 and 1/2 when it's rotated around the x-axis. Let's wrap up with one more example. This time we're going to rotate on the y-axis and see how that impacts things. Let's say our function is f of x equals the square root of 9 minus x squared. And x is going to run from the square root of 5 to 3. And we're going to rotate on the y-axis. And that's significant because if we rotate on the y-axis, we have to take the derivative with respect to y. Basically, the only extra step we have is to convert everything into y's. So let's start with, we've got x equals the square root of 9 minus, I'm sorry, not x equals, y equals 9 minus x squared. If we square both sides, we get y squared equals 9 minus x squared. Add x squared to both sides, subtract y squared from both sides, and then take the square root, we get 9 minus y squared. It's basically the same function, which is kind of interesting. To get our limits, we're going to plug the square root of 5 in for our x. So we get the square root of 5 squared is 5. 9 minus 5 is 2. We'll plug the 3 in. 3 squared is 9. That goes to 0. And let's just put them in order. We're really integrating then from 0 to 2. We still need to know the derivative of our function so that we can plug it into our equation. So we've got x prime, the derivative is 9 minus y squared to the negative 1/2, pulling the 1/2 out front, times the derivative of the inside, which is negative 2y. It's nice because the 2's divide out, not the y's. So when we simplify, we're left with negative y over 9 minus y squared to the 1/2 power. There's our derivative. Okay, we have the pieces we need. Now we're ready to go after the surface area. Surface area is 2 pi times the integral from 0 to 2, we said, of our function, that's the square root of 9 minus y squared, times the square root of 1 plus the derivative squared. So let's write out every step here. Negative y over 9 minus y squared to the 1/2 squared dy. And this is the integral we need. Again, the algebra is going to take some work. This integral is even easier than the last one to actually evaluate. But we have to do a little bit of algebra to clean it up to make it like we want. So let's work with it. We have 2 pi times the integral from 0 to 2 of the square root of 9 minus y squared times the square root of 1 plus, let's go ahead and square. We've got y squared over 9 minus y squared. Let's do that common denominator thing again by multiplying by 9 minus y squared on top and bottom. Oops, I forgot the dy. So now that's equal to 2 pi times the integral from 0 to 2 of the square root of 9 minus y squared times the square root of 9 minus y squared plus y squared over our common denominator of 9 minus y squared dy. Cleaning up, we have 2 pi times the integral from 0 to 2 of the square root of 9 minus y squared times, notice the y squares divide out, or subtract out, negative y squared plus y squared is 0. We're just left with the square root of 9 on top, which is 3, over, we've got a square root of 9 minus y squared in the denominator, dy, which is really nice because that square root divides out. And so the integral we're actually going to take is 2 pi times the integral from 0 to 2 of 3 dy. That integral we can take really quick. It's 2 pi times 3y integrated from 0 to 2. Or 2 pi times, 3 times 2 is 6, minus 0. We are left with a surface area of 12 pi. So what you start to notice with these problems, both surface area and arc length, the integration step's quite simple, but we'll have to work with the algebra inside that formula to get it to a spot where we can take an integral a bit nicer. All right, take a look at the homework assignment. We're doing surface area formula and the arc length formula. Practice a few of these, and we will discuss these in more detail in class. Using a lot of these concepts behind volumes and surface area and arc length, we can solve several different physical applications. Today we're going to take a look at work and force. We're going to answer the question, how do we calculate the work done by a force? And we'll start simple and kind of build to the more complex. We're going to start by first talking about the fictional one-dimensional objects. And how we can calculate the mass of this one-dimensional object. How much stuff is stuffed into this one-dimensional object. And the idea behind this is we're going to have a thin rod on the x-axis. So it's this long, straight, skinny thing. It's so skinny, it doesn't have any width or depth. It just has length. It's just one-dimensional. And it's going to be over the interval from a to b. And rho, that's a Greek letter, rho, looks kind of like a p. Rho of x gives the density of this rod at the point x. Turns out that the mass of this rod is the integral from a to b, how much stuff there is underneath this curve of the density rho of x dx. So the mass of a one-dimensional object is simply the integral of the density function. So for example, if I have a rod over the interval from 1 to 3, where the density is given by rho of x equals 2x squared plus 3. If I wanted to calculate the mass of this guy, we would simply need to integrate over the distance from 1 to 3 of that density function, 2x squared plus 3 dx. We should be really good at this. We end up integrating, we get x cubed, 2x cubed over 3 plus 3x integrated from 1 to 3. Plugging in our limits of integration, 3 cubed is 27. 27 divided by 3 is 9, times 2 is 18. Plus 3 times 3 is 9. Minus, plugging 1 in, we get 2/3 minus 3. If we run that through our calculator, we'll get 70/3 for the total mass of this function. Now, one-dimensional objects aren't real, but they can give us an idea how the more complex two-dimensional functions work. We're going to work with two-dimensional circular objects, or disks. Kind of like a CD, if you remember those. If I have a two-dimensional circular object with no real width, it's just two-dimensional, how do we find its mass? Well, similarly, we've got a function. Rho of x is the radial density of the disk, the density of that radius with radius r. Then the mass equation is simply 2 pi, it's a disk, so you have to see pi in there, right? Times the integral from 0 to the edge of the disk, the radius. And now, because we're in 2 dimensions, we have to account for x and the x distance that we are away from the axes times the density function dx. So in 2 dimensions, if we're looking for the mass of our circular disk, we'll have 2 pi times the integral from 0 to r of x, p of x dx, or rho of x dx. So for example, what we're talking about there is if rho of x equals 3x plus 2 is the radial density of a disk with radius 2, we're going to find the mass. Well, using our equation, mass is just 2 pi times the integral from 0 to the radius, 0 to 2, times x times our row equation of 3x plus 2 dx. Or if we distribute that x through, we're really taking the integral of 3x squared plus 2x. So that's going to be x cubed plus x squared. Oops, don't lose the 2 pi out front, though. 2 pi times x cubed plus x squared integrated from 0 to 2. Plugging those limits of integration in, plugging 2 in, we get 8 plus 4. Plugging 0 in, we get 0. And that's 12 times 2, or 24 pi for the mass of this two-dimensional disk. Let's extend then to another application, and that is the work that is done by a spring. The work done to stretch or compress a spring. First off, in general, the formula for work is going to be the integral from A to B of the force that's applied. So specifically in the context of a spring, we know that the force is equal to some constant that varies based on the spring times x. So that means work for the spring is going to be the integral from A to B of kx dx. Now, a couple notes on springs. We must be in feet and pounds or joules and meters, depending on which units we're in. If we're not in the correct units, you do have to switch the units. Also, A and B are the length of the stretch. Not the length of the spring, but how far the spring is being stretched. So let's see if we can solve a spring problem. Let's say a spring has length 50 centimeters. And it takes 3 joules to stretch it to 60 centimeters. We want to know how much work it will be to stretch it from 60 centimeters to 70 centimeters. It was 3 joules just to go from 50 to 60. Would it be 3 to go from 60 to 70? Well, let's see how it works out. First thing we're told is we're told the amount of work, this is the work, used to stretch to 60 centimeters. So from 50 to 60 centimeters, we're actually stretching from 0 to 10 centimeters. That's the actual stretch. Those are our A's and B's. But the problem is those are in centimeters. So when we change those to meters, we divide by 100 from 0 to 0.1 meters. So our work is the integral from 0 to 0.1 kx dx. Evaluating this, keeping k as a constant, we end up saying that the work is k over 2 times x squared integrated from 0 to 0.1, or 0.1 squared times k over 2, or 0.005 k. And this is interesting because they actually give us the amount of work. We said it was 3 joules. So 3 joules must be equal to 0.005 k. And if we divide both sides by 0.005, we find the constant, the stretch constant for our spring is 600. Notice we had to first find the stretch constant for the string before we went to answering our question. Question wants to know how much work it's going to take to stretch it from 60 centimeters to 70 centimeters. Well, actually, from 60 to 70, 60 already is an increase of 10 centimeters. To 70 is an increase of 20 centimeters. But we need to change that to meters. So from 0.1 to 0.2 meters. So we're integrating from 0.1 to 0.2 times our constant, which is 600, x dx. And now this is the integral we need to solve. X squared divided by 2 leaves us with 300x squared, integrated from 0.1 to 0.2. So we have 300 times 0.2 squared minus 0.1 squared. And when we do that, we end up with 9 joules of work to stretch from 60 centimeters to 70 centimeters. So it takes a lot more work to stretch because we're further down. There's more tension on the string, or on the spring, when we're going from 60 to 70 than when we're going from 50 to 60. All right. Now we're ready to get to the real good problems, and that is talking about the force of water. And to set this up, first, in general, force can be calculated as the density of what's pushing against it times the distance it has to travel times the volume of what we're taking the density of. When we're talking specifically about the force of water, we can know that the density of water is equal to either 9,800 newtons per cubic meter or 62.4 pounds per cubic foot, depending on if we're in the metric or SI units. So let's do a couple water force problems. First, what we're going to do is we're going to pump water out of a tank. Let's say we've got a cylindrical tank. And it has a radius of 3 feet. It is 10 feet tall. The water itself is not full to the brim. The water is 2 feet down from the top, which means 6 feet from the bottom. What we need to do is take all this water and we're going to pump it up and out of the cylindrical shell. We want this cylinder to be completely empty. Well, let's give it some dimensions. Let's say this top, we're going to call that top x equals 0, the bottom x equals 10, which means where the water stops is x equals 2. And we're going to just take one tiny disk out, kind of like a CD. It's so thin, it's just going to have a width of dx. If we just look at the amount of force it's going to take for that disk to be pumped out of this cylinder, we'll use our force formula. First, the density, that's water. We're in feet, so the density is 62.4 pounds per cubic feet. Times the distance that it has to travel up. So x started at 0. So whatever x is, that's going to be the depth of that disk. So if x is 6, we're 6 feet down. If x is 3, we're 3 feet down. But whatever x is, that's the distance that disk has to be pumped up and out. The volume of that disk, it's a cylinder with a tiny little height of dx. So volume is pi r squared. Pi times the radius of 3 squared times the height of dx. Well, simplifying a bit, 3 squared is 9. And 9 times 62.4 is going to be 561.6 pi times x. That's what's required to pull out that disk out of the water, to pump it out of the tank. Now, we don't want just that disk, but we want all of the disks from a depth of 2 all the way down to the bottom at depth of 10. And we know to do that, we need to integrate from a depth of 2 to a depth of 10 our expression. Let's pull the constant out. 561.6 pi times x dx. So we have 561.6 pi times x squared divided by 2, integrated from 2 to 10, which is equal to 561.6 pi times 10 squared is 100, divided by 2 is 50, minus 2. And this we just have to plug into our calculator. And when we do, we get a total work done of 26956.8 pi. So about 26,000 pi, almost 27,000 pi foot-pounds. Let's take a look at another example using water. This time what we're going to do is we're going to look at the force against a dam. Let's say we've got a dam here holding back water. It's a small dam. It's 10 feet long and only 5 feet tall. And actually, the water itself on the other side starts 1 foot down. So there's only actually 4 feet of water pushing against this dam. We want to know how much force is actually being pushed against this dam. Now, we remember we've got this equation that the force is equal to the density times the distance times the volume. So if we take a sliver, like we did before, a really skinny sliver of width dx, for our density, we're still talking about water, and water has a pressure of 62.4. The distance that we have to travel, if x is 0 at the top, we're 1 foot down. So we're off by 1. We lose 1 foot of water at the top. So it's not just going to be x. But we need to subtract off the 1 foot of the dam that's not actually putting any pressure on the wall. So we'll call it x minus 1. And then we multiply by the volume of this strip that we cut. Well, this strip we cut has a distance, a length of 10. and a width of dx. And it only pushes on 2 dimensions, only on that rectangle. So we don't have to multiply by anything else, just 10 times the dx. And so when we simplify this, we end up with 624 times x minus 1 dx. That is the force against that little tiny strip. Of course, we want all the strips from 1 foot down to 5 feet down. So to get that, we'll take the integral from 1 to 5, pull the constant out, 624 times x minus 1 dx. Or 624 times x squared over 2 minus x, integrated from 1 to 5, which is equal to 624 times, plugging 5 in, 25 halves, minus 5, minus, plugging 1 in, 1 half, plus 1. And when we put that in our calculator, we end up with 4,992 foot-pounds of pressure against this dam. So we've looked at several different physics applications here today in this video. Take a look at practicing some of them on the homework assignment. We'll talk about them more in class, and we will see you then. Today we're going to take a look at another application of integrals, and that is answering the question of how do we find the center of mass. The idea here is kind of like a teeter-totter. If you want it to balance perfectly, or maybe spinning plates would be a better example. If you want it to balance perfectly, where is the center of the mass that will balance perfectly on a point? We're going to start by looking at the simplified one-dimensional option. First, looking at the discrete situation. Discrete basically meaning we've just got points on the x-axis. And the way we find the center of balance with a bunch of points is first we need to identify the mass. The entire mass, what we'll do is we will sum or add up all the individual values of the mass. And that calculates our total mass. To find the center of that mass, we're going to find m sub y, which is going to represent the moment away from the y-axis. M sub y, the distance from the y-axis, that moment from the y-axis, is the sum of the product of the individual masses times the individual x values. And that will give us the moment. And then to actually calculate the point where the center of balance is, we will take the moment function and divide by the mass function. So we have 3 equations here to help us build the center of mass, with the key one being at the end when we divide the 2 pieces. So in 2 dimensions, we'll first find, in 1 dimension, we'll first find the total mass, then we'll find the total moment away from the y-axis, and then we'll find that x bar, that center of mass, by dividing those values. So for example, if I put my first mass of 12 kilograms at x equals -4, my second mass of 12 kilograms at x equals 4, and this is in meters, and my third mass has 30 kilograms, and I put it at, we should be numbering these x's, 1, 2, and 3. We put it at x equals 2 meters, and we put our fourth mass of 6 kilograms, and we put it at x4 equals -4 meters. We want to know where to put the center of balance so that this balances out perfectly. First, we'll calculate the total mass. We find the total mass by finding the sum of the individual masses, which is 12 plus 12 plus 30 plus 6. And so that's going to come out to 60 kilograms for our total mass. Next, we'll find the moment function for the y, which is the sum of the mass times the x value. Notice we multiply by the opposite coordinate from what the moment asks for. It's the moment of y. We're going to multiply by the x. So we'll do 12 times the first x of -4 plus the second mass 12 times the second x of 4 plus 30, the next mass, times its location 2, plus 6 times -4, multiplying the mass times the location. And when we add all that up, we get 24 kilogram meters. And now to find the center of balance, x bar, we just have to divide your my, 24, by your m of 60. And when we reduce that, we'll find out that it is 2/5 of a meter away from the origin. Will cause this situation to balance perfectly. So that's one-dimensional, discrete, with our mass, moment, and center function. But what if it's not discrete? What if it is continuous? With continuous, we'll see some type of row function that represents the mass over that continuity. Well, similarly, we'll first calculate the mass, which is going to be the sum of all of the masses along our interval. Well, that would just be the integral from a to b of the row dx. We'll also find the moment function in the y direction. And just as before we took the x's times the mass, we're going to also take the x's times the mass function and integrate it from a to b to get all of our individual moments added together. And then to find our center, x bar, we simply will take that moment and divide by the mass, like before. Again, our goal is that x bar, but all three of these help us get there. So let's try a continuous example where we have to calculate where is the center of balance. Let's say rho is going to be equal to x cubed on the x interval from 0 to 3, and we want to know where this is going to balance. Well, first we'll calculate the total mass, which is the integral from 0 to 3 of our function, x cubed dx, which is x to the 4th divided by 4, integrated from 0 to 3. And if we plug 3 in, we get 81 over 4 minus 0. So our total mass is 81/4 kilograms. Our moments away from the y-axis, that's going to be the integral from 0 to 3 of x times our function, x cubed dx, or the integral from 0 to 3 of x to the 4th dx, which is x to the 5th divided by 5, integrated from 0 to 3. And 3 to the 5th is 243 divided by 5 minus 0. And so we have our moment. And the way we calculate the center of balance is we divide that moment, 243 over 5, by the 81 over 4. And we can multiply by the reciprocal, 4 over 81. And when we reduce, we get 12/5. 12/5 is where this x cubed will balance perfectly between 0 and 3. This has all been in one dimension, though, so let's make this a little more interesting. In 2 dimensions, we'll again first look at the discrete case to set up the continuous case. With the discrete case, now we're not just talking about points on the x-axis, we're talking about points in general. Again, we'll start by calculating the mass, which is the sum of all of the m's. And again, we'll calculate the moments away from the y-axis, which is the sum of the masses times the x-coordinates. And then we'll also calculate the moments away from the x-axis, the other direction, which is the sum of the moments times the y-coordinates. Once we have those, we can calculate x bar, which is the y moment divided by the mass, and y bar, which is the x moment divided by the mass. And that will give us our center point that we're looking for of x bar, comma, y bar. So in 2 dimensions, we just kind of extend that same formula, considering both the x and y coordinates to get our formulas. So let's try if I took a single mass of 5 kilograms and I put it at the point -2, -3. And I took a second mass of 3 kilograms and I put it at the point +2, +3. And I took a third mass of 2 kilograms and I put it at the point -3, -2. Where would the center of balance be for these 3 masses? Well, first, we need to know the total mass. 5 plus 3 plus 2 equals 10 kilograms for the total mass. Next, we'll find the moment in the y direction, which is the x-coordinate, the mass times the x-coordinate. So we'll start with the first mass was 5 times its x-coordinate of -2, plus 3 times its x-coordinate of 2, plus 2 times its x-coordinate of -3. And that gives us -10 plus 6 minus 6, that's -10. We also need to find the moment in the x direction where we multiply by the y-coordinate. So the first mass of 5 times its y-coordinate of -3, plus 3 times 3, plus 2 times -2. That's -15 plus 9 minus 4 is also -10. Interesting that it's the same. So then to find our x bar, we'll use the m sub y. I'm going to label that. We can use that one to get the x bar, because they're both the same number. I don't want to lose which one we used. -10 divided by the mass of 10 gives us -1. Y bar, we use the second one, which came from the moment of x. -10 divided by 10 equals -1. So this time our center that we're looking for is at the point -1, comma, -1. The continuous version of this, then, as you might expect, just alters the formula slightly. And with continuous functions, if we're finding the center of balance or the center of mass, we call it a lamina. And here we're going to talk about laminas that go to the x-axis. If they don't go to the x-axis, it's a little different, and we'll talk about that in a minute. So first, we have to calculate our mass. As you might expect, we have to add up all the individual masses. That's just an integral from a to b of the function that represents the masses, dx. Then we'll find the m sub y, which again, as you might expect, similar to the last continuous case, is x times f of x dx. But when we find the moments from the x-axis, this one's quite different. The integral from a to b of, and we actually take our function squared divided by 2 dx. It's a little different than you might expect. It comes from having to solve for the other variable, but we're not going to get into the derivation right now. Once we find those two moments, we can then find x bar again by taking my divided by m, and we can find y bar by taking mx divided by m. And so again, our center is x bar comma y bar. So this is the continuous version of our formulas. So let's see if we can solve a continuous case. Let's say we've got a function that is bounded above, or a region that's bounded above, by f of x equals x squared, and below by the x-axis on 0 to 2. We want to find its center of mass. Just to get a visual idea of what we're looking at, this function starts at 0, goes to 1, 1, goes to 2, 4. Bounded from 0 to 2. So we have this kind of a triangle. It's got a curved left side to it. We want to see where is that shape going to balance. We're going to find the exact point. To do that, first we need the total mass, which is the integral from 0 to 2 of our function x squared dx, which we know is x cubed over 3 integrated from 0 to 2. And 2 cubed is 8/3 minus 0. So we just have 8/3. Then we need the moment of y, which is the integral from 0 to 2 of x times our function, which is x squared, dx, or the integral from 0 to 2 of x cubed dx, which gives us x to the 4th over 4, integrated from 0 to 2. 2 to the 4th power is 16, divided by 4 is 4. To find the m sub x, this is the weird one. We're going to integrate from 0 to 2 of our function squared divided by 2, which gives us the integral from 0 to 2 of x to the 4th divided by 2 dx, which is x to the 5th divided by 5 times 2, or 10, integrated from 0 to 2. 2 to the 5th is 32. So we have 32 over 10, which reduces to 16/5. Now we're ready to find x bar and y bar. X bar is the moment from y, which is 4, divided by the 8/3, or 4 times the reciprocal of 3/8 gives us 3/2. For the y's, we'll take the 16/5 and we'll divide by the mass of 8/3, which is equal to 16/5 times the reciprocal 3/8. Reducing gives us 6/5. And so we found the center of balance at x equals 3/2, y equals 6/5. So 3/2 and 6/5. It's going to be somewhere around there on our graph. Will perfectly balance that triangle. Now I mentioned this is only going to work if we're bounded below by the x-axis. If we're not bounded below on the x-axis, we need a slight adjustment to our formulas. So let's look at still continuous. So we still have what's called a lamina. The lamina this time is between functions. Similar to how we found the area between two curves, we just need to subtract the two functions. So our mass function is still the integral from a to b, but this time we'll subtract the functions f of x minus g of x dx. For our moment function, it's in the y direction. It's still going to be the integral from a to b. And we're still going to do x times f of x. But this time, before we multiply by the x, we have to subtract g of x. So x times the difference in the functions, dx. And the moments from the x, from a to b, it's still going to be the function squared divided by 2, but we're going to square the functions and then subtract them. Let's move the divide by 2 out front as 1/2, just for the sake of space. And then it's going to be f of x squared minus g of x squared dx. And once you have those, you can find x bar, as always, by dividing the moment from y by the mass. Find y bar by dividing the moment from x by the mass. And these functions will help us find the center of balance, or the center of mass, between two functions on an interval from a to b. So let's do one last example where we do just that. Let's say we want the space that's bounded above by f of x equals 6 minus x squared, and below by g of x equals 3 minus 2x. To kind of get a picture of what we're looking at, actually, let's move it a little more center. The above function, 6 minus x squared, looks like this. And the below function, 3 minus 2x, looks something like this. And so we've got this mass that we're trying to find the center of balance for. Looks like it's probably going to be around here somewhere. But that's just kind of eyeballing it. A little to the right. Maybe it's a little too high in that picture. But we want to find out, where is that center of balance? So to do that, first we find the total mass. The total mass is the integral from a to b. Well, we have to find these x coordinates of where it's going to intersect. Where is this space going to start and end? You can derive that by hand by setting them equal to each other and solving. Let's do that kind of up above in this space. 6 minus x squared equals 3 minus 2x. Adding everything to the right, we get x squared minus 2x minus 3. X minus 3 times x plus 1. So x equals 3 and negative 1. So we've got negative 1 to the left, 3 to the right. So we're integrating from negative 1 to 3 of the difference in the functions. 6 minus x squared's on top, minus the 3 minus 2x. Remember, that changes both signs. Let's combine like terms before we integrate. The integral from negative 1 to 3 of 3 minus x squared plus 2x dx is going to equal 3x minus x cubed divided by 3 plus x squared integrated from negative 1 to 3. Which means, I guess I don't need a parentheses, 3 times 3 is 9. Minus 3 cubed is 27, divided by 3 is 9. Plus 3 squared is 9. Minus 3 times negative 1 is a positive 3. Being careful with our signs, we've got to subtract a negative. But then when I do the negative 1 cubed, it also becomes a negative 1/3. And then plus 1 minus 1. And when we put that all together, 9 minus 9 plus 9 plus 3 minus 1/3 minus 1, we should get 32 over 3 for our total mass. All right, let's find the moment for y, which is the integral from negative 1 to 3 of x times the difference in the functions. 6 minus x squared minus the other function, which is 3 plus 2x, dx. Combine like terms and distribute the x through. 6 minus 3 is 3 times x is 3x. Minus x squared times x is x cubed. Plus 2x times x is 2x squared. Integrating, we have 3x squared divided by 2 minus x to the 4th divided by 4 plus 2x cubed divided by 3 integrated from negative 1 to 3. Plugging 3 in, 3 squared is 9 times 3 is 27 halves. Minus 3 to the 4th is 81 fourths. Plus 3 cubed is 27 times 3 is 54 thirds. Minus, plugging negative 1 in, we get 3 halves. Minus a negative is positive. Negative squared to the 4th power is a positive 1/4. Minus, but negative 1 cubed is a negative again, positive 2/3. And we put that in our calculator, we'll get 32 thirds for our moment in the y direction. Now for the moment in the x direction. This one's going to be probably the most involved, going from negative 1 to 3. We have the 1/2 out front times the first function squared. The top function is 6 minus x squared squared minus the second function squared, 3 minus 2x squared dx. Squaring everything gives us the integral from negative 1 to 3 of 1/2 times 36 minus 12x squared plus x to the 4th. And then we're subtracting. So 3 squared is 9. Then we have 12x. It's a negative 12x, but when we subtract it, it becomes a positive 12x. And then negative 2x squared becomes a negative 4x squared dx. which, let's pull the 1/2 out because that's a constant, from -1 to 3. Of combining like terms, we've got an x to the 4th. We've got -12 minus 4 is -16x squared. Making sure we don't lose anything here. Next, we've got a 12x. And then we've also got a 36 minus 9 is a positive 27 dx. So when we take the integral, we have 1/2 times x to the 5th divided by 5 minus 16x cubed divided by 3 plus 12x squared divided by 2 gives us 6x squared plus 27x integrated from -1 to 3. So plugging 3 in, we have 1/2 times 3 to the 5th is 243 out of 5 minus 3 to the 3rd is 27. 27 divided by 3 is 9 times 16 is 144. Plus 3 squared is 9 times 6 is 54. Plus 3 times 27 is 81. And then subtracting, being careful with signs, -1 to the 5th is -1/5. Subtracting -1/5 makes it positive 1/5. -1 cubed gives us -16/3 with a negative in front, which is a positive 16/3. And when we subtract it, we get -16/3. Very careful with our signs. -1 squared just gives us 6. So we subtract the 6. And then we subtract a -27, which is a positive 27. And if I put that all in my calculator and tell my calculator to change that into a fraction, we get 416 out of 15 for the moment in the x direction. Lots of work, but we finally got through it. It's mainly algebra. The calculus is pretty straightforward. Now to figure out our x bar, we take the moment from the y direction, which is 32 over 3, and divide by the mass, which is also 32 over 3. So the center of balance for x is 1. For the y bar, we take the moment in the x direction of 416 out of 15, and we divide by 32/3, which is 416 out of 15 times the reciprocal of 3 out of 32. And I'm just going to do that on the calculator. And that's going to equal 13/5. So finally, we have the coordinates of our center of balance, the center of mass, at 1, 13/5. So that's how we can do it. If they're between two functions, we just have to subtract the functions, adjusting our formulas. I do want to show you one little trick that comes up sometimes. It doesn't always apply, but when it does, it's really nice. We want to use symmetry whenever possible. It can save you a lot of work. For example, if I have x plus 3 squared plus y minus 4 squared equals 4, and I were to graph that, turns out that that's going to be a circle with a radius of 2, centered at -3, 4. See if I can draw a nice little circle here. And if that's a nice little circle, I know the center of the circle, because it's symmetrical about the x and y axis. The center is going to be right there at -3, 4. And we're done. We don't have to go through all the equations to find those points. Although if we did, we'd get -3, 4. So that's really nice and can save you time. More often, it'll give you one coordinate. You'll notice it's symmetrical around x equals 0, so x bar equals 0. And then you have to do the work to find the y bar. Or you know the y bar because it's symmetrical, and you have to seek the x bar out. But that can save you a lot of time if you catch some symmetry to your shape before you go through all the calculations, which is why I strongly suggest you always graph the function before you go through the algebra. So take a look at these on the homework assignment. Practice finding some centers of mass, and we will see you in class to discuss these centers of mass in more detail. Today we're going to take a look at something that's going to feel like a review conceptually. However, now that we have the fundamental theorem of calculus and we're looking at applications of that, we can gain a new understanding of the true definition of integrals related to exponential functions and logarithms. The question we're going to answer is, how do we define exponentials and logarithms? And we're going to start with some definitions, because up until this point, we have used logs and e to the x and natural log and just kind of waved our hands over it and said it's just a thing that's been defined in such a way that. Well, now that we have the fundamental theorem of calculus, we can have our formal definition of the natural log. The natural log is defined by natural log of x. It is defined as the integral from 1 to x of 1 over t dt. This is the formal definition of the natural log. And what's nice is, out of that definition, from the fundamental theorem of calculus part 1, you'll remember that the derivative of the left side is going to be equal to the function on the inside with the top piece plugged into it. So the derivative of the natural log of x is formally defined then as 1 over x. We're also going to formally define the number e such that from this definition, the natural log of e, which is equal to the integral from 1 to e of 1 over t dt, that integral will equal 1. E is the value that makes that integral 1. Turns out to be a little bit more than 2 and a little bit less than 3. We'll also define e to the x then such that the natural log of e to the x, or the integral from 1 to e to the x of 1 over t dt, is going to be simply equal to x. And what that establishes is an inverse relationship between e to the x and natural log. The natural log of e to the x is x, and e to the natural log of x will be x as a direct result. This gives us a couple additional properties that we can use with our derivatives and our integrals. Consider e to the x natural log of a. Now, our properties of exponents say a double exponent really means an exponent has been raised to an exponent. This is really saying e to the natural log of a to the x power. But because we have this inverse relationship, e to the natural log of anything is just that base. So e to the natural log of a becomes simply a, and we still have the x power on the outside. And in this way, we define any exponential as e to the x natural log of a. Why is this significant? Well, it's significant because now we can consider the derivative. So let's call this subpoint A. Now we can consider the derivative of a to the x because we know that's the same as the derivative of e to the x natural log of a. And then, using the chain rule, we can say e to the anything, the derivative is that, x natural log of a, times the derivative of the inside. Well, the natural log of a is just a constant, so we have times the natural log of a. However, this e to the x natural log of a is simply equal to a to the x, based on our original definition, natural log of a. And so what we've really done is we have defined the derivative of anything to the x as that anything to the x times the natural log of a. And that's where that definition comes from initially. Before we just stated it and claimed it, now we have formally proved it. We can similarly do exercise to calculate the integral of a to the x dx, because that's the same thing as the integral of e to the x natural log of a dx. Using u substitution, we'll let u equal the x natural log of a. Therefore, du is going to be the natural log of a dx, because that natural log of a is just a constant. We can multiply it inside and 1 over it on the outside. And that's going to give us 1 over the natural log of a times the integral of e to the u du, or 1 over the natural log of a e to the u plus a constant, which is equal to, and I'm just going to stick that e to the u in the numerator as I do this. Substituting back to x's, we have e to the x natural log of a all over the natural log of a plus our constant. But again, because we know e to the x natural log of a is equal to a to the x, this is going to simplify to a to the x over the natural log of a plus a constant. And what we've done is created a definition for the integral of a to the x dx. It's equal to a to the x over the natural log of a plus a constant. Previously, we just stated this was true. Now what we've done is we've actually proven it's true, all based on this original definition that the natural log of x is the integral from 1 over x of 1 to x of 1 over t dt. And so these consequences come out of it, and what this provides is a true understanding of how the natural log and the e to the x exponential function work and what their definition is. However, the emphasis of this lesson is going to be on actually taking derivatives and integrals with these functions. So let's first look at derivatives. And you've seen these derivatives before. Now we just understand why they work instead of just claiming they work. The derivative of the natural log of sine squared x. Well, by the chain rule, we take the derivative of the outside times the derivative of the inside. So the outside is 1 over sine squared x. The derivative of natural log is 1 over the stuff, times the derivative of the inside. Well, the inside's an exponent problem, 2 sine x, times the derivative of its inside, which is cosine x. And this one will clean up really nicely. The sine gets rid of one of the signs. And cosine over sine, we know from trig, is just the cotangent of x. And so the derivative of the natural log of sine squared is 2 cotangents. Let's try this one. Let's take the derivative of the natural log of x squared plus 3x plus 1. Again, on the outside, the derivative of the natural log is 1 over the stuff over x squared plus 3x plus 1. And the chain rule says we multiply by the derivative of the stuff, 2x plus 3. And we don't have any simplifying there, so that will be our final derivative. Let's do one more. Let's take the derivative of the natural log of x squared, and then we'll take the whole thing to the 4th power. One thing that I see before we start solving this, to make it easier to work with, we can pull that 2nd power in front of the natural log, because an exponent inside the natural log can be moved out front. So what we end up with is 2 natural logs of x to the 4th power. Now, using the chain rule, on the outside we have an exponential, so we take 4 times the inside stuff, which is 2 natural logs of x, all raised to the 3rd power. Times the derivative of the inside. The derivative of 2 natural log of x is just 2 over x. And so what we end up with is, careful, that 3's got to go into each part. So we've got 2 to the 3rd power, which is 8, times 4 times 2 is 64 natural log of x cubed all over x. That's a quick review of taking derivatives with logarithms. That wasn't the only type of derivative we took with logarithms. If you remember, we also did what was called logarithmic differentiation, which was based on implicit differentiation whenever we had the variable in both the base and the exponent, or sometimes just to make more complex expressions simple. So for example, if we had y equals x to the sine of x power, and we wanted to find dy dx, before we took the derivative, we would first take the natural log of both sides, because when we took the natural log, the exponent would move out front, and we would have sine x, natural log of x. Then we could take the derivative. On the left, we get 1 over y dy dx. On the right, we've got the product rule. The derivative of sine is cosine x times the natural log of x, plus the derivative of natural log of x is 1 over x times the sine of x. And then to get the expression dy dx alone, we would multiply both sides by the y. And so we'd end up with dy dx is equal to the cosine of x, the natural log of x, plus the sine of x divided by x, times y, but y is the original expression, times x to the sine of x. And that would be our derivative. And that logarithmic differentiation was very helpful on these problems that would otherwise be impossible. But in addition, logarithmic differentiation gave us a much easier way to find dy dx when y is equal to something like e to the x sine of x over the square root of x times the natural log of x. We could, on this one, use the product rule in both the numerator and denominator within the quotient rule of the entire problem, but that would be a huge expression to simplify. This becomes much easier if we first take the natural log of both sides. because we know that the numerator, being a product, is logarithms added to each other. So we take the natural log of both sides. We'll end up having a positive e to the x, a positive sine of the x. In the denominator, denominators are made by negative exponents. So those are going to be negative natural logs. So what we end up with when this spreads out is the natural log of e to the x plus the natural log of sine x minus the natural log of, I'm going to write it as x to the 1/2, minus the natural log of the natural log of x. And this can be even simplified further to make life easy by pulling these exponents out front. And so we end up with the natural log of y is equal to x times the natural log of e, which is just 1, plus the natural log of the sine of x, minus 1/2 natural log of x, minus the natural log of the natural log of x. Now the derivative is much nicer. On the left, 1 over y, dy dx. On the right, we have 1 plus the derivative of natural log is 1 over the stuff, times the derivative of the stuff, the derivative of sine is cosine, minus 1/2. Derivative of natural log is 1 over x, minus the derivative of natural log is 1 over the stuff, natural log of x, times the derivative of the inside, and the derivative of natural log of x is 1 over x. And so finally, to get our solution, we multiply both sides by the y to get dy dx equals, simplifying a bit as we do this, 1 plus cosine over sine is cotangent x, minus 1 over 2x, minus 1 over x natural log of x, times y, but remember y is the original function, e to the x, sine of x over the square root of x, natural log of x. And that derivative was much easier using logarithmic differentiation than it would have been using regular differentiation in the product rule and the quotient rule. All right, so now that we've reviewed derivatives with logs and exponentials, let's also review integration, the antiderivative. Let's first start with number 1. Let's first do the integral of x squared over x cubed plus 6 dx. Quite often with these, our key to make them work is going to be to use substitution. And you notice that denominator x cubed plus 6 has a derivative du of 3x squared. So we'll multiply by 3 and 1/3 to get 1/3 times the integral of 1 over u du, which is really nice because that's 1/3 times the natural log of u plus a constant. But we have to change back to x's, so for our final answer, 1/3 times the natural log of x cubed plus 6 plus a constant. Let's try another one. Let's do a definite integral this time. Let's do the integral from 0 to 1 of 4 over e to the x dx. Actually, let's do 4 over e to the 3x dx. One thing to make this easier to integrate that I'm going to do is I'm going to write that as the integral from 0 to 1 of 4e to the negative 3x dx. Now we can see straightforward that this is just a u substitution, where u is negative 3x and du is negative 3 dx. Oops, forgot the dx on the first example. So we'll multiply by a -3 inside and a -1/3 outside. And when we do, we get 1/3 times the integral. And we'll plug the limits of integration into u. -1/3. 0 times -3 is 0. 1 times -3 is -3. And one thing I might notice here is those limits of integration are kind of backwards. We usually go smallest to highest, but right now we're 0 is bigger than -3. We can switch those and go from -3 to 0 if we also switch the sign in front of the integral. So we'll go from -3 to 0 of 4e to the u du. Which is 1/3 times 4 e to the u, because the integral of e to the u is e to the u, integrated from -3 to 0. So if we plug those limits in, we get 1/3 times 4 e to the 0 minus 1/3 times 4 e to the -3. And I'll do a little bit of cleanup on that. E to the 0 is just 1, so we have 4/3 minus 4 over 3e cubed. In fact, we might even get a common denominator by multiplying by e cubed to get 4e cubed minus 4 over 3e cubed for our final answer. Let's do one last integral to wrap up here. This is my favorite integral using logs and substitution because it's not exactly obvious right away that we're going to go that direction. And it's the integral of tangent x dx, and cotangent's very similar. We don't have a direct way to get to tangent of x because there's no antiderivative of tangent of x. We don't know of any derivative that gives us an answer of tangent. However, we can rewrite this problem as the integral of sine x over cosine x dx. And when we do that, now we're set up for a u substitution, where u is the denominator, cosine of x, and du is the derivative of cosine, which is negative sine x. Well, we need a negative sign in there, so negative in and out. Dx. So we have negative integral of 1 over u du, which is equal to the negative natural log of u plus a constant. Or going back to our x's, we get negative natural log of the cosine of x plus a constant as the antiderivative of the tangent. So again, today feels like a big review of integration and derivatives with logs and exponentials. But what's nice is now we have a clear definition of what the exponential is and what the natural log is so that we can work with them. We're going to build on this concept by doing some applications of exponentials and logs with tomorrow's lesson, but for now we're going to get really good at reviewing how these exponentials and logarithms work. So take a look at the homework assignment, practice several of these, and we'll see you in class to work on them further. After experimenting with the natural log and the exponential e to the x and seeing how they actually come from calculus definitions, it's good to take a look at some applications of those natural logs and exponentials, which generally center around exponential growth and decay. So the question we're going to answer is, what are some applications of the natural log of x and e to the x? And the first application is going to be exponential growth. Where things are growing by some constant. And actually with exponential growth, we have this guiding equation y equals y sub 0 e to the kt. And this equation is going to kind of guide everything that we do today, but specifically in the context of exponential growth. First, labeling a couple things here. Y is the final amount. Y naught, or y sub 0, is the initial amount. K is some constant, which varies based on the situation. And then T is time. And so, for example, exponential growth might be seen in a population. Let's say the population of a bacteria grows 5% per year. Actually, no, let's say 5% per day. It's a bacteria. Bacteria grows pretty fast. If there are 500 bacteria present in some culture, bacteria, how long until there are 10,000 bacteria? Well, using our exponential growth equation, y is the final amount. We want to have a final amount of 10,000. Y naught is the initial amount, the 500. E to the k, that's our growth constant. Here we know it's 5%, 0.05. And T's the time we're looking for. That's what the question's asking us about. Well, to solve these type of equations, we first are going to isolate the exponential part. So we'll divide by 500. When we divide by 500, we get 20. So we have 20 is equal to e to the 0.05t. Taking the natural log of both sides to get at the exponent, we end up with the natural log of 20 is equal to. The natural log of e is going to always simplify to the exponent. So that's going to be 0.05t. And so to finish solving, we just divide by 0.05t, and we get the natural log of 20 over 0.05. So our calculator can really quickly tell us what the natural log of 20 is divided by 0.05, making sure I close the parentheses on the natural log. We get about 59.91. So 59.91 hours of 5% growth will move this bacteria from 500 to 10,000. Another context where we see exponential growth would be with continuous interest. Interest is when you make an investment and it grows, and the interest could compound annually, which means you get the entire percentage at the end of the year, or monthly, which means that percentage is split up into 12-month increments, or weekly, divided into 52 increments, or daily, divided into 365 increments, or minutely, secondly. And if you keep going and take the limit as n goes to infinity, you get continuous interest that it's always growing at. And it's actually the exact same exponential growth equation. So we can use that equation to answer questions such as, what is the annual growth of 8% compounded continuously? In other words, what percent has it grown at the end of a year, at the end of the annual period? It doesn't give us an investment amount. It actually works the same regardless of the investment amount. So let's say our initial investment amount is 1. That makes the math easy. So we want to know what the final amount is. So we invest 1, e to the growth rate of 0.08 times time. We're talking about 1 year. So we can see how much this is going to grow by. So we have 1 times e is just e to the 0.08 times 1. I really just have to type in the 0.08. And when I hit enter, I end up with 1.0833. Let's round that to 33. 1.0833. And if I convert this to a percentage by moving that decimal point over, I can see after 1 year, I have 108.33% of my initial investment. Well, 100% is actually what I invested. The growth, it wants to know what the growth is. That's the 8.33% growth. So this investment gets 8% compounded continuously, which turns into an annual growth of a little more, 8.33%. Continuous interest. Another place we could see an application of exponential growth is in what's called doubling time. If I know how long it takes something to double, that's going to reveal to me what the constant is that I'm working with. The constant is the natural log of 2 divided by the time it takes to double. Now, if I had a tripling time, it would be the natural log of 3 divided by the tripling time. If it was multiplying by 10, it'd be the natural log of 10 divided by the tripling time. Whatever we're multiplying by, but usually we're talking about a doubling time. So, for example, let's say a population doubles every 15 years. How long will it take it to grow to 10 times its size? Again, we're not told the initial size or the final size, but it turns out it works out the same regardless of what those are. We just need to make sure that our final size is 10 times the original. So I always choose 1 for the original, because that makes the math easier. 10 times that means we want a final size of 10. E to the k power, which is the natural log of 2 divided by the doubling time of 15 years, times t, the time it's going to take to get there. Since 1 times e is just e, we don't have to divide by anything in front of it. We can jump to taking the natural log of both sides. And when we take the natural log of e, we'll just end up with its exponent, the natural log of 2 divided by 15 times the time. Which means to solve for t, we'll multiply by 15 on both sides and divide by the natural log of 2 on both sides. And that'll give us the time. Be very careful as you type this in the calculator. As you do 15 natural log of 10, make sure you close the parentheses on the natural log before you divide by the natural log of 2, closing the parentheses. And that's going to give me 49.83. So how long is it going to take? 49.83 years to grow to 10 times its initial size. So that's exponential growth. Exponential growth is y equals y naught times e to the kt. The opposite of exponential growth is going to be exponential decay. which is really similar. We're just shrinking instead of growing exponentially. The only difference in this formula is we're going to have a negative constant. Y equals y naught times e to the negative kt. If it's negative, that means we're decaying or shrinking. And very similar to talking about doubling time, we have what's called the half-life. And that's the amount of time it takes a population or a group of stuff to shrink down to half of its original size. And very similar, the constant for a half-life is the natural log of 2 divided by the half time. I'll just call it the time. Because the exponent is negative, that's what gives us the 1/2 equivalent instead of a doubling time. So because that exponent is negative, it's going to shrink to half 1/2 instead of doubling to just the 2. For example, this works great with dating really old things. Half-life of carbon, it's carbon-14 technically, is 5,730 years. In other words, every 5,730 years, half of carbon decays away. One of the Dead Sea Scrolls was tested in the year 2000 and found to have 81% of its carbon-14 remaining. What year is it from? Approximately, because with all dating of old relics, there's always a little bit of fudge in it. We're talking about half-lives, so we want to have 81% remaining. That's a good final number. If we start with 1 initially, 81% of 1 is 0.81. E to the constant, remember it's a negative constant because we're talking about decay and shrinking. With half-lives, the constant is the natural log of 2 divided by the time, 5,730 years, times t, the amount of time or the age of this relic. Whoops. We don't really need the 1 out front. We do need the e, though. Taking the natural log of both sides, we get the natural log of 0.81 is equal to the natural log of e gives us the exponent, negative natural log of 2 divided by 5,730 times time. So to solve for the time, we'll multiply by negative 5,730 times the natural log of 0.81, and then divide by the natural log of 2. So negative 5,730, natural log of 0.81, make sure I close the parentheses, divided by the natural log of 2, closing the parentheses. And we end up with, let's round it to the nearest year, about 1,742 years old. But be careful, the question was not asking how many years old it is. It wants us to estimate what year it's from. So this study was done in 2000. It was 1742 years old at that time. So when we subtract, we'll get approximately 258 AD as the year this scroll must have been originally written. And that's the mathematical process that they often go through to date old relics. In fact, more often this method is used to prove fake relics. You'll see something that they claim was something that belonged to John the Baptist, the cousin of Jesus Christ in Israel, but they carbon date it and they find out that it came from the year 500. Well, that doesn't work in the timeline, so it's obviously a fake. So this is often used to identify fake relics or to verify a legitimate relic. Very interesting, though. Half-lives and carbon dating. Another example of exponential decay, it's got a little bit of a variation on a theme, but it is quite interesting to us, is Newton's law of cooling, where we say the final temperature of some item is its initial temperature minus the air temperature times e to the negative kt, how much time goes by, plus the air temperature. So just to label, TF is the final temp, T sub O is the initial temp, T sub A is the air temp. And then lowercase t is time, so let's not get lost in all of the t's. If I have a pot of coffee that is poured at 180 degrees Fahrenheit, after 5 minutes of room temperature, and for all sake, we'll say room temperature is 72 degrees Fahrenheit, it cooled to 160 degrees. The question that we have is, when will it be cool enough to drink? And let's say cool enough to drink means 150 degrees Fahrenheit. The big piece of information we're missing here is what is the constant cool of this type of coffee. So we're going to run through the whole equation with this initial information given to us. It starts at 180 degrees. That's the initial temperature. After 5 minutes, that's the time. Room temperature, the temperature of the air is 72. It cooled to 160. That's the final temperature. Let's put this in our equation. The final temperature is 160 equals the initial temperature of 180 minus the air temp of 72, e to the negative k, that's what we're looking for. T, the time, is 5, plus the air temperature, which is 72 degrees. We have to isolate that e. Just like solving equations, we'll subtract first. 160 divided by 72 is 88. Equals 180 minus 72 is 108. E to the negative 5k. Dividing both sides by 108 and reducing, we'll get 22 over 27. E to the negative 5k. To get at the exponent, we take the natural log of both sides, 22 over 27, equals, the natural log of e just gives us the exponent of 5k. So k, our constant, is the natural log of 22 over 27 divided by negative 5. Now that we have an expression for the constant, we can answer the question. When will it be cool enough to drink? When will the final temperature be 150 degrees? So 150 degrees times 180 minus 72 times e to the negative. Notice we've got a negative negative, so it's actually going to be a positive. K is the natural log of 22 over 27 divided by 5 times the time plus the 72. We're going to solve this much the same way. We'll subtract the 72 to get 78. equals 108 e to the natural log of 22 over 27 divided by 5t. Divide by 108. When we reduce, we get 13 out of 18. E to the natural log of 22 over 27 divided by 5 times t. Take the natural log of both sides. Natural log of 13 over 18 is going to be equal to the exponent, which is the natural log of 22 over 27 divided by 5 times t. And if we multiply by 5 and divide by the natural log of 22 over 27, we end up with our final temperature. So pulling up our calculator, 5 natural log of 13 over 18, closing the parentheses, divided by the natural log of 22 over 27. To get our final amount of time we have to wait before we drink of about 7.95. 7.95 minutes. This coffee will be ready to drink. Almost 8 minutes. So we looked at 2 equations today and a couple variations on a theme. Exponential growth and exponential decay. Very similar equations. Decay has a negative on the constant. Growth does not. Take a look at practicing some of these applications of logs and exponents on your homework assignment, and we will meet in class to discuss these further. Good luck.